Hello there, my name is Ahmed Fathi and I will be your instructor for this course. I am a senior machine learning engineer with 10 years of experience and a master's degree, and I actually like to think of myself as someone who can take a very complex and long topic and convert it into an even longer topic, but much more simpler. And this is exactly what I plan to do in this course. This course is a comprehensive deep dive into reinforcement learning. We will cover a lot of concepts, a lot of ideas, a lot of intuitions, a lot of proofs, a lot of algorithms, a lot of derivations, and by the end of this course I am pretty confident that you will be very comfortable with reinforcement learning in general. Now, reinforcement learning is nowadays used in a lot of different domains, probably the most famous of which is tuning large language models to be great at mathematics, at reasoning, and at programming. And this is why I have a complete section towards the end of this course that purely focuses on using reinforcement learning algorithms alongside large language models. However, reinforcement learning is actually used in multiple other domains. For example, it can be used like in robotics, it can be used in recommendation systems, in games, in healthcare, in energy optimization, in finance and trading, and multiple other domains. So it is really a very general framework that you can apply to many different domains. Tuning large language models is just the famous use case of reinforcement learning nowadays. In this course, we will start from the very basics of reinforcement learning and then keep progressing and adding more and more complexity until we are 100% comfortable with how reinforcement learning is used in a real world setting. Now, I happen to prefer a more traditional teaching experience where I have my electronic pen here and my electronic blackboard, and I draw my illustrations and write my equations in real time as I speak. I really prefer this over just having slides and scrolling through them. So I really hope that this is also what you prefer, because this is what I'll be using in this course. And in general, I really hope that you enjoy this course. See you in the next video. So in this lecture, I would like to walk you through some real world interesting success stories of reinforcement learning that will hopefully make you interested in learning more about this topic. Now, on a very high level, reinforcement learning is the field of machine learning where an agent learns from direct interaction with the environment. You do not give it direct supervision. You don't tell it, in this situation you need to do this, in that situation you need to do this. It just learns via trial and error, via interaction with the environment, and then it could receive either a positive reward or a negative penalty, and using those rewards and penalties it just learns something useful, and eventually it can excel at a lot of interesting tasks. So in this video, I'll just show you some examples of those real world success stories, and probably the most trendy of those right now is training or tuning large language models to be able to think, to be able to generate those chain of thoughts and to solve mathematical problems, and even to be very good at programming or coding. So for example, if you fire up any large language model like Gemini right here, and you can also move to the thinking process or thinking mode, and then I could just ask it, please solve like this equation for me and state your chain of thoughts, and then I type like f of x is equal to like maybe x squared plus 4 is equal to 0, and then I would like it to think and try to solve like this equation. So after some time it gives you a response, and here I have show thinking, and then those are like the chains of thoughts. So it says here, I am solving this equation, I am working on solving the quadratic equation, my focus is something, and then it actually moves through those steps and then gives you an answer, which is a correct answer. It is plus or minus 2i. So this is the chain of thoughts and a correct mathematical solution Probably under the hood there was some sort of tool calling as well, so maybe there's actually called some Python script in order to solve this equation, but the mere fact that it understood that I really need to write a Python script and call a Python script to solve this equation is also another success of reinforcement learning actually. So tuning large language models is a multi-step process. Reinforcement learning is only one part of it, but it is the one most responsible for like mathematical correctness and programming correctness and so on, and we will see this in the last section of this course. So this is one of the examples. Another very famous classical example now is AlphaGo. So researchers in Google managed to teach a reinforcement learning software or a reinforcement learning agent to beat humans, to beat expert humans at a very complex game called Go. So this is similar to chess, but it is more complex than chess, and obviously reinforcement learning also can beat humans at chess as well. So this is the field of classical games. Reinforcement learning is really good at those kinds of games nowadays. Another super fun example was teaching a reinforcement learning agent to beat humans at like Atari games. So this is a paper that we will actually cover more in the course itself, like human level control through deep reinforcement learning. And you could actually find this architecture. They give the reinforcement learning agent a video feed of an Atari game, and they don't give it anything else, and through trial and error the reinforcement learning agent tries to maximize the score, and it tries to understand how to play this game and successfully actually beats humans at a lot of those like Atari games. Nobody tells it the rules of the game, nobody tells it what to do to win, what to do to lose, no supervision at all. It just records or like observes the rewards and try to improve. And you could see in this paper that in a lot of games actually it achieves like super human performance. And for some visualizations there is this GitHub repo right here you could check out. So those are the kinds of like Atari games that reinforcement learning worked quite well to win really. Another fun example where reinforcement learning was used in control, you can find it in this paper by Stanford. It is a pretty old paper now, but researchers managed using reinforcement learning to teach a helicopter to do some fun and cool like movements and so on. You can actually find a video about this on YouTube, also by Stanford. So I mean, this helicopter was trained using reinforcement learning to do some different kinds of like maneuvers. So let's have a look. Okay, I think this is like enough. I just would like you to understand that reinforcement learning is like a general framework. You can use it for different domains, and it is used in multiple other domains, not just robotics, not just games, not just LLMs. It is also used in recommendation systems, in health systems, in energy optimization systems, and generally in many systems that require complex decision making. Okay, so welcome to the first lecture of the course actually, and I'm actually recording this lecture like way before my future self records the introductory lecture, or like the lecture where he should do a great job at making you interested in reinforcement learning by, you know, showing up some of the great success stories of reinforcement learning in different fields and domains, and, you know, show you some visualizations and so on. I'm really not sure what he did at this moment. I hope he did a good job. If he didn't, just let me know and I will have a talk with him. So now let's actually start diving into the actual topic. So reinforcement learning. Reinforcement learning is the branch of machine learning where we want to teach the software, or what we call an agent, we want to make it learn from experience by interacting with the environment without clear supervision. So what do I mean by this? You know, in supervised learning, you could have a data set where you have a situation and the best action to do at this situation. Then another situation, then the best action to do at this other situation, and so on. So you have kind of supervision. In this situation, do this. In that situation, do that. So that's what we call supervision in this context. In reinforcement learning, we still want to teach some agent, like a robot, to do the best possible actions, but we really don't have this data set of which action is better or is best at every specific situation. Instead, we would like to design algorithms that make this robot or agent or anything interact with the environment for some time and then receive feedback from the environment regarding what it did. And based on this feedback, it could be a good feedback or a bad feedback, like positive rewards or negative rewards, we say in the terminology of reinforcement learning. It should update its actions somehow, like change its action. It should say, you know what, I took this action and probably that wasn't the best action, right? Like, for example, you could be like a businessman and then you take a loan that you can't pay back in time, and then you just work for a while, and then you eventually go bankrupt and you go to jail. And so you say, you know what, I went to jail. That's a pretty negative reward signal. I probably should not have taken a loan, right? So that's the kind of thing, roughly, what we are trying to do. Okay, I mean, we will cover this in more detail later, but let's just say that the main component we care about in reinforcement learning is what we call an agent. An agent. Right? So, what is an agent? The agent is the entity that can take actions and, do something, right, in the environment. So I always like to attach like a mental model or an easy thing to visualize or to recall to every term. And actually in the first couple of lectures, unfortunately, they might be a little bit boring because we will be introducing a lot of concepts, a lot of definitions, a lot of terminology. But I really would like you to attach a small and simple like idea or visualization or mental image to every term we add. So for an agent, I would always like to use the the resemblance to a small kid, a little kid, like let's say 2 or 3 year old kid. That's because kids at this age are not very great at following instructions, mostly, or at following supervision. Like you could tell a kid, please don't do that, and they will do that anyway, right? You could ask a kid, please don't drink from this, hot cup of tea, but they will try drinking from that hot cup of tea anyway. And then they might feel it's like too warm or like too hot for them, and then they will receive a pain signal, and maybe they don't like the taste anyway, so it could be a double pain signal, which is in reinforcement learning terminology we call a reward, like a negative feedback or a negative reward. And then they will learn from experience that touching or drinking hot cup of tea or hot cup of coffee is not something you would like to do again, right? So kids are very experimentation oriented, they are very exploratory, like in a sense, and that's why I think they are a little bit, close to reinforcement learning agents. Also, kids are like, they start with really blank knowledge of the environment. They don't know much. Like they don't know what is a street, right? What is a car? What will happen if a car hits me? They don't necessarily know that. That's why they could just, run away in the street and cross across the street, right? And do some risky moves. They don't know that maybe some people are not very good. Like they should interact with everyone around them in the same way, and so on. So this is in a way similar to the agent state that we start with. Like, as we will see, like in the future, an agent could eventually be just a neural network, and we will see those like a lot. A neural network starts with random weights, like randomly initialized weights. so it doesn't really know anything useful. And then we would like to design algorithms to train this network in a way that makes it able to take better and better decisions or actions, we say in the reinforcement learning terminology, via training. The same happens with the kid. The kid starts with no experience, and then they just interact with the environment and do stuff, and maybe they do something and they receive a reward in the form of pain, or in the form that that their parent is now like smiling, so this is kind of an encouraging reward, or the parent is like angry and this is a bad reward, like a negative feedback reward, and so on. So they start really with nothing and then they evolve over time. So I really like to attach the idea of a kid to the concept of an agent, but then you could also attach an idea of a robot or even of yourself. Okay, so an agent is able to take actions into the environment, but the agent does not fully control the consequences of their actions. And this is very important. Like, you could be, you know, the greatest software engineer ever, like you took a great degree from a great university and then you really passed all the interviews in the job of your dreams, but then something completely out of your control happens, like COVID-19, right? Now every flight is off and you can't really go and travel to the place where the company wants you to go, right? So now you don't have a job. Even though you did everything, you took all the correct actions and so on, the environment has a say in that, right? Yeah, so this is a very important like concept in reinforcement learning, which is the state you end up in, we call stochastic, or has some stochasticity in it, depending on the environment or the external factors, right? Similarly, like a kid could try to run and cross the street. Now, so the action the kid is taking is cross the street. What happens could be different. Like maybe the parent is not paying attention and the kid really crossed the street and maybe a car like hurts him. That's one way the environment could react. And the other way is the parent could be paying attention, right? And then he just gets the kid and puts it outside the way of harm. So again, the same action, but different like next states or different like conclusions, and also different rewards. So if the car like hurt the kid, that's a very negative reward. If the car didn't hurt the kid, this probably maybe, you know, a zero reward for the kid. The kid is still annoyed because he wants to do something, maybe a little bit negative immediate reward for the kid, but a huge positive, what we call long-term reward or cumulative reward. And this is also a great like concept, or a very important concept in reinforcement learning, which is we don't really care that much about immediate rewards. We would like to maximize what we call the long-term reward, right? That's what we want to teach the agent. So we would like to teach the agents, or like, you know, make the agent weights, if it's in your network, adapt in a way that it makes it choose the actions that maximize what we call the long-term cumulative reward, right? Because if you, for example, leave the kid like cross the street, the kid might be happy because it did something it wanted. So the immediate reward is like, you know, positive before it gets hurt, right? Or he or she gets hurt. So the immediate reward is positive, but the long-term reward is very, very bad. Now, if you take the kid away from the way of harm, the immediate reward is actually negative because the kid is annoyed because you didn't let him like cross the road. But the long-term consequences is actually good, and so you want to maximize the long-term or the cumulative reward. Again, we will actually formalize all those things in like pure mathematical terms moving forward. I just wanted to give you a very broad overview of what we're trying to do in reinforcement learning. Okay, let's continue in the next lecture. Okay, so in the previous lecture, we introduced the concept of an agent. We also actually, in a way, introduced the concept of an environment And in reinforcement learning, the environment is really like all the external factors that are not in your control as the agent, okay? We also talked a little bit about what we call like reward, right? Reward signal, either positive or negative. It could also be like immediate reward or the long-term reward, right? And we said that our goal in reinforcement learning is really to maximize the long-term cumulative reward, not the immediate reward. Like one example for that is like if you are playing chess. Now, if you eat one piece of the enemy's like pieces, that's a short-term reward, but it doesn't really guarantee that you win the game, the full game. And so if you are teaching like a computer or a software via reinforcement learning techniques to, you know, beat humans at chess or like be perfect at chess or very good, then the agent shouldn't focus so much on like eating the pieces at the beginning of the game. It should actually plan or think about ways or like strategies to win the game eventually, right? So that's the distinction between an immediate reward and long-term cumulative reward. Like in a way, also reinforcement learning is the, you know, field of decision making. You need to make actions or take actions or decisions over time. Like it is not really focusing on taking one single action. No, you start in a specific state or situation, right? And then you take an action. So you end up in a slightly different state or situation. You received some reward from the environment, and also the environment and its stochasticity made you move to another state or another situation. Then again, you take another action in that state, and then you receive another reward and another, you know, the environment interacts a bit with you and moves you or throws you in a third state, and so on. So in reinforcement learning, we care about this sequential action taking or sequential decision making in order to maximize the long-term cumulative reward, which in the case of chess is really winning the game eventually, right? So the game with chess has maybe a nice or an easy representation of states where the state is really the board configuration, right? Like maybe how the pieces are aligned, how many pieces are eaten from the, you know, the white team or the black team, sometimes gold and silver teams, and so on. So this is really the state of the board, the state of the game, the state of the environment, you know, whatever you call it. We will actually tweak a little bit what we exactly mean by state and what we exactly mean by environment and so on. Like later on, we are just still introducing some intuitive concepts. Now, the chess game is actually interesting in another sense, which is the environment in the chess is actually deterministic. It is not stochastic. Like I move a piece, I move, you know, a soldier from this position to this next position, right? And the environment can't really tell me no. Of course, as long as this is a legal move, the environment, there is no stochasticity. I can't move the soldier, you know, one step forward and then the environment just randomly, you know, spawns the soldier in a different position. This is not really what happens in chess. So in chess, we could say that the environment is a little bit deterministic, right? Like the transition probabilities, and we will define this term soon, is deterministic for the game of chess. But this is not always the case, right? This is not always the case. For example, you know, we mentioned some examples in the last lecture where you try to do something, but then COVID happens, and or like maybe tariffs happens, or some, you know, Cold War or like real war happens, and so on. So it could affect the next state or the eventual state. Okay. Also in chess, most like implementations of chess like don't really define positive rewards for eating specific pieces. So the intermediate reward is gonna be 0, and then if you win the game, you get a positive reward. if you lose, you get a negative reward, and maybe if it's a tie, you get 0 reward or something like that. In order for the agent to not try to optimize for those small immediate rewards and still lose at the end of the game. But I mean, that's not very important right now. So we just introduced those terms: agent, environment, and reward. Now let's actually introduce a new term. Not really new, but I want to talk about it a little bit more, which is this concept of state and also transition probabilities and so on. So in general, in reinforcement learning, we actually use those state diagrams that you will talk MDPs later on, but let's just think of them now as state diagrams. Now you have every circle here is a state. So maybe you have state A, maybe you are in a zoo, okay? And you are actually standing at the door of a lion's cage. Okay, so here let's define this state as standing at lion's door. Okay, so this is just the state. Now you are the agent in this example, and you can take multiple actions. You could, for example, keep standing. So maybe this is the most boring action, but you could choose to keep standing. But then you might be a little bit, risk taker, and you decide to go into the lion's cage. Probably not a smart idea, but then you could, maybe this is action 2 is equal to go into, or like maybe just call it enter to avoid writing too many words. So enter cage, right? Enter means enter cage. Now you can control that, right? Like you have the autonomy to decide something, but you can't control the consequences. Like if you enter the cage, there are maybe two possibilities. Maybe the lion is actually extremely hungry, and then what happens is, unfortunately, you end up in a state, let's call it SB, where you are unfortunately eaten, right? So I mean, that's just, bad luck maybe. So we could say that the reward you get here is maybe a negative 1,000 or something, and then that's just the end. So you reach what we call a terminal state, and that's it, like you're done, right? But maybe the lion was actually just had its lunch, and so it's not hungry, and then you just end up in a state where you could maybe you could take a selfie with the lion in its cage, right? And just post it on social media, and then the people standing outside the cage are all photographing you and so on. So you get, famous, you get rich and so on. And then this is really a positive reward in this case, right? So maybe this is positive 10 or something. I mean, it really depends on how much you care about this. So what I'm trying to say here is you take an action, right? But the environment could throw you away into this state or that state. You can't control that fully. It really depends on factors outside of your control. Okay, nice. Now, if you imagine this path, I mean, this path here, you just ended terminal state, you just died, right? But here you could have, more states, more stuff happening in your life. Maybe, an advertisement agency calls you, and then you do some advertisements, and you get, richer and so on. So every step here could have its own reward. And so maybe the cumulative reward is like large, and then you eventually die in your 90s, and you are still in a terminal state anyway. And we say that the, episode terminates. So, I mean, there is this concept of an episode or trajectory. And we'll talk about this later on, so don't worry about it. Okay, but again, you could think of this state diagram as some world, and then you still want to maximize the long-term, immediate the long-term cumulative rewards, not immediate rewards. And obviously in this specific situation, you would like to never go into this branch here, this branch here, but you can't control it. So someone might actually decide to only go into action 1, which is keep standing. Maybe the reward here is really boring, so maybe just +1, right? Versus here, where you could have either a very, very bad result here, or maybe a very good result here. So some people might just take the risk and go into this direction, or maybe some other people will just go into this direction and just go on the safe side, right? It really depends on how much risk you would like to take and so on. And this is also something we can control in our algorithms. How much do we want them to explore versus, you know, just do some what we call exploitation of the easy paths or something. I mean, this is something you can control, but generally you want to maximize the long-term average cumulative reward, as we will see. And to do that, you really need to know more information about the environment, right? Like, for example, which path should we choose, right? Like let's actually try to think about it. It really depends on the probability of the lion being hungry versus the lion being not hungry. Like if you are maybe in a zoo where the lion is really taken care of, you could say that the probability of this happening is very, very low, like maybe 0.0000001, right? In which case, maybe entering the cage is actually a good thing, because the probability of you like being eaten is not that large anyway, right? But in another situation, maybe this probability is like very high, maybe 50-50, maybe it's a horrible zoo. And so the risk now increases significantly, right? So what I'm trying to say now is there is something called the transition probability, right? And this is a function of the environment, right? Or like a property of the environment. Like the probability of you being eaten, given that your current state, so maybe we call this like the next state in reinforcement learning, so maybe the state at time t+1. So the probability of the next state at time t+1 is you being eaten, given that at state t you are actually standing at cage, or like lion's cage, and given also that you take the action at time t, which is action enter. Maybe this is just, you know, 0.1, something, 10% probability. And then the probability of the next state being like the selfie and famous and rich kind of path, given that at time t you are still also standing at cage, and the action is enter. Maybe that's higher. Okay, so this here is called, another term here, transition probability. And this is a property of the environment, like you can't control it. It's something that, you know, is a property of the zoo and the specific lion and, you know, the zookeeper and so on, like something you can't control as an agent, right? So the transition probability is a function or a property of the environment, and also the rewards are a property of the environment. You also can't control the reward in the reinforcement learning like framework or like workflow. You can't control the rewards you get. You just receive those rewards from the environment, okay? You can control the actions, yes, but you can't control what rewards you get based on those actions, right? Okay, let's continue in the next lecture. Okay, so in the last lecture, we introduced this concept of transition probability, and we showed how the environment, like next state, is a bit probabilistic or stochastic. And now we have a question, like, is this transition probability the only thing that is stochastic in reinforcement learning? And the answer is obviously no. We can also think of other things that are stochastic. The first one is the reward. The reward itself could be stochastic, could be modeled as being stochastic. It also could be modeled as being like deterministic. I mean, it depends on the problem, but in general, it is like stochastic. Like, think of it as, in some problems, maybe you are really in, like, you know, a gambling place, and you play some games, or maybe you pull some of those levers, right? And then maybe you pull it at some time and you receive some money, and maybe you pull it at another time and you don't receive anything. So sometimes the reward itself is actually like stochastic. And maybe in our example here, maybe the reward you get, or if somebody else does this path, maybe you are very lucky and you get really famous and so on. Maybe someone else actually does the same thing, and people are, no one cares about him, and so he has entered the lion's cage and he still didn't get rich. So I mean, the rewards could be stochastic, and in reinforcement learning we could kind of define something like the reward probability. So maybe you could define something as the probability of like reward given the state you were at, the action you took, and maybe the state you ended up in. This could be a probability distribution. Like, depends on if you model things as discrete probabilities or as continuous probabilities. So maybe you could define this actually as something like this. So maybe this is the reward value, and then maybe you either get a reward of 10 or a reward of 2, and maybe the probability of getting a reward of 2 is like this, and reward of 10 is like this, you know, and this is a probability. This is this term here, and so maybe this is here like 0.8, and this is 0.2. So in general, in the general term, we model the rewards in reinforcement learning as being also stochastic, and this is also another property of the environment, and we call it the reward probability, or the reward model sometimes, like the model of the reward, like the model of the probability distribution of the reward. So this is another thing that is stochastic in reinforcement learning. A third thing actually that is generally considered also probabilistic at reinforcement learning is what we call a policy. So the policy, denoted as pi generally in reinforcement learning, is really the probability distribution of the actions. So in this state, you can choose to keep standing or choose to enter. And this is something under your control, but it is still stochastic in the sense that you could choose either of those two like approaches, like two actions. So you could say the probability of, let's say, action 1, which is like maybe staying at place, given state SA, which is you are standing at the door of the lion's cage. Maybe you are very risk averse, and so this probability is like 99%. But then you have another probability of you actually entering the cage in this state. So probability of a specific action in a specific state, and those obviously need to add up to 1. So this will be only 1%. So again, the policy is stochastic, and the policy is just a mapping between a state and an action. Now, sometimes you actually have like deterministic policies, right? And sometimes you could have stochastic policies, and the reasons for this could be very different, and we will cover some of those like later on. But for example, let's say you are playing, rock, paper, scissors with a friend, right? So if you choose rock, you beat scissors, scissors beat paper, and paper beats rock, right? In this case, if your policy is always deterministic at every game, you'll eventually lose, right? Like if you always play scissors, the other agent or the other player or your opponent might actually exploit you and always choose rock, and then you will always lose. So this is a situation where a deterministic policy is really not a good thing at all. While in other cases, maybe a deterministic policy is better, right? Like you go to your workplace through the same route every day. It's a fun route. It's short and it's safe. So why change that? Why every day try a different route? I mean, it's already good enough. So sometimes in some problems, you have good deterministic policies. Sometimes the optimal policy, which is the best possible policy or the best possible policy that actually leads to the highest, cumulative reward on average, is deterministic. But sometimes it's also stochastic. Sometimes the optimal policy is stochastic, like this rock, paper, scissors example. The optimal policy is actually to be completely random, like to choose rock or paper or scissors at random for both players. Like both players need to be completely random for both of them to get the best reward, right? So in a way, we could define the reinforcement learning goal is find the optimal policy. We generally call that by star, and this is really the goal of reinforcement learning. Okay, see you in the next lecture. Okay, let's formalize things a little bit more. So you will often find this sort of diagram when people talk about reinforcement learning, where you have an agent, right? And you also have an external environment, right? And the agent takes action in the environment at time step t, as we said, right? And then the environment actually responds with changing the state into state of time step t plus 1, right? And the environment also provides reward we call rt plus 1 to the agent, right? This is the immediate reward. So you'll often find this diagram. It's a nice and compact diagram, but we need to think a little bit more about state. What is the state really? Is it the agent state or the environment state or both? Like in the lines example we covered previously, the state we used was a bit your own state, right? The agent's state, like you are either standing at the door of the lion's cage, or you are eaten, or you are like, selfie and rich and so on. So in a way, the state was the agent's state in this example. But you also need to know that the action you take doesn't only affect your own personal state, it also affects the environment state. Like you enter the cage, and so maybe the lion woke up, right? Or maybe the people outside the cage got very nervous, and the guards wanted to go in and save you and so on, right? So the action not only affects your own state, it also affects the environment state. And so in reinforcement learning, when most people talk about state, what they mean is the agent state, still the agent state, right? But also augment with it all what the agent could observe from the environment, okay? So that's why sometimes you'll also find this diagram here. Instead of having st plus 1, you'll have O t plus 1, where O is an observation, right? Observation. So people try to make it clear that the state is really the agent's internal state. Like if you think about a robot, the robot's internal state, it can measure, like it can measure its own speed or its own acceleration, or maybe, you know, the joint angles of itself as a robot, if it's like a, you know, a robot with hands or with legs, right? But also the state includes all the observations that the robot could see in the environment. Maybe the robot has a camera with like a face detector in that camera, and so part of the state is really, you know, the people that the robot sees, right? Or maybe it has a radar or a LiDAR or something. So all of this could be thought of as part of the state. And so when we talk about state, we mean the agent state, but we also mean the parts of the environment state that are first relevant to the problem, and second, the agent can actually observe. So if there is some part of the environment that the agent can never observe, typically this is not part of the state, except if the agent can also kind of estimate it, right? Like, let's say you are playing one of those card games where you have, like, you know, some card games, and then you can observe some of the papers, like some of the papers on the table, but you can't see what the other players have on their hands. In this case, we can call the other players other agents, but from your perspective, they are part of the environment because you really can't control their actions, right? But then you really know that the state of the game is not only the papers on the table, but also the papers in everyone's hand, but you can't observe all the papers all the cards in everyone's hands, right? But you can try to make some guesses, some beliefs somehow, so you can still try to estimate those you know, hidden parts of the state or something. I would also like to emphasize that when I say like state or observations from the environment state, what I really mean is what we care about, what is relevant to the current problem at hand from the environment state. Not everything, because really everything is really everything. If you really talk about the full environment state, you are still talking about, you know, the atoms and the electrons and maybe the processor, like clock speed, and like all of that is really part of the state of anything and everything, but not all of that is relevant to all the problems. So there are still some abstractions that you need to think about, right? Like if you have a robot that tries to hold cups, what it cares maybe about the environment state, which is the nature of this cup, is maybe its weight, maybe its material, like is it slippery or not slippery, something like that. It doesn't really care about you know, its state of origin, like where was it manufactured, you know, is it manufactured in Egypt or China or anywhere. It doesn't really care, it doesn't really matter for this problem. It is still like part of the state in a way, but it doesn't really matter, right? Similarly, if you are like playing a video game or something, what you care about is what is in front of you, like on the screen. You don't necessarily care about, you know, the binary numbers in the registers of the computer, something. This is still part of the state, but you don't care about it. It's not very relevant or not very highly relevant for your success at playing the video game, okay? Now let's introduce another important concept, which is the concept of observability. Can we observe all what we care about from the environment state or not? Now imagine you are playing chess, for example. So in chess, the two agents playing chess could fully observe the board, and that's maybe the best, or the that's the desired way, or that's the best configuration for reinforcement learning problems. Like you have full observability and try to solve it, but this is not always possible to have. For example, if you are playing those card games again, where like some cards are in the open and some cards are hidden in the other agent's hands or other players' hands, you have what you call partial observability. Now you would typically want to have as much full observability as possible, but if you can't, you still try to have some beliefs or some estimations of those hidden states, but it is a more difficult problem to solve. Note also that in those multi-agent problems like playing card games or chess or something, you could think of all the other agents as part of the environment state. Okay, so I mean that's just a point. But in general, in a fully observable situation, the distinction between the agent state and the environment state maybe doesn't matter that much. Maybe they are all the same state, which is kind of the case in chess, right? Like in chess, is the board, like what is it? It is the environment state, but it's also the agent state because the agent can observe everything in the environment. Maybe there's another, a piece where you need to know, which turn, whose turn is it? So this is also part of the state, right? It affects the dynamics of the game. For the same board configuration, it matters which one is to play next, right? Maybe you could also say that, okay, for chess, I'm not really fully observable because there is something about the fatigue level of my opponent. If my opponent is really tired and hasn't slept well, maybe he will play or she will play like worse, or vice versa. But then you could also argue that this doesn't matter that much. Maybe it matters, maybe it doesn't, because you want to reach an optimal policy where you could beat that opponent regardless of their fatigue level. So if you model your problem as I want to really beat my opponent no matter their fatigue level is, then maybe the fatigue level is not part of the state, right? Not part of the state you want, because you will just assume they are not tired and just play with it. If you would like to be more, fitting towards that fatigue level, then maybe this is part of the state, and then you will need to observe it and, make your actions based on that observation as well, right? I'm mainly trying to say that it is your responsibility as an engineer to design that state space, like what you care about, what you don't care about. This is your responsibility as an engineer, like designing this reinforcement learning solution framework, right? Okay, so we have like fully observable systems, and in general those are easier to solve, but you also have what you call like a partially observable system or systems, and those are harder to solve, but still they are solvable, and we will see how we could try to solve them as well in this course. One example is maybe a self-driving car, like a car that moves into the streets, but it has maybe only a camera. It doesn't necessarily know what's behind it, for example, or something, but it can somehow try to estimate it because you are moving and then you see the cars moving as well. And so you could build some mental map in this robot about what's behind you based on what you saw maybe at previous time steps or something like it is partial observability, and you need to do more work to solve it like in a proper way if you want to solve it using reinforcement learning. Another example for this partial observability would be like a robot trying to localize itself, which room am I in, but it exists in a tall building and it only has access to maybe some laser beams, so it could shoot a laser beam and kind of try to map the world or the room using those the distances to different walls and so on. But maybe multiple rooms have the same dimensions, and so it can't really say for sure which room it is in right now. So it has partial observability, and it needs to use more signals, maybe the history, maybe some time-based, estimation or something to kind of disambiguate those states. If it can't, then we exist in a situation where we have what we call state aliasing, where some states are different but are not distinguishable from each other at all because of the reduced observability. And we can think of ways to solve those kinds of problems. But in general, to solve a partially observable reinforcement learning tasks, we first try to convert it into a fully observable reinforcement learning task and then solve it using the methods and algorithms we will design and reach in this course to solve fully observable reinforcement learning tasks. So I'm trying to say that in this course, in the vast majority of this course, we are actually gonna focus on solution methods to the fully observable reinforcement learning problems, and then any partially observable problem, we will try to convert it to a fully observable problem and then solve it using the methods we will, work through in this course. Okay, that's it for this lecture. Let's see you in the next lecture. So in a lot of the examples we covered so far, we were kind of focusing on discrete state space problems, like when we talked about the person standing in front of the lion's cage. That was in a way a discrete state space. We could draw a state diagram with discrete states, right? Also, when we talk about chess is a discrete state space problem, and so on. But in reinforcement learning, we don't only care about discrete state space problems, but we also care about continuous state space problems. Like, for example, you could be controlling a robot, you could be controlling a rotation like a helicopter, right? And this helicopter has its position, its velocity, its acceleration, its angular position, its angular velocity, its angular acceleration, and every one of those numbers you would like to control in order to do some maneuvers or something, and every one of those is really a floating point number, like it is continuous. So the state in this case could be a vector of 6 numbers for velocity, acceleration, position, for both angular and linear velocity and acceleration and so on. So this is a different formulation, but we will see that the algorithms and the ideas we use to solve discrete state space problems, which are generally easier, will also generalize well to continuous state space problems with some tweaks that we will cover in this course. So we are not going to ignore that in this course. In fact, a big chunk of this course will actually be about this generalization when we cover like function approximation and so on later on towards the second half of the course. So don't worry about it. However, we will start with discrete state space representations and problems because they are easier a little bit, and at least some of them are easier, and the algorithms will really generalize and the core ideas are very similar. You might think that it's easy to solve like continuous state space problems by just discretizing the space. Like if you have a 1D robot in a factory and you want to control its position, right? Then the position is continuous, but you could just discretize the position into 1 millimeter like chunks, and then suddenly you have a discrete state space representation, which is fine. In some problems, this is actually very fine. But in some other problems, this is not very realistic, especially if you have a lot of dimensions and then you want a tremendous amount of granularity for every dimension and so on. And so it will not be as easy as that. And you will need to design algorithms or tweaks to make it really work with continuous state space representation. But I also would like to emphasize that it is not really the case that every continuous state space problem is harder to solve than every discrete state space problem. I mean, some discrete state space problems are extremely hard to solve and extremely like they need you to do very smart things in order for you to have an agent or train an agent to solve them effectively. Like, for example, let's actually start with a simple discrete space problem like the XO problem or tic-tac-toe problem. I mean, you have this grid and you are either team X or team O, and then you win if you do something like this or like this or like this. Obviously, this is not a valid state because once you reach something, one of them, you already won, right? And it really goes like in turn if you are not aware about this game. So X plays, then O plays, then X plays, then maybe O plays, a stupid move, then X does this, and then X wins, right? So the number of states here is actually not very large. It's also surprisingly not extremely small. Like every valid board configuration is its own like state, right? And so if you think about it, the upper bound on the number of states here is like you have 9 blocks, and every block could either be empty or X or O. So you kind of have an upper bound of 3 power 9. So this is the upper bound. However, the legal states are roughly around 5K, like people counted it. That's because this, for example, this configuration is not a legal one, because you already won, X already won here, so you can't really have this configuration. Still, like, this is not a very large number of states. Like, you could even define the optimal policy or optimal behavior by having a table, like in this state do this, in that state do that. Like, you could just have an array or like a dictionary in Python or something, 5,000 elements, and then you could just have the optimal policy, roughly, right? So this is an easy discrete state space problem. However, you could find harder ones like chess, as you might expect. So in chess, the number of legal states is sometimes like estimated between 10 to the power of 44 up to 10 to the power of 47. And actually, it's interesting that this is not a fixed number. It should be a fixed number, right? But it's not really the case, because some of those, not all of the states are legal, and for chess it's even more complex. You need to say that a state is legal, you need to show that it can be legally reached from the original start state where every team has their army at their position. Sometimes it's hard actually to say that for an extremely large state space problem like this. So if you want to solve this using reinforcement learning, you can't really have a table of the policy. You need to be smarter, and you need to use more complex algorithms. Like an even more like complex game is called the game of Go. It is also a board game, Go, and this one is very famous in the reinforcement learning community. I didn't play it like with my friends at all. I did play chess and I did play XO, but Go is like famous because it has much more states. It's even much more difficult than chess. You are talking roughly 10 to the power of 170. This is an insane number of states. Okay, so the fact that you might even think about creating a table, no, that's completely impossible. However, using reinforcement learning, researchers could create very good systems at playing Go and at like playing against humans and so on. So you need to be smart about it. And all what I'm trying to say is those are discrete state space problems which you might think are very easy to solve, but they are really not easy to solve. And there are obviously a lot of continuous state space problems that are much easier to solve than those kinds of discrete state space games. Okay, so I think that's what I wanted to say in this lecture about continuous versus discrete state spaces. In the next lecture, I'll talk about something similar, which is actions as well could be discrete or continuous, but let's leave that for the next lecture. So similar to what we said about states, actions also could be discrete or continuous. Like a discrete action could be, like move left, right? Or move right, or move up, or move down. Something like this, or maybe touch the hot cup of coffee. Like it is a discrete action. But also you could have continuous actions where you increase the speed of the car by specific number, or maybe the steering wheel of the car, like move it or rotate it by a specific angle. So this angle could be also continuous. So again, in reinforcement learning, we care about both, and in this course, we will care about both. But again, we will start with discrete actions and discrete states, and we develop the core ideas in this world, and then we will see how we can generalize to continuous actions and continuous states. Also, you could have, continuous action but discrete state space, or like maybe continuous state space but discrete action. Like for example, if you are playing a video game or an Atari game, the actions are discrete, right? Like you are either move left, right, up, down, or maybe shoot, right? But the state itself could be continuous, like the position of the plane into the game, or the character, or its speed and so on, or the car. Like you could have continuous states but discrete actions, and you know, the mixes, all the mixes, you could have them. So that's another interesting point. While we are at it, another quantity in reinforcement learning that could also be continuous or discrete is time itself, like time, right? We kind of always in reinforcement learning talk about you know, state at time step t and state at time step t plus 1, t plus 2. But what is this quantity? Like, what is this quantization? Is this like a second, a minute, an hour, a day, a month, a year, right? Like it really depends on your problem. It could be a millisecond, a microsecond, anything. It depends on your problem. And in reinforcement learning, we mostly deal with discrete time. And if we want more granularity, we just decrease the meaning of this time step. However, other fields, also it is also reinforcement learning, but I will not really cover it in this course. Some people try to also model time as continuous time in like kind of continuous control settings. But in this course, we will not care about this, because we will anyway be able to solve continuous states, continuous action problems while using discretized time. Like moving into continuous time will involve like integrations instead of summations and so on. And also it is also in a way the case for like continuous states and actions, like moving from discrete to continuous almost always results in moving from some summations that are easy to implement on a computer into you know, integrations and so on. And it's a little bit more complex, but I don't think in this course, at least, I don't think we will lose much by not considering continuous time steps at all, because you could always, you know, reduce the granularity of time. I just wanted to mention it so that you know that this also could be different in other problems. Okay, this was a short lecture. See you in the next one. Okay, let's dive a little bit deeper. Like, consider this state diagram right here that we will call later like a Markov decision process. For now, it's just a state diagram, and we have like 1, 2, 3, 4, 5 different states, right? So this is a state diagram of a person who works as a marketing employee at some corporate. Okay, so the person always starts with a breakfast, right? And then after having breakfast, the person could actually choose one of two like paths. Like he always has breakfast at a cafe outside home. Then he might just decide to go home, you know, take the day off, in which case he gets a small reward because he's not gonna work today, so he's happy. And then he arrives home and the episode terminates. Like when I say episode, I mean, you know, one instance of following this diagram until termination. Like you see here at home, there are no arrows flowing outside of at home, so we call this a terminal state. We could also do something like this, like, you know, put a terminal state here if we want. Means it's fine either way, but let's just not do that. So that could be one action the employee takes after having breakfast, but also he could just decide to go to work. When he goes to work, he gets a negative reward because he's a little bit annoyed. He doesn't like going to work, right? But then he has to, so he switches or moves to another state, which is at work. Now, while he is at work, he has to make those annoying cold calls that I hate so much. Like he just calls some random numbers and offers the company's product. Now, sometimes he makes a sale. And when he makes a sale, he earns a commission, and so he gets a large reward here. But other times, probably most of the times, he actually just gets an angry response from someone he just talked to while he wasn't really ready to receive a marketing call. He was waiting for a very important call. So he gets an angry response from this person, and this is the state he moves into. And obviously he gets a negative reward because someone yelled at him. Okay. Now, when he gets into this state, he either returns back to, like, you know, his normal work flow, and then he prepares to do another cold call, right? Or he could just, you know, go home, in which case he gets a reward of 1 again because he's now away from work. In the other case, when he makes a sale, he always goes home. Now I'm done for the day, I will go home for the day. And then at some point, if the person's at work, I mean, he tried this cycle, this loop multiple times, and then he just, you know, like, he just goes home anyway at the end of the workday, right? So this is just a small and completely arbitrary state diagram or Markov decision process that we will use to, you know, explain some extra concepts. Okay, so the diagram as it is now, we know the state transitions, right? We know the state transitions. Like, we know that when I take some action, I know where I will end up in. So most of those state transitions are actually deterministic, except for this one. Like, when I make a cold call, I don't know where will the environment throw me. It will either throw me to a sale, right, or an angry response. So this one we call the state transition is actually probabilistic, but for the other ones, I know that if I take this action, go to work, I know that I will end up at work. In this simplified machine, obviously I might, you know, have an accident and then go to hospital. I mean, this is possible, but we ignore this complexity here in this diagram. For this diagram, I know that if I take the action, go to work, I will arrive at work. In which case we say that the transition probability, the probability of st plus 1 being equal to at work, given that st is equal to breakfast and at, the action at time t, being go to work, is exactly equal to 1. This is what I mean by knowing that transition probability, and the transition probability is deterministic. Now, this doesn't mean that I will always go to work, right? Because there's another quantity, which is the policy, right? Like, the policy pi of go to work, this is the action, given the state is breakfast, right? This could be something, maybe most of the time, like maybe 90% of the times, like every 10 days I take 1 day off and then I take 9 days at work, for example. So this is the policy. This is stochastic, but it is not a property of the environment. It is my decision. I decide this. But the transition probability is a function of the environment. Also, this one here, like, you could also like, if I write something like probability of sale given the previous state was at work and the action is cold call, maybe this is very little, like maybe this is 0.01, like out of 100 calls I make 1 sale, maybe. But this one is still a transition probability, and it is a property of the environment. I can't control it that much. I just receive some numbers from, like, my manager, and I just call them in sequence, and then maybe some person just decides to buy and someone doesn't, right? Like, it's a property of the environment in this example, at least. Okay, we also know the rewards, and we here assume that the reward at every state, action, next state, like group or tuple, is deterministic, right? Like, for example, the reward, reward of being at work, like, that's st. So the reward of st equals being at work, right? And at equals cold call, the action, and st plus 1 equals like sale, this reward is always 1000. So here we assume that the reward is deterministic. Now, in some cases, as I said before, the reward itself also could be modeled as a probability distribution, but I mean, for this example, we assume it is just deterministic. And to be honest, for most like reinforcement learning formulations, we try, even if it is like stochastic, we will still try to take the expectation or the average of this reward in order to make it just a number, to simplify things. And really, because what you care about in reinforcement learning is to maximize the expected future rewards, or like the expected rewards, or the expected what we call return. We will talk about this later. So anyway, you don't care if like, one of the rewards is extremely high, but the probability of it happening is very small. You need to talk about maximizing the expected return or the average return in a way. So anyway, if this reward was like stochastic, we could still take its expectation and convert it to like something deterministic. Now, if we know all those rewards at every state, action, next state group, and also we know all the transition probabilities, we say that we have a model of the environment. So the model of the environment includes both transition probabilities and reward probabilities at every single transition and state and so on in the Markov decision process or in the state diagram we have. If we have a model of the environment, someone tells us those probabilities, then the reinforcement learning problem becomes a little bit easier. And again, the reinforcement learning problem is find the policy that maximizes the return, right? The long-term return, in a way. Now, not all reinforcement learning problems have it this easy. Like sometimes we don't know the model of the environment. We don't know the transition probabilities. We don't know the rewards. Like no one tells us this. And in this case, we need to kind of interact with the environment directly to gather this information. Like in some cases, we know those perfectly. Like again, the example of chess. Like the example of chess, you know the environment 100%. Like you know that if I take a piece and move it from this square to that square, I know that it will move to that square. Okay? So this is the transition probability. It is deterministic and known. Also, for the rewards, we could model it as, the reward for every move is just 0, except if I win the game, then it's 1, or lose the game, then it is -1. So again, I know the reward model of the game. This doesn't mean that it is trivial to solve it using reinforcement learning, but it is definitely simpler than having the same complex problem and not knowing the transition probabilities and rewards, okay? But in other cases, we don't know the transition probabilities or the rewards, in which case we have two ways to solve this problem. The first one is try to construct a model of the environment, from observations. So somehow try to, do this a couple of times. Try, for example, to know, okay, so try out 1,000 cold calls and then record, in those 1,000 cold calls, like 900 calls resulted in an angry response and only 100 resulted in a sale. And so in a way you realize that the probability of sale given cold call and being at work is maybe 10%, something like that. So you try moving or interacting with the environment multiple times to collect information from all the states and try to find out how the environment operates, and also record that whenever I make a sale, my manager just hands me $1,000, and that's deterministic. No matter the nature of the sale, no matter how big it is, how small it is, I always get $1,000. So I kind of understand that the reward here is 1,000. So I know this from experience. So we could actually do this, construct a model from the observations, and then use some, math that we will cover later, just to get the optimal policy, like using just pure math, not necessarily data-driven math. If you already know the model, you don't necessarily need to use machine learning to solve it, or like data-driven approach if somebody gives you the model. Now, if you don't have a model, then you will need to use data to construct a model, which is the first approach, or there is another approach that tries to get to the optimal policy directly without trying to construct a model from observations at all. Like, those are called model-free reinforcement learning techniques. And to be honest, like, we will spend most of the course on model-free reinforcement learning. I mean, we will spend some time also on what we call model-based, so maybe model-based reinforcement learning. We will spend some time on model-based reinforcement learning, but then we will spend most of our time on what we call model-free reinforcement learning, because in a lot of real-world examples, it's not easy to get that model of the environment. Nobody gives it to you in a lot of cases, not all of cases, but in a lot of cases, like a robot interacting with the environment, a robot learning to walk, a car like learning to drive, and so on. Like, not always it is easy to really find out the entire environment dynamics beforehand, okay? Also, like, if you are like playing an Atari game, or you are teaching a reinforcement learning software to play an Atari game like Super Mario, or like, Chicken Invaders or something, you want to throw it into the wild, just give it the video feed similar to what you as a human player would do. So you give it a video feed and just, ask it win, try to win. You don't give it anything. You don't give it the rules of the game. You don't give it what is winning, what is losing, what does, taking coins result in. Nothing. You just give it a video of the game, the video feed, and ask the reinforcement learning agent, please learn to win. And surprisingly, it does. And it does that using what we call model-free reinforcement learning algorithms that we will cover in this course. So I think that's enough for this lecture. Like, see you in the next lecture. Okay, so let's do some extra formalization. In this lecture, I'd like to talk about something called the Markov property. So for a reinforcement learning problem, or like for a system or an environment, we say that our formalization or formulation of the problem is Markovian if our choice of states guarantees that the future is independent from the past given the present, which in like easier terms means that you don't need to know the full history of state transitions and actions and rewards in order to like realize what will happen next, or what is the optimal policy from now on. Like, let's give a concrete example, and again we will use the boring example of chess. Like, if you are playing chess and you are in some intermediate state, like some board configuration, and you want to win from now onwards, it doesn't really matter how you reached that specific state, right? Like the fact that 10 steps ago something happens that led you to do something, it really doesn't matter. Like, all the paths that lead to the same exact like current state of the board configuration doesn't matter at all. You want to win from now onwards, and so we could say that the future, the steps you need to take in order to win in the future, is independent from the past given the present, right? All what matters is the current state. You don't need to look at the previous states in order to decide what to do next. So the chess game is definitely, it follows the Markovian property or the Markov definition. Now, this is not always the case in a lot of cases, it depends on your choice of state representation. So let's say that you have a self-driving car, right? And for some reason, you choose your state to be the position of the car. And you want to predict, where the car is gonna be at time t plus 1. So just knowing the position of the car at time t doesn't tell you anything about the position of the car at time t plus 1, because you don't know the velocity, you don't know the acceleration, you don't know if you are like parked or like moving forward or backward, and so on. So in this case, the current state alone, which is the current position, is not really does not really say anything about the future. And so this state representation is not Markovian. Okay? Now, if you happen to augment your state vector representation or like feature vector representation to include the position of the car, the speed of the car, the acceleration of the car, and maybe some camera feed like showing the what else exists in the street and so on, then this state representation is rich enough to let you know where the car will be in the next step, because you know the speed, the position, the velocity, the acceleration, and maybe the orientation of the car and so on, like other things. So here you would have a richer representation of the state that, so now your system is a little bit more Markovian. There is another like subtle but related concept to this non-Markovian representation. So we say a representation is non-Markovian if the state representation itself is like missing, it's not rich enough. But there is another concept that we talked about, which is the partial observability. It is similar, but it's not exactly the same. Like in partial observability, like the state representation that is Markovian, but you just can't observe it. Like again, if you are playing like card games, you know that the full state includes the cards in everyone's hands. You just can't observe everything. So this is a little bit different, but it is a little bit similar as well. But it is something different, right? Like if we have a non-Markovian representation, then our state representation itself, even if we observe it fully, is not rich enough to have this Markov property that the future is independent of the past given the present. In the other case, the state representation is rich enough, but we just we can't observe it. Okay, so again, for the vast majority of this course, we will assume that we have a Markovian representation of the environment, like the state is rich enough. And then if the state is not rich enough, you'll try to convert it somehow to be a Markovian like state representation as well. So this course, we will assume you are Markovian and solve for that. And that's why we talk about or use what we call Markov decision processes. Let's formalize this a little bit more in the next lecture. Okay, so let's formalize this Markov property assumption a little bit more. Let's define something that we call the history until time t or at time t. So this includes everything that happened from the beginning of time until time t. So you start off your robot or your agent, and then the agent starts, observing something. So it makes an observation at time 0, right? Based on that observation, it does an action, chooses an action to do according to some policy, right? But then the environment responds with giving an immediate reward at time 1, and then the robot could do another observation after that because the state of the environment changed, and so the agent could observe something new at time 1. Now here we use this convention that when you take an action at time t, you receive the reward at time t plus 1, not at time t. This is completely arbitrary, like you could define it in a different way, but in this course we will just use this convention that we will define that the reward you get from the environment at the next time step. It doesn't really matter that much, it's just a convention. But then after you observe another observation at time 1, you take another action at time 1. And then again, the environment responds to you with some other reward at time 2. You make another observation because the underlying state of the environment changes, and based on that you take, you know, another action at time 2, and so on, right? So this is the full history. Now, if we want to define a state representation that captures everything, I mean, the easiest thing for us to define is to choose a state representation which is exactly equal to the history. I mean, you have all the observations, all the actions, all the rewards. So in a way, you have the entire state of the system, right? Now, this is not a very useful choice, but it is a valid choice that satisfies the Markov property, that if you know the state, you don't need to know anything else. But now the state is really everything, so obviously if you know everything, you don't need to know anything else. So that's why this is a valid definition, like a valid Markovian state definition, but it is not very useful. Like in chess, again, if you record all the actions and all the board configurations and everything that happened, I mean, this definitely captures everything, but it is not necessary to have all of that, right? Just knowing the board configuration is enough, and so this is maybe too much for the game of chess. So this representation here is not very useful, not only because it's complex and it's like grows linearly with time, which is something you don't want necessarily, but also because the state never repeats itself again. Like every state is completely unique. You can't reach the same state or something, right? And in machine learning in general, we would like to reuse like the knowledge that we learned before to inform our future in a way. Like you want to know that if state A is a little bit similar to state B, then maybe the action I should take here is similar to that. But if every state is completely, you know, different, you never see a state more than once, and every state is completely different, then maybe you don't have this generalization ability somehow, okay? But anyway, we need to find a state representation. Instead of having the full history, every state representation that is valid will anyway be a function of this history, but we want it to be a compact function that we can use and work with, and that's not super complex, but still satisfies the Markov property. So more formally, we could say that we need a state representation such that the probability of getting a specific, next state and maybe a specific next reward, given the state at time t, the state representation that we choose at time t, and the action we take at time t, we want this to be exactly the same as the probability of, again, st plus 1 going into state st plus 1 and getting a reward rt plus 1, given the full history at time t, or you could also say the full history at time t and the action you take at time t, depending on if you define the history to include at or not include at. Like sometimes do this, some people do this, sometimes people don't do it. So, but you get the idea. You want this representation to be a really good representation of the entire history. Like it is a function of the entire history. You want it to be good representation such that those probabilities actually like match. If this is satisfied, we say that given this state definition, the future is independent of the past given the present, and we say that this process is now Markovian with a Markovian representation. Okay, and that's what we will work with. So in the next lecture, let's actually start defining some terms related to Markovian processes. We start with something called the Markovian process, okay, or Markov process, and then a Markov reward process, then a Markov decision process, and then finally a partially observable Markov decision process. Okay, so we already know one example of, what a Markov decision process looks like, and it's really this example we covered a couple of lectures back. So a Markov decision process really is characterized by having multiple states, and then you have an agent or someone who can take actions, and then each transition in a way has some sort of reward. So a Markov decision process has an environment, has states, has actions, and has rewards, and this is the main thing we will work with in our reinforcement learning course, right? Because we are trying to optimize the actions or optimize the policy. Now, if you take the actions away from this MDB, you get what we call an MRP, a Markov reward process. So a Markov reward process, you only have states and you have rewards, you don't have actions. So there is no autonomy, there is no agent involved. Still, it is something that is very beneficial to model. So let's give an example. Let's say you are a pirate and your ship sinks in the sea in a way, and then the sea carries you over to some island. So this island could still have positive reward or negative reward. Like you could still find treasure on this island, or maybe you find some very fierce animals. So there are still rewards involved, but this poor pirate can't take any actions at all. Like, no, he just, the environment just throws him however it likes, and it has zero control. So this would be a Markov reward process, and you might be wondering, okay, why does this matter at all in a reinforcement learning course? I mean, you could think of it as a mathematical convenience, because we will show later, like very soon, we will show that any Markov decision process under a known policy, like if you make the policy fixed, okay, can be converted, any MDB can be converted to an MRP, a Markov reward process, under a fixed policy, okay? And the Markov reward process has a nice property, which is you can actually solve it. You can find out the total expected reward if you follow this policy. Like suppose you have 10 different policies that you would like to evaluate in order to choose the best policy out of those 10 policies. So you can apply this transformation from a Markov decision process into a Markov reward process under each one of those 10 policies. Then you can solve each one of those MRPs and find the total expected reward if you follow the corresponding policy, and then you could just choose the policy with the highest overall expected reward until the end of time. Okay, so I mean, generally we will not do this, but like in real world solutions, but it is interesting to know that this transformation exists and that you can solve MRPs using very easy linear algebra solution that we will find out. Now, if you also remove the reward, you get what you call a Markov process. So a Markov process is just the environment, some states, some transition probabilities, and that's it. Like you don't have rewards and you don't have actions. And again, you might be wondering why this might be relevant for anyone, not only in reinforcement learning, but it is still useful in some cases. Like suppose you just try to model something now. Like suppose you own a mall, a shopping mall, and you just want to understand how people move through the mall. Like you want to understand that people spend some time in the supermarket, and then there is a probability after spending some time in the supermarket that the people will just go to a restaurant and then maybe go to a toy store for their kid and so on. So you want to understand this because you want to know, let's say, where to position every store, or maybe you want to model the crowd probability distribution over time and so on. So there is no real reward involved, and there's no actions really. You just use this state diagram formulation and transition probabilities and so on to really model some environment. So this is called a Markov process. We will not use it super much in this course, similar to MDBs or MRPs, but it's still something you should know about. And then lastly, I'd like to talk about this partially observable MDP, which is really something you already know about by now. Like if the state representation is not, fully observable, like you are playing those card games, or the robot doesn't only has a camera in the front, it doesn't know what's happening on its back or something, then you have what you call a partially observable MDP. So the state representation is good, but you can't observe anything. Everything, sorry, you can't observe all the things that you need to observe, but you still can try to solve those kinds of problems using the same techniques we use for MDPs in reinforcement learning. But you might need to be a little bit smart about trying to estimate those quantities you don't know. So sometimes you estimate it using some other features, or maybe you just have a time estimator, like a recurrent neural network or something, that tries to use everything it saw and compact it into some representation that also captures the past, right? Like if the robot is moving forward, then yes, it doesn't have a camera in the back, but maybe it's moving forward, right? So some of the environment it saw at time step t could be useful at time step t plus 10, for example, even if it can't observe it at time step t plus 10. So that's why sometimes people use recurrent neural networks to try to convert a partially observable situation into a fully observable situation somehow, okay? So this is the general idea, but in this course we will be mainly focusing on MDPs. So let's continue in the next lecture. So in this lecture, I'd like to cover some notational conventions we will be using throughout the course, and we'll try to follow as much as possible. So for example, when we use a capital letter, something like this, we generally mean a random variable, while when we use a small letter like this, we generally mean a specific action. Like AT is a random variable. It could take multiple values, like left, right, forward, backward, something, and it really represents a random variable that could have some distribution, for example, depending on the policy or something. But now A is a specific instance or is a scalar. Similarly, when we use something like for the reward, something like RT plus 1, capital letter, or RT, right, we mean again the random variable that could have some distribution, depending on the state, the action, the next state, and so on. So it is a random variable that could have some distribution, while when we use a small letter r like this, we really mean some scalar value, okay? And so on for other like random variables. We'll have more random variables. Also the state, like when you use st, this is again the random variable that represents the states, and then this could be state 1, state 2, state A, state B, and so on. So capital letter is random variable, small letter is specific instance, okay? Roughly, I'll try to mostly use this convention, although sometimes I might make mistakes, and I hope that if I make mistakes, the context will make it clear that what I mean is the random variable or the scalar value. This notation is used by some books, although not all books use the same notation, so maybe you'll find some discrepancies here, but I'll just use this. Now let's actually define some more notations. So when I say something like R, reward, right, S prime, you should view this as some shorthand notation for this is small letter, right? So it is a scalar, and here we mean the expected value of the reward RT plus 1 of this random variable, right? Given that at time t we were at the specific small letter state S, and we took the specific action A, small letter A, from this random variable, right? And at state st plus 1, we got to a specific small letter state S prime. So this is a definition. So in general, the reward you get could be stochastic, even if you take the same action from the same state and reach the same next state, could be still a distribution. So here we talk about the expectation of this distribution, right? Like maybe, for example, at some instance you take, you get a reward of 100, but only like 10% of the time, and you get a reward of 1000 maybe 90% of the time. So the expected reward then, will be equal to 0.1 multiplied by 100 plus 0.9 multiplied by 1000, right? And this will be 910 plus 10, right? Plus 10, something like this. So this expectation converts kind of a probability distribution into a scalar number, which is the expectation. Right? I assume you are already quite aware about at least the simple probability concepts like expectations, like variances, and so on. If you're not, I think you should really refresh your memory about those concepts first and then come back. Okay? Okay. Now, in a lot of reinforcement learning sources as well, and like algorithms, you will find people simplify this to something even simpler, like the reward of S and A. Like they kind of ignore this S prime right here and just define the reward as a function of state T and AT. And then you should understand this as the expectation again of RT plus 1, given that ST is equal to S, specific instance, and AT is equal to A. So in a way, they kind of average out all the differences in the reward for different next states, right? Like in a way, you could actually define this as, you know, the summation over all possible next states. Then you get the probability of reaching a specific next state from a specific state and action, and then multiply this by R S A S prime. So this is the definition here. So this is another expectation. It is similar to the thing that I did here, right? I took a probability multiplied by a value and then plus probability multiplied by value and so on. So here, if you are at a specific state and you take a specific action, you might reach, you know, different next states depending on what the environment does, right? So for each one of those probabilities, you might have another reward or a different reward, which in this case is assumed to be an expectation. So it is this one. So it's still a number in this context, just an expectation, because you still could have another layer of stochasticity, right? But then if you average out all those or take this expectation, this is an expectation, you get a reward, bear, state, and action. So if we take the example that we had before, where you had, you know, you were at work, right? And then you took an action of call, right? Maybe you get a sale, and maybe you get an angry response, right? So in this case, the sale had a reward of maybe 1000, and the angry response had a reward of negative 10. So this one here is the reward of at work, action call, and next state angry response. And this is also a reward of S prime. But then you might define R of, at work, which is a specific instance, specific state, and cold start. You could try to average those two terms, but you don't just, add them and divide by 2. You need to find that transition probability, the probability of, sale given at work and cold, right? Like this is a property of the environment. This is the transition probability. So if this is, let's say, 0.1, like only 10%, you get a sale, while angry response, response given at work and cold call, this is maybe 90% of the time, then the expected value of the reward you will get, it will be equal to 0.1 multiplied by 1000, right? Plus 0.9 multiplied by -10. And this will be 100 minus 9, which is equal to 91. So then you could actually simplify this specific part of the graph or of the MDB and just, you know, say that the reward, you could put the reward here is equal to 91 and remove those two, and then you could in a way define this reward as being the reward of being at work and taking this action, and just use the expectation. So some people do this, and maybe depending on the problem, it might make sense or might not make sense. I personally prefer this one, but I understand why people use this one, because I mean, just for to avoid so much notation, and later on we will use those in more complex equations and so on. So people try to simplify things in order to have, you know, shorter equations. Even some people even actually try to define the reward as just a function of state. So they say the reward of being at this state is the expected value of RT plus 1 given I am at this state, given that ST is equal S. And in a way, they actually, this means they do another expectation. They remove the action, and they remove the action by having an expectation over all actions. So if you are at a specific state, you might take any action, right, with a specific probability multiplied by the reward of S and A. So this is another way you could simplify. You just get the average reward or the expected reward of being at a specific state. Of course, you need to have a specific policy to do this, but this is another expectation. Like this is another expectation, but now over actions. Okay. So notation wise, you will find people use those. I mean, in books or in papers and so on, people will use whatever is convenient for them. Okay. Okay. Now let's actually look at this. So let's define this more formally. So when I say bi of A given S, what I really mean is the probability of taking action A given I am at state S. Okay, so this is the formal definition of this one, or maybe a shorthand notation for this one. Okay. Now, similarly, you could also define something like this, like the probability of maybe S prime given S and A. So this is the transition probability. This could be thought of as a shorthand notation of maybe this one. The probability of ST plus 1 is equal to S prime. The probability of the environment throwing you at S prime, a specific S prime, small letter, given that you were at state S and took action A, right? So this also is a shorthand notation. Similarly, maybe you could define the probability of the environment giving you a specific immediate reward R if you are at state S and take action A. So this is shorthand notation for the probability of RT plus 1 equals R, right? Given that ST is equal to specific S and AT is equal to a specific A, right? And now you could call those the environment dynamics. So the environment dynamics is those two probabilities. In a way, this kind of assumes that the reward and the next state are independent, like the environment gives you a reward and also moves you to a next state, and there's an implicit assumption here that those are independent, which might be or not be the case for your specific problem. The general form of this would be something, a single equation that represents the joint distribution of S prime and R given S and A, And again, this is a shorthand notation for probability of st plus 1 being equal to s prime, rt plus 1 being equal to r, given that st is equal to s and at is equal to a. Okay, so if those are assumed for some reason to be independent from each other, or like for example, if you assume that the reward is not really a function of s prime, it's only a function of s and a, then you could then this joint probability could actually be decomposed into the multiplication of those two terms, right? Now, whether this is a good thing or a bad thing really depends on your specific problem. Again, I personally find it extremely more intuitive if we assume everything is like if you use this formulation and if you assume that they are kind of dependent. However, I truly understand why people try to simplify the notation, because later on we will go into bigger equations and people will try to simplify the notation. And anyway, moving from the simplified notation into the more generic one is really straightforward. You either put another expectation or remove an expectation, right? Like it's really simple. So we will most likely still use the simpler notation, maybe this one, and also use those simplified environment dynamics for the case of simplicity. But I mean, every idea you present, you could actually move it to another representation pretty easily. Okay, so I hope this was not super boring. Like, see you in the next lecture. So in this lecture, let's define the idea of an episode or a trajectory until the end. Like in reinforcement learning problems, in a lot of cases, we care about what we call episodic MDPs, like this one in front of us right here. Like every sequence of actions in this environment here will eventually end into this at-home state, and this at-home state doesn't have any transitions out of it, so we call this a terminal state, okay? So in a lot of reinforcement learning problems, you have this property, like you are playing a video game and then you will either win or lose. You are playing chess and you'll either, reach the end of the game and win or lose as well. Or maybe even, when you talk to ChatGPT or Gemini or any of those large language models, which are trained in part using reinforcement learning nowadays, the sequence that this model generates for you eventually ends. The code it generates eventually ends, and so on, right? So those are episodic MDPs, and those will be the main focus of us in this course. So let's define what an episode is. So an episode is a sequence of states, actions, rewards, states, actions, rewards, until you reach the terminal state, okay? So in this MDP, we could sample some trajectories or sample some episodes. So for example, maybe episode 1 could look like this. Like we always start at breakfast. So this is the first state. Then we could take an action like go home, right? So we follow this path and then we get a reward of 1. And then we are at state at home, which is a terminal state. So this is one episode. This is one possible episode. And we can have multiple episodes. Like episode 2 could be the same as this one if I have a large probability of just going home, right? If my policy pi lets me choose go home like with 99% probability, for example, then the second episode will also look the same. But then we could have a different episode, like we could follow another path, like go to work and then be at work. So we start at breakfast again. In this MDP, this is always our start state, but this doesn't always have to be the case. You could have different start states. So at breakfast, and then we choose the action of go to work. So go to work. And then we get a reward of -1, so this is the reward, and then we get to the state of at work, right? And then if I'm at work, I could take an action, maybe cold call. So that's the action, cold call. and then I might get a reward of 1000 and go to the state of sale, then take the action of, here you could take the action of go home and then at home. So go home, this is the action, and then I get a reward of 1, and then I am at home and the episode terminates. Okay, so those are different episodes. So in general, any episode will follow this formulation, like S0, the initial state, then you take action, and after you take action, you receive a reward R1, and then move to S1, right? So in our formulation here, we assume that the reward happens after state and action. So it's R of S and A, and that's why you get the reward before going into the next state. But really think of those as combined together, like for the general purpose or for the general case, just, those two are correlated. So, and then in state 1, you take action 1, and then you get another reward, R2, and you move to another state, S2, and so on until end of episode, until you terminate, like terminal state. Okay? So those are called episodic MDPs. They terminate naturally, but there are also some cases where you have non-episodic MDPs, or what you call continuous MDPs, like you are trying to control maybe a power station or something, and you never shut this power station down. You want it always to act optimally according to the resources and to the requirements of the grid and so on. So in this case, there are multiple ways to deal with those. One simple way is to just assume that every episode is exactly t time steps, a maximum of t time steps. So even if it is continuous, you could just say, you know what, I will cap every episode at 1000 time steps. Maybe a single day, or maybe a single week, or something, right? So this is one way to do that, and there are other ways as well. But in general, in this course, we will focus on episodic MDPs most, and a lot of those ideas, in fact, almost all of those ideas are transferable in a way to also the continuous tasks, but with some simple tweaks, okay? So I guess that's what I wanted to say in this lecture, this concept of an episode or of a trajectory, because we will use it throughout the entire course. So reinforcement learning is built upon a hypothesis that any goal you would like to achieve can be described as a maximization of rewards, or like a maximization of some sequence of rewards, or some addition of rewards. And those rewards can be like immediate rewards and delayed rewards. They can be positive rewards or negative rewards, but eventually any goal could be described by those rewards. So you really need to design those rewards in a way that allow you to get to your goal. So this is really the hypothesis of reinforcement learning, and this actually makes us need to have a definition of this cumulative reward, and we use the term return for that. So in reinforcement learning, you will often see the letter G, T, and this is called the, let's call it just the long-term cumulative return, which is just a fancy way of saying that GT is equal to the summation of all the rewards you get until the end of episode, or if you have a time t cap, then until this time t, right? So mathematically, the return is the reward you get at time t plus 1 plus the reward you get at time t plus 2 plus the reward you get at time t plus 3, and so on until the end of the episodes. And here we make a conscious decision to define GT to be equal to the reward you get at time t plus 1 and then moving forward, not RT. But this is just a choice, this is just a convention. It is really similar to the convention that we said before, that when you are at state S and you take action A, you receive the reward at the next step. So it is kind of a convention. You could define it otherwise, but in this course I will follow this this definition. This is just a convention. It doesn't really matter. Okay, now in reinforcement learning also, especially in episodic tasks, we prefer to use something called the discounted return, which is really a way for us to say that we care about immediate returns a little bit more, or like not immediate, but like closer returns a little bit more than, you know, returns or rewards that happen, you know, so far away in the future. We care about immediate rewards more than we care about, you know, those long-term rewards to an extent. It's a knob, it's a balance. Like think about it. Like maybe if I ask you to choose between getting $10,000 today or getting $100,000 like 40 years from now, the smart thing to do is definitely to take the $10,000 today, not to wait 40 years to get, you know, the $100,000. That's because those $10,000 actually have more value today, due to inflation, maybe due to the fact that you will just invest it, and if you invest $10,000 you will probably end up after 40 years with much more than those $100,000 and so on. So you prefer here, it's smart to prefer the immediate reward here. However, if the situation is a little bit different and I let you choose between getting $10,000 today and $100,000 like next year, then you should wait. Right? So there is a balance between choosing the immediate reward or the long-term reward. Also, you could look at it on the opposite way. Like sometimes you are okay actually sacrificing or getting a penalty right now in order to get later a bigger benefit or a bigger positive reward. Like suppose you are like you are racing in a car race, but then you move away from the track to put fuel into your car, right? And then you could win the race. If you didn't do that, I mean, putting this fuel really causes you a penalty. You lose some time and you get far behind your opponents and so on. But then after that you could win. If you didn't do that, you will not have this immediate negative penalty, but you will actually lose the game and will get a larger penalty later on. So again, that balance exists. The way we mathematically do that is by defining something called gamma, the discount factor, and this is between 0 and 1. Ideally, it shouldn't be exactly 0 or exactly 1, and hence you actually define the reward or the return, as being the immediate reward plus gamma multiplied by the next step, right? And then gamma squared multiplied by the following step, and then you could just move this a little bit, and then gamma cubed multiplied by the following step, and so on, right? So this is a number that is less than 1, which means that you multiply farther away rewards by smaller numbers, so their effect on the overall return gets smaller and smaller. A more compact form for this could be written as just summation. So GT is equal to a summation from k equals 0 until the end, and we could just write infinity here, and this is one of the nice things about having this, discount factor be less than 1, because even if you sum this until infinity, not until a max t, you still get a convergence series this will still be a number. It will not blow up to infinity, because gamma power infinity is going to be 0 anyway, because this is less than 1, right? So I mean, that's also a nice thing about having this discount factor, just mathematical convenience. But then we could define this as being gamma power k or t plus 1 plus k, right? So at the first one, at k equals 0, this is gamma power 0, which is 1, and then rt plus 1 plus 0, which is rt plus 1, and then if you move forward, and this is the definition of return. Let's just put it into a weird box right here. Okay, so this is the return. We will use it like a lot of times. Now I would like you to be aware that this here is a random variable, right? It actually depends on those R's. This is capital letter, those are all capital letters. So every one of those is a random variable, and this makes sense because you don't really know at every step which reward you will get. It will follow some distribution. So this one, RT plus 1, follows some distribution, right? This one follows some distribution. This distribution really depends on the state and the action and also the stochasticity of the reward itself and so on. So every one of those is a random variable. And this means that this one is the summation of random variables, which is also another random variable. And obviously, this random variable has larger variance, because you sum a lot of randomness and then you have more variance in that return. So this is a random variable. This is just not a number. And then for every different episode, you will have a different return, right? This makes a lot of sense. Okay, so let's also try to summarize some of the reasons why we might use gamma. So why gamma, right? So maybe one thing we said is we favor like sooner rewards, and then an example for that is financial example. Like I always want you to, you know, have a simple example in your head for every concept. So financial case, you know, but another thing is mathematical convenience, right? Because this makes this infinity summation converge, and this one we will use, you know, more often than you think. In a lot of the derivations and proofs and algorithms we'll cover in this course, we will depend on this mathematical convenience like a lot of times. Okay. Another interesting reason for using this gamma here is maybe you do not trust your model that much. Like maybe you used some data in order to estimate the reward model and the transition probability model and so on, but this is still estimated and you don't trust it that much, and maybe you just need to discount or like factor in this distrust, especially into later and later rewards or time steps, because you don't trust this reward model. You don't trust the probability distribution that you assigned to those like rewards, for example. And so maybe no trust, no full trust, or like reduced trust in estimated reward model. So this is also another like interesting reason for using the discount factor gamma. A fourth reason could exist in like continuous tasks. Like in continuous tasks, you don't have episodes, and so you sum up to infinity anyway. So maybe having a discount factor makes it simpler to model that continuous task. However, I mean, this is a little bit shady since this is really a continuous task. When you put gamma here, you say that after some time, I really don't care. But in reality, you do care, and so it is not as straightforward in continuous tasks. Some people use it in continuous tasks as well, but I mean, it's a little bit shady. In continuous tasks, you should really think of a different way, and there are different ways to tweak the reinforcement learning, like, you know, quantities in a way that works better with continuous tasks as well. I will write this here, but just take it continuous. Like in a way, in continuous tasks, using gamma is equivalent to putting a cap on the time step t, an artificial cap on the time step t, after which you don't care about, roughly. But so I will just put something like this, just with a caveat, I would say. Okay, so I think this roughly summarizes what I want to say. This one here is called the discounted return. So cumulative, it's called the cumulative discounted return, and we will use that throughout the course. Okay, see you. So in this lecture, I'd like to just give more notes on this idea of return, GT. So the first one, I mentioned in the previous lecture that gamma is chosen between 0 and 1. I just want to emphasize that if you choose gamma equal to 0, then you practically set all those long-term rewards to 0, like, and then you say that I really only care about the immediate reward. I don't care about the future rewards. right? If you set it to 1, then you say that I care about the future rewards equally to the way I care about the immediate rewards, right? Like I care about all rewards equally. Now, in reality, we don't like using gamma equals 1. Sometimes we do, but we don't like doing that in real world problems because it adds a lot of complications, and it's also, there are a lot of convergence proofs and algorithms that are only really provable to work if gamma is a little bit less than 1. So we generally use gamma a little bit less than 1, and then this is really a balance. If you use gamma equals to 0.9999, then you still care very much about future rewards. If you use gamma equals to 0.1, for example, then you care more about immediate rewards, right? So I think this was clear, but I wanted to say it emphasize it explicitly. So this is the first note. The second note is actually, I want you to look at this equation. So GT is equal to RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3, maybe plus gamma cubed RT plus 4, and so on, right? But if you look at it, you could say this is RT plus 1, and then you could take gamma as a common factor here and say this is RT plus 2 plus gamma RT plus 3 plus gamma squared RT plus 4, and so on. And if you look at this, this is actually very similar to this. This is G but at t plus 1. This is a return starting from the index more than this one. So in a way you could say that gt, the return at time t, is equal to rt plus 1 plus gamma gt plus 1. This is like a recursive relationship, and this is really interesting and we'll use it a lot. It really says that the return from time step t onwards is equal to the immediate reward plus the discounted return from time step t plus 1 onwards, which starts at rt plus 2, right? So this is the recursive formula for the return, and we will use this like more than you think probably in the course. Okay, so those are the notes I wanted to say in this lecture. See you in the next one. So in this lecture, I'm going to introduce one very important concept and very important quantity in reinforcement learning that is called the state value function. So let's start again from the return. So this return here is a random variable, right? It is the summation of other random variables, and every one of those rewards is only conditioned on a time step, right? So in a way, this random variable follows a distribution that doesn't care, or that is not conditioned on being at a specific state at every time step. So let's have an example. Suppose you are an Uber driver, right? And suppose that we have a reinforcement learning formulation where every time step is 1 hour. So something like G10, for example, is really the expected discounted reward from 10 a.m. every day until the end of day. Let's assume that every episode is 1 day. Okay, so 24 time steps. So G10 is the total amount of money discounted, if you have a discount factor, that you get from 10 a.m. until the end of day every day. It is not conditioned on your state. So it doesn't even like condition on you being working. Maybe you are at home and still you want to count the amount of money you get until the end of the day, right? Or maybe you are at a specific city that has a lot of tourists and then you get a lot of money, or another city that has no tourists at all and everyone has their own car, so nobody calls an Uber. So it really is a random variable that takes into consideration like that has all those factors affecting its randomness, right? It only cares about the time step. So G10 in this case will be like R11, right? Plus maybe gamma R12 plus gamma squared R13 and so on. So it is like a random variable that is not conditioned on a specific state. However, in reinforcement learning, you kind of care about, you want to put a label on every one of those states, like how good is a specific state on average or in expectation. This is a quantity that is actually quite useful because it helps you get the optimal policy. Like if you know that there are a couple of states you could choose from, and you have a value for each state that represents how much future rewards can you get from this specific state, then you could, in a way, design your policy, like choose to go to this state. Like if you know that if I work on Uber in a city that is very touristic, I will get, a lot of money. And then if I'm in another state or another city that is really not that touristic and everybody has their own car, I will get much less money. Then I can choose a policy to try to go or to reach a state or a city where I expect a lot of money, right? So that's roughly why we need something that that is conditioned on the state you are in. You have a lot of states, you need the best state. You need to reach a good state in a way. Like let's actually have another example. Like suppose you are playing XO, right? Suppose you are actually X. You are X and then there is another one who plays O, right? If I ask you, what is the value of maybe this state where the turn is now for X? Like, is this a good state to be at or no? If you think about it, you say, you know what? Now is my turn as X. So I am very close to winning, right? So this means that this state right here should intuitively have high value. So the value of this state is high because I'm very close to winning, or because the expected return from this state onwards is high because I'm expecting to win. Now, on the other hand, if I give you another, instance of XO, where you have something like this, right? And maybe it's O's turn now. So in this case, the value of this state is not very good, right? Because now it's O's turn and they could win by putting an O here or an O here. So I'm probably, as X, I'm probably gonna lose. So the value of this state is really negative since the expected return from now onwards is negative, right? So roughly that's what I mean by the value of a state. So more formally, we define the value of a state as being the expected return, the expected or the expectation of this random variable, gt, given that st is equal to s small, right? So in a way, I'm saying that if I'm at time t, I am at this step, at this state s, okay, at time t, then moving forward, so I'm now at specific state s, right? Now I'm conditioning, right? So I am at specific state s. In a way, the return here is, or this expected return is, you start some trajectory from s until end of episode and record some return, maybe g1, right? Or g, let's not g1. Or I just don't want to put g1 here in order to not confuse the time step, but this is one instance of the return. But now I have another g, right? Maybe I put it here, g1, g2, and then I fire another trajectory and get g3 and so on, right? And then have a million trajectories all starting from this same state s, and then I kind of average all of them out, and then this is the value of this state. Because sometimes, maybe I'm just very stupid. Like maybe this state should be a good state, but maybe I choose to do something completely stupid like this. In which case we say we follow a very bad policy, right? And then maybe the other player does this, and then I do something stupid again, so I do this. Then the other player wins. So it is possible that I am in a really good state, but I follow a very bad policy and then still end up on a very bad reward, right? So that's why the state value function is also conditioned on the policy. And here you also take the expectation following the policy you choose. So what I'm trying to say is the value of a state, you have to condition it on a policy as well, because it is the future discounted reward if you start at a state, but also following specific policy. You could try to reach, again, this, like, this specific case, and you start to follow a horrible policy and you lose, or you could start a very good policy and you win, right? So that's why the definition of state value function is always, you always have this, subscript here that says, under a specific policy, then you could have multiple policies. And the state value function depends on this policy, okay? So you have the expectation following this policy as well. So I hope this is clear. There's another concept that is also related. We will talk about a lot more, which is also called the action value function, which is really similar to this one, but you define it as Q by also, like it also follows a policy, but now it is a value of both a state and action. And we will see and we will find out really why we need a separate quantity for this. But this is very similar. It is the expected value of the return still. Like it's still the return, but given that at time step t, I am at state S, and I choose a specific action, action A, right? So this means that the value of this state and action pair is defined by, you start at specific state. Now, in general, at a specific state, you can choose multiple actions, right? Like right here, maybe here. At this state, you could choose this action or that action. If you care about the state value function, then you need also to factor in the probability of you taking this action multiplied by, whatever return or reward you will get here, plus the probability of taking this action as well. You need to factor out both. But if you talk about the action value function, then you say, I am at a specific state and I care about only one action. So I am at this state and I take this action. And then I need to know if I do that and then continue following the policy at all the remaining states in the future, a specific policy, what is the expected return? What is the average return? What is the expectation of the return I will get moving forward? So I understand that now it might sound a little bit, why are we doing this? Like, why are we not only using the state value function? And I promise you this will be extremely clear. There are very good reasons for this. And actually this is the main quantity that will allow us to really find an optimal policy when we move into bigger problems where we do not have a model of the environment. But I mean, I'll talk about this in great detail later, so don't worry about it. You could also think of those values in a different way. Like suppose you are at specific state S, then you fire or you try out millions of episodes starting from this state, but you follow a specific policy to choose the actions, and then you also have the environment dynamics like the rewards and the transition probabilities and so on. If you fire a million trajectories and then average all the rewards or the cumulative rewards you get, then you will get a good approximation of this state value function. So you could think of it as averaging a lot of samples, or you could just think of it as some probability, like if you know the policy, and if you also know the reward dynamics, and if you know the system, the transition probabilities, which means you know the model of the environment, then you could actually calculate this value analytically without using any data, without being data driven at all, because you have everything. You have the environment model, you have the reward model, you have the policy by, and then if you know that, you could analytically even, or using some iterative algorithms that we will cover in great detail, you could find the value of every state, right? Or of every state and value, state and action pair. However, this we will see that this is not really realistic in very big problems or like, real world problems, you generally don't have the model of the environment. And even if you had the model of the environment, we will find out that it will still be difficult for us to solve analytically. And so you will depend on some sort of data-driven approach using samples. So you still sample and then you do some stuff with machine learning to find the state value functions or the action like value functions. Now I'm using the word function here, like not in a perfect sense, like the state value function is a function of a state, right? So if I already have a state, we should say you find the state value, not the state value function, or you say that you find the state value function result or the output of the state value function at this specific state. But I will probably like just use those words interchangeably, and then I'll just you will see me saying stuff like probably the state value function of this state, but what I really mean is the state value of this state. But yeah, I think it will be clear from the context. So this is a very important concept, and then let's keep going in the next lecture. Okay, great. We have this definition. The value function of a specific state S is the expected value over a policy of the return given that at time t I was at this state S, right? Okay, now we are gonna do some derivation in order to map the value function of a state to the value function of the next states. Like from this state I could reach state A, B, C, D, and we want to make some mapping between the value function of this state to the value function of the following states using some sort of a recursive relationship, right? Like, why would we need to do that? I mean, this will be very helpful throughout the entire course. This is probably the most important equation in the entire course, which is called the Bellman equation or the Bellman expectation equation. But like intuitively, why we need this is let's think of an example. Like, let's say again in XO, you have that this state maybe is a good state for X, right? But now, since this is a good state for X, then any state that could lead to this state should also be a little bit good, should be considered a little bit good. Not as good, right? But a little bit good. Like, this is the intuition of it. Like, if you know that one state is a very good state, then maybe, let's say the value of this state is, let's say 10, like just some random number, okay? But then this means that the value of this state here should be maybe has a value of 5 or something good still, like maybe 9, right? So if you define these recursive relationships, then maybe in some cases at least, some states are winning states or very close to winning states, then any state that leads to those states should also get a piece of the reward, and also the states leading to those states should also be a little bit good, and so on. So if you have this recursive relationship defined, you could in a way propagate the rewards from the winning goal into the initial states. Roughly, I mean, this is really an intuitive explanation. It is not the case that in all reinforcement learning problems that there is one goal at the very end. This is not what I'm trying to say. It is still the case in a lot of cases, in a lot of tasks, but only think of this as like kind of an intuition to convince you why we even care about this. But in reality, the use of this will be clear more as we try to solve reinforcement learning problems in reality. So let's actually now dive into some math and let's try to look at this. Remember, we before defined GT recursively based on GT plus 1, right? Remember, like we said that GT is equal to the immediate return, so RT plus 1 plus gamma multiplied by GT plus 1. But now we are still conditioning on ST being equal to S, right? So this is the same equation because we have the recursive relationship for the return. Okay, nice. Now this is an expectation, so you could spread out an expectation if you want. So this is really equal to the expected value over pi of RT plus 1 given ST is equal to S, right? Plus gamma multiplied by the expectation of GT plus 1 given ST is equal to S, right? Okay, that's because the expectation is a linear operator and you could really distribute it over a summation. Now you might be tempted to replace this one and say, you know what, that's the return at t plus 1, so maybe this is the value function of the next state. But this is not really true, because here you are conditioned on st equals s, not st plus 1 equals s. So this is not the value function. This is not the value function of anything. It is just some expression that you will try to tweak into being value function. But let's do that step by step. Let's actually look at this one first. The expected value of the next step reward, or of RT plus 1, given your specific state, right? Now, I am at a specific state, right? Maybe S. I could take one action, maybe A1, A2, or something. And then the environment could actually throw me at maybe S, B, or SC, or here maybe it just, maybe the environment only could throw me at SD, right? So I am at state S, and then I'm talking about the expected value of RT plus 1. So here maybe I get one reward, maybe call it reward, 1 or something, reward 2, reward 3. So I need the expected value of those rewards, and as you can see from this diagram, the policy affects this one. Like if my policy is defined such that I always take A1 and never take A2, then this value will only be R1, right? Again, if my policy is defined to take A2 only, like with 100% probability, and never take A1, then this RT plus 1, the expected value of this, would be some expectation over those. But the expectation here, the probability of every one of those, really depends on the transition probability of the environment. The environment could throw me at this path or that path. I can't control it. So you could imagine that this value here, this expectation here, must depend on two things: on the policy, which is under my control, pi, and also on the transition probability of the environment, right? So in a way, we need to sum over all the possible actions. And for every action, we need to sum over all the possible ways the environment could throw me away, right? So in a way, you need to sum over maybe all the possible actions and then get by of A given S. So here I have chosen one action. Now for every one of those actions, I might be thrown by the environment into different paths. So I need to sum over all the next states that the environment could throw me at. So probability of the next state being S prime, right? So S prime is really part of all states, and maybe A is part of all actions if you want to be formal. So probability of S prime given that I was at state S and took action A, right? So the probability of the environment throwing me, let's say, at SC if I was at S and took action A2. And then for every one of those, I have a reward. So now this is the value that I'm averaging over. And this reward in this formulation is a function still of S and A and S prime, right? So now I'm using this formulation of reward that has everything, but you could also simplify and have R of S and A only, in which case we kind of assume that the reward is only a function of the state and action, which means we could really convert this entire thing into R of S and A. But let's do that later. We will do it, since that will be the formulation we use more often. But here I'm just trying to let you know that it's really not a big deal to use this one over the other one, or the other way around, okay? this whole thing is actually this first term. But then you still need to also add the second term, which is this one. So it's gamma multiplied by another expectation. And now let's think about this other expectation. Here I'm talking about, let's say roughly, not formally, the average value of this return, or the expected value of the return at t plus 1, right? If I start at state S. So I'm here at this state. Now I want the expected value of the return I get starting from the next states, not from this state. So this is not the value function of S, right? I am here, I am at this state S. I want to know how much value I will get, or how much rewards or discounted rewards I will get from the next time step onward, right? So in a way, you need to factor in this transition again, right? So in a way, this is the average return, and I'm using the word average here a little bit informally because it's an expectation, not an average, but let's just use average just for intuition. So I want, so maybe this, from this state, SD, I get on average a return of like 100, and then from SC, I get a return of negative 100, and then from SB, I get a return of 1000. Then I need to average those three, so 1000 plus 100, negative 100, so it's 1000 over 3, which is roughly 333. Roughly, again, not exactly. But now to make it exact, we need to work on expectation, not average. I'm just trying to tell you that you need to factor in all the possible next states first, and then average the value of those next states, right? So you need to get the probability of reaching a specific next state, right? Then multiply by the value of this next state, and then do this for all the possible next states, right? So it's, in a way, it should be an expectation over all the next states. So again, we start from this state here, and then we consider all the actions again. So all the actions that we could get, that we could take in this state, right? For each one of those actions, there is a probability we get thrown into each one of those like next states, right? So we have another probability here, the transition probability of the environment of reaching S prime given S and A. Then for every one of those, we will get like a return, a different return, and we need the expected value of that return. So it's really expected value of GT plus 1, given that I am now at state S prime now, right? Like I took an action, the environment threw me at specific S prime. Now I need the expected return I will get if I am at time t plus 1 am in state S prime, right? So in a way, this allows us to convert this one here into this one here. But now this one is really the value of state st plus 1. So now this is the formalization of what I tried to explain intuitively using the averages, right? So now let's actually simplify this a little bit more. This is v by of s prime, okay? So let's actually see. So now let's do it again. You could also see that this summation here, those two summations here are shared between the two terms. So I could actually put them outside. So it's a summation over a by of a given s multiplied by summation over s prime, the transition probability of reaching s prime if I am at state s and took action a, right? And then here you have r of s and a and s prime from the first equation, and then gamma multiplied by this expectation, which is really the value function of the state s prime, which is, you know, the next state, or at least one of the next states of that you could reach from state s. And this is really what we wanted to get, right? So you could actually take this and copy it and paste it and just write down this as an expectation. So I mean, as like a full equation. So the value of one state s is equal to this expression right here. Now this is a probability distribution, and this is a probability distribution whenever you multiply probability distribution by some quantity, this is really an expectation. So you could actually simplify this and say that V by over S is equal to some expectation over all the actions and next states of the immediate reward you get, right, plus gamma multiplied by V by of S prime, if you want. So I mean, this is also a good formulation, but I personally really prefer to write things down like in the less compact form. I think it's less confusing, but you could also think of it as this, because this is still like this. You could remove this term and have an expectation of this, and then this is another expectation because this is also a probability distribution, and you sum over all the next states, so this is another expectation. So I mean, this is you could think of this as a short form notation for this one if you want. Now, finally, I also would like to show how this notation will look like if we prefer to use the R of S and A formulation. So it's actually simple. You could say that V pi of S is equal to summation over all the actions by of A given S. So this doesn't change, but now the multiplication of this one and this one is actually R of S and A. This is the expected value of R and S and A. You just remove the S prime being explicit. So you could have the bracket here, and then you multiply those together and you get R of S and A. This is the expected value of the reward for this specific state and action. But then you need to distribute this one here again. So plus gamma multiplied by the summation over all the transition probabilities B of S prime given S and A multiplied by the value function of the next state. Okay, so this is also another formulation. You will find this may be used a little bit more, and this is called the Bellman expectation equation for state value functions. We will see later that we could also have a similar one for the action value functions, but let's focus for a while on state value functions, and then we'll just see what we can do for action value functions later. So now we only care about state value functions for a couple of lectures. Nice. Now suppose we have an MRB instead of an MDB, so there is no notation for actions. Then the Bellman expectation equation simplifies a little bit. So for an MRB, like let's say for an MRB, there is no policy and there's no actions. You could think of it as you have only one action, which you don't even choose, right? So it's something here, this will be one, so you'll not have this summation. So the V pi of S for an MRB, and I'm saying it because we will need it, is equal to, again, you only have a single action, so it's just the reward is only a function of state in this case. So it is just the reward of this state. It only depends on the state you start from, and then gamma, and also this transition probability is now independent of the action, so you still sum over the next states, but you have now transition probability like this multiplied by the value of the next state. So again, this is the Bellman expectation equation if you have an MRB. Okay, I think that's enough for this lecture. See you in the next one. So in the next lecture, we derived the Bellman expectation equation for an MDB and also for an MRB, but I made a small mistake because I wrote the MRB equation and I still had a policy pi, but this is not actually correct. An MRB doesn't have actions, so it doesn't have policy. So it's really, you should just remove the pi from the equations. Apologies for that. But now our goal is we want to find those state value functions. Again, because if we know the state value functions and the model, the environment dynamics, you can choose the optimal policy, and this is really the goal of reinforcement learning, to find the policy that maximizes the the return you get, right? So that's really the goal of reinforcement learning. You'd like to find the policy that maximizes the return from each state in a way, especially if we are talking about discrete states. Now we will find out very, very soon that this equation right here actually has a very straightforward closed form solution, just some linear algebra, which means that for any MRB, you can just find the state values of all the states in using some matrix algebra, some linear algebra. Now, in reality, if you have a tremendous amount of states like chess or Go, then you can't do this linear algebra in a closed form because the matrices are huge. But at least theoretically, for the small problems, you can do that. And this is a really good start. This is a really good introduction to estimating the state value functions. But that's only for an MRB. For an MDB, you don't have this easy solution. But we are in luck, since every MDB under a fixed policy could be converted into an MRB. And that's what I will cover in this lecture. But this is the whole point of this lecture. Like, every MDB can be converted to an MRB if we use a fixed policy. So this means really that if you have 100 different policies and you want to choose the best out of them, you could just convert the MDB to an MRB like 100 times, every time with a different policy, then use the closed form solution that we will derive later to solve for the value of every state, right? And then you could try to find the optimal policy, like out of those 100, for example, or you could mix them if you would like. If some policy is better at a specific region of the state space and another one is better at another region of the state space, you could mix them and so on. And this all assumes you have the transition dynamics and the reward model. So we are model based in a sense. So if you are model based and if you can find the state values of all the states, or if you could find the policy that maximizes the state values, then you could find the optimal policy, or this would be the optimal policy in a way. We will see later that if you don't know the model dynamics, then you will need to work with the action values instead, but that's for later. So in this lecture, let's just see how we can convert any MDB under a fixed policy into an MRB. So, I mean, let's start with some math and then let's move towards an example. So if you think about it, an MRB has this transition probability that does not depend on an action, right? So if you want this quantity and you have an MDB and a policy, you could easily see that the probability of the transition probability of getting into S prime from, or given that you are at state S, this is really the summation over all the actions of the probability of taking any action from state S multiplied by the transition probability of reaching S prime if you take action A at state S, right? This equation makes sense. It is still one other expectation equation. Since you sum over all the actions, you kind of remove this action here from the right hand side. So in a way, you have the transition probability that does not depend on an action. Similarly, for the reward, you could understand that the reward of R of S is again summation over all actions, the probability of taking specific action from a specific state multiplied by R of S and A. So now again you get the reward per state and you remove the action from the equation entirely. So those two equations are the way where you convert an environment with actions like an MDB into an MRB. Okay, so let's actually look at a concrete example. So let's look at this concrete example. It is still a state diagram, or an MDB in this case. You are at home, which is the first state, and then you can either go out or stay. So the probability 0.8 here is really pi. This is pi of go out given you are at home, and this is pi of stay given at home, but I'm just using b for compactness, right? Now, if you go out with a friend, and you have zero personality, so your friend really decides where you go. So your friend is part of the environment in this example. So this friend either takes you to the gym or takes you to eat in a fast food restaurant, and you will just depend on whatever they say to you. So they are the environment, and the probability of that friend pushing you to go to the gym, this is a transition probability, is 0.3. The probability of that friend pushing you to eat fast food is like 0.7. So in a way, this b here is different than this b here. This is pi. This is the probability of taking an action in state, but this is a transition probability. The probability of the environment throwing you at state gem or s prime, given you are at state home and take an action, go out, right? So it is a transition probability. If you go to gem, also you have a negative reward because that's a painful experience. At least in the short term, in the immediate term. While if you eat fast food, this is, a nice experience in the short term. You love the taste, but eventually you get to a worse reward later on because you become not healthy. While here you get in the long term, you get a better reward. Kind of. This is a very simplified thing. And if we want to convert this MDB into an MRB, we really need to remove all the actions. So the transition here doesn't have any actions. So this is already, MRB friendly. And this one from the fast food to the not healthy is also MRB friendly. So the only action you'd like to remove is this one. So we need to find out the probability of gem given home. And you could see from this graph, it is really the multiplication of this one and this one. So it's really 0.8 multiplied by 0.3, right? Under this specific policy. So we use this specific policy. And now the probability of, fast food given home, this is really 0.8 multiplied by 0.7, 0.8 multiplied by 0.7, and naturally the summation of those is 0.8, right? And then you have the probability of being home. You also need to get away this stay action. This is still an action, right? Given you are at home, this is equal to 0.2, and as you can see, the summation of those 3 is equal to 1. So now we can convert this MDB into an MRB since we have our transition probabilities. But before we do that, we need also to make sure that we have the proper, rewards on each arrow. So in an MRB, each arrow will be a transition from one state to another, and we need for each one of those arrows, we need a reward. So actually, if you look at this formulation right here for the Bellman expectation equation for the MRB, we assume that the reward is only a function of state. But to actually convert to an MRB, I think it makes more sense to define the reward as being a function of S and S prime, R of S and S prime, because we need something to put on the arrow between every two connected states, right? It is fine. It is similar to the case where for an MDB, we have either R of S and A and S prime, or just, have an expectation over all the next states and just assume that the reward is a function of S and A. So it is really the same. You will have a slightly different Bellman expectation equation. I think you can figure it out yourself. But actually, for converting an MDB to an MRB, I think it makes more sense to work with the notation that R is a function of S and S prime. So actually, something like this as well, this equation here as well, assumes that R is a function of state. But to draw an MRB, we need the more, rich formulation of reward. Now, for this specific example, it doesn't really matter. We can actually use those rewards directly without doing any averaging. But I want to tell you that if we have a more complex MDB where there are, multiple paths, that could reach to the same state, the same next state with different rewards, then you will need some sort of averaging for the rewards as well. And we will cover that, but let me actually finish this MRB first, and then I will tell you how we can work in a slightly different, a slightly more complex situation. So this one is simple. Every state transition to another state goes only through one path, so there is no need to do extra work on the rewards. So here you have a home state. Then there is probability 0.2 of staying at home state, and the reward here is just 0, but we remove the action. And then from home you could directly reach gem state, and the reward here is just -1, right? I went to the gem, I received -1, and no need to do averaging since there are no different actions that could lead to me going to the gem. It's only go out. Like, in a way, if this is not very convincing to you, like you have R of S and A and S prime in the MDB, and you want to convert it somehow to R of S and S prime, so you need to roughly sum over those actions, right? So if there's only one action, then those are really, the same. But we will talk about this in more detail just right after I finish the MRB, so stay with me. So the reward is -1, the probability is really 0.8 multiplied by 0.3, which is this one, right? So 0.8 multiplied by 0.3. But from home you could also reach another state, which is fast food. And the reward again is 1, since it's only one action. So if you sum up over all the actions, you are summing over one action anyway. So the probability is 0.8 multiplied by 0.7. And the reward is actually +1 for this case. And here you have reward is equal to 10 in order to go to, like, you go into a healthy state. Here you go to not healthy state, right? And the reward is equal to -10. The probability here anyway was 1, and it is still 1, right? In the MDB and in the MRB. So by this we converted this MDB into this MRB, and in the next lecture we will see how we can actually solve the MRB and find the value function, the state value function for all states using a closed form solution. So now we can find the value of all states in our MDB, and we can find, if you have multiple policies, you could, as I said before, find which policy is better, right? So I think this is a good ending to this lecture. However, I still need to talk about the more complex case because it is not exactly extremely straightforward. So let me actually take this one, copy it, and have another one right here, and let's actually remove those stuff here. Now suppose that there is another action you take that could lead to fast food. Let's say the action is order delivery, okay? But now since you order delivery, you pay more for the delivery guy, and so the reward you get is maybe a little bit less, so maybe it's 0.5 instead, and the probability of that, let's say, is equal to maybe 0.2, but this means that this one needs to go down to be 0.6, right? Because the probabilities here need to sum up to 1. Now if I ask you what is the reward of being at home and going into fast food, now this is actually more complex than before because you have two paths that lead to fast food, so you need to average those two paths. So let's see how we can do that like mathematically. So in the MDB we have R of S and A and S prime, and we want somehow to get to R of S and S prime. And the way we do that is through something called the law of total expectation, which is really just a fancy name to say that, you sum over all the actions and then have the probability of A given S and S prime and multiply it by R of S and A and S prime. So this is very similar to other marginalizations we did before. We are trying to marginalize the action, like remove the action from the function here, from the reward right here. So intuitively, what this equation is trying to say is, in our environment, there are multiple ways you could get from S to S prime, and those are different paths or different actions, and every one of those ways will give you a different reward. So if you want to know the average reward, you need to marginalize this action. So you need to get every reward and weigh it by some weight, and this weight is defined by this probability right here, which you think of as the probability. Like if you already move from S to S prime, maybe 90% of the times you go through action A and 10% of the times you go through action B for some reason. So the weight of those rewards needs to be weighted by those action probabilities. So it is a simple and intuitive equation, but it's formally known as the law of total expectation, which is a little bit different than what we call in probability the law of total probability. It is very similar but a little bit different, but it's really the same idea that we used before to marginalize other quantities. So now this is the equation, but this doesn't let us calculate R of S and S prime, since this quantity right here is actually interesting. We didn't deal with this one before. We already are aware of probability of A given S, which is the policy, but now this is probability of A given S and S prime. So now it's a little bit different. And to actually make something useful out of this, we need to use like Bayes' rule. So there is this famous rule in probability, I assume you know it, which is the probability of A given B is equal to probability of B given A multiplied by the probability of A divided by the probability of B. I think this is super famous rule in probability, so I assume you already know it. But now there is another version of it, which is conditional. So you just add conditioning on another quantity. So probability of A given B and C, I mean conditioned on multiple variables here, is equal to probability of B given A and C, right? Multiplied by probability of A given C divided by probability of B given C. So this is really the same, but since you added C in the condition here, you add it at every part of the equation. So this is still Bayes' rule, and using it we can simplify this equation into something we can compute. So let's say that A, for every A in this rule you put A, right? For every C you put S, and for every B you put S prime. So if you do that, then probability of A given S and S prime, right? This is equal to, you could use this, so probability of B, which is S prime, given A and S, right? Multiplied by probability of A given C, which is probability of A given S, right? Divided by probability of S prime given S. I also want you to note that, S and S prime here, you could just make them S prime and S, right? So, it's fine either way. So now you could see that if you go a little bit down here, that R of S and S prime is equal to summation over A, and then this term here, right? So probability of S prime given A and S. So we know this. This is the transition probability in the MDB. So this is a known quantity to us from the original MDB. And then you multiply it by B of A given S. This is the policy actually. So this is also known to us. We can choose it, right? And then we divide by the transition probability B of S prime given S. And all of this is multiplied by R of S and A and S prime, right? So all of those equations or all of those quantities are known to us. which means we could get R of S and S prime, which is all what we wanted to get at the first place, right? So all of this is me trying to tell you that for any MDB, even if it is a complex one with multiple paths and so on, you could still convert the MDB into an MRB and still have the proper, rewards and transition probabilities. This one also, if you like, we also know this one, right? This is the ones that we computed here, like this one, probability of S prime given S. So we have all the terms in this equation. Now, I will not try to compute R of S and S prime in this diagram. I think it's straightforward to do this. But I also want to say here before I end the lecture that if you didn't get like this thing about Bayes rule very well, I would say it's fine, because this is probably the last time we will use Bayes rule in this course. I mean, in general, when we solve real world problems using reinforcement learning, we will not be converting MDBs to MRBs at all, because in real world problems, the number of states will be huge, or you might even have continuous states, not discrete states, and then we will use different methods to solve. We will not convert to MRBs first, and also, and more importantly, even if we could do that, the closed form solution of finding the value functions using the MRB involves like heavy matrix inversion, and if you have tremendous amount of states, you will not even be able to get the value function using this matrix inversion like anyway. So in reality, we will not use this. So if you didn't fully get this part, it's fine. All what I want you to care about is to understand that for every MDB, you can convert it to an MRB and then solve it if the state space dimension is, small enough for this to be mathematically feasible. So in the next lecture, I will cover the closed form solution to the MRB. So let's finally find a solution to this value function. Try to estimate the value function for an MRB. Like, remember the Bellman expectation equation we found out was like the value function of a specific state S in an MRB, we don't have a policy, right, is equal to the reward or the expected reward from this state R of S, right? Then the discounted expectation of the next value function, or the value function of the next state or the next time step. So you sum over all possible next states and then get the probability of reaching S prime from S and multiply this by the value function of S prime. So this is the Bellman expectation equation, and we want to find values for V for all states that satisfy this equation. I want you to think of this Bellman equation as, as a definition. Like, if you find any numbers, even if you find those via trial and error, that satisfy this equation for all states, then you have found the correct value functions. This is a definition, okay? Now, in general, in discrete reinforcement learning, we kind of assume that all states are always, connected to all other states. And if one of those states is not really connected, then its probability here will be just 0. Similarly, when we consider actions in MDBs, we assume that all the actions are doable from all states, right? But if one of the actions is not really doable, then its probability of taking the action in one state is set to 0. So I mean, we just, for mathematical convenience, assume that for every state, when we sum here over all the next states, we need to sum on all the states. So that's why we put S prime belongs to the entire state space. So that's just a convenience. Let's actually try to understand how we can solve this. So let's have an example. Suppose we have only 3 states, right? So maybe state A, state B, and state C in some sort of MRB. And then every state is connected to itself and to all the others. So this as well is connected to itself, and this, and this, and this is connected to itself, and this, and this, right? So let's try to actually write this equation in complete form, like expand it, assuming we have exactly 3 states. So this equation should be satisfied for every one of those states. So let's actually write it for every one of those states. V of SA is equal to R of SA plus gamma multiplied by, here you need to sum over all the next states, which are all states, right? So probability of SA given SA multiplied by V of SA, right? Plus probability of SB given SA multiplied by V of SB now, plus probability of SC given SA multiplied by V of SC, right? So this is the term for the first state, but then we need to repeat that for the other 2 as well. So value of SB under the Bellman expectation equation is the reward, the immediate reward of SB plus the discounted here. And then from SB, we also move into all the other states by a specific probability. So we just change the second one here. And then we have value of SA plus probability of SB from SB, value of SB, right? And then probability of SC given SB, value of SC. And finally, for SC, we have R of SC plus gamma probability of SA given SC multiplied by the value of SA plus probability of SC given SB. SB given SC, right? Multiplied by the value of SB plus the probability of SC given SC multiplied by the value of SC. Okay, so now I've wrote the equation 3 times, once for every state. But the nice thing about this form is actually we can convert it into a matrix form. So if you think about it, if you define this as a vector, you could have a vector, let's call it V, that has V of SA, V of SB, and V of SC. You could also define a reward vector, which has R of SA, R of SB, and R of SC, plus gamma, which is a scalar. And this right here is simply just a matrix vector multiplication, right? Like you could do something like this. Like here, you put V of SA again, V of SB, this one, and V of SC. And here you write only the transition probabilities. So you have something like this, right? SA given SA, SB given SA, SC given SA. And here you have probability of SA given SB, SB given SB, and SC given SB. And finally, here you have probability of SA given SC, probability of SB given SC, probability of SC given SC. Right? So I think that's correct. And the nice thing about it is now you could just say that there is a vector V. This vector V shows up here and also here, right? So this is equal to a vector R plus gamma P, which is, the transition probability matrix from S to S prime, multiplied by V. Like in an MDP, the transition probability will be a different matrix per action. But here we are in an MRP. We assume we already converted the MDP into an MRP. So now this is just one matrix for the entire system. And this is actually, you can, try to solve for V, like V minus gamma PV equals R, which really means that I minus gamma P, this is identity matrix, multiplied by V from the right is equal to R, and we want to solve for V, so we multiply by the inverse of this matrix. So this is I minus gamma P minus 1 multiplied by R. So this is actually the solution that allows you to get the value V for all the states. Okay, so this is a closed form solution, and the nice thing about this is not the closed form solution itself. It's really the fact that you can find the value function for all the states. The fact that you can find it using a closed form solution is not very relevant for real world problems or for extremely large state space problems, because this inverse is O of n cubed, right? O of n cubed. And if you have 1 trillion states, this will be super large, and so generally we will not use this often. However, we will use some iterative algorithms later on, and we'll use some approximations later on, but at least now you know that there is a solution that exists. How to reach the solution is a different story, right? For small problems, we can definitely use this equation, and we will have a numerical example, concrete example, in the next lecture, just for the sake of establishing this fact. But now this is actually an interesting result. Also, for us to be able to use something like this, we need to know the reward model, right, and the transition model. So we need to know the environment dynamics. Now again, in a lot of real world problems, you don't have those. Those are a property of the environment, and you don't know them. So if you do not know the environment dynamics, you really can't use this equation or approximations or even iterative algorithms to solve the same equation without knowing the environment dynamics, in which case you need to depend on other methods like sampling and to be data driven in general. But for this lecture and for a lot of the following lectures, we will first assume that we already know the environment dynamics. Someone tells us the environment dynamics, or that we already have approximated it using data, and then using data we created a model of the environment dynamics, and then we just use it to solve. Okay. Okay, so in the next lecture, let's do a numerical example. So let's finally have a look at a concrete example. Suppose we have this world here where you have 6 states, A, B, C, D, and G, and L. G is the goal state. If you transition into G, you get a reward of +1. L is the losing state. If you transition into L, you get a reward of -1. Okay, so we define our reward model, R, the reward of being into B and choosing the action up is equal to 1. The reward of being in state C and moving down, this is equal to -1. Okay, now otherwise R equals 0, otherwise transitions don't do anything. Now this one has actions, so it is an MDP. We would like to find vPy. What is vPy? So in order for us to find vPy, we need to define a policy. So let's actually start with this policy. So let's say from A you go here, B you go here, C you go here, and D you go here. And in this one case, this is a deterministic policy. Okay, so there is no probability in the action distribution over states. Now in the terminal states, by definition, when you reach a terminal state, you are done, so there is no action to be defined in the terminal state. And also by definition, in the terminal state, if you would like to use the Bellman equation like this, there is no reward in the terminal state itself. You can do something more. So by definition, we define the value of any terminal state to always be 0, Because the value is what? The value is the future return starting at time rt plus 1, right? Remember the G return definition, it is the rt plus 1 plus a discounted return after that. But if you are in the terminal state, there is no rt plus 1. So the value of any terminal state, whether it's winning or losing, is 0. That's actually by definition, okay? So in a way, we don't need to define any policy here in G or in L. So the first step in order for us to get the value of this policy is to convert the MDP into an MRP, but this is actually simple enough that you don't need to do anything fancy to do this conversion, since the policy is deterministic. And also here, we assume that the transition probability is deterministic. You know, like if I am in D and try to move left, the environment will 100% let me land in C. If the transition probability was probabilistic, then maybe I try to move left, but the environment decides, you know what, no, you are not moving left, you are staying in D, you know, someone is pushing me back into D or something. But here we are assuming that the transition probabilities, like P, sometimes it's written like this, transition probability is deterministic. So really this could be thought of as an MRB already in a way, right? Where the reward of B is equal to 1 and the reward of C is equal to -1. Because if you want to find the average reward, you need to average over all the possible actions, right? But now the actions are really like only one action and it is deterministic. So in a way, this is already the MRB. So we need to solve this, right? You need to solve this. But we have now 6 states. We have 6 states, right? And to do this inversion like manually will be, you know, something not feasible. So let's just use Python. So here I replicated the problem into a Google Colab notebook. So let's walk through the code very quickly. So this dictionary just maps the states to indices, you know, A, B, C, D, G, L, they just have indices, that's just for convenience. But now you define the transition probability matrix, and it is a 6 by 6 matrix. It is good that you define it to be zeros, and then for the elements that you want to change, you change them, because in general, most of those values are zeros, right? Like the transition probability from D to B directly is 0, from D to A is 0, from D to G is 0, and so on. So most of them are zeros. But then here I set some of them to be ones, because under this policy, from A to B, the probability is 1, the transition probability is 1, because this is the deterministic action. And when we convert from an MDP to an MRB, we kind of consume the action. So this means that we always go from A to B, and we always go from B to G, and from C to L, and from D to C, right? So that's why those are exactly ones. So from A to B is 1, from B to G is 1, from C to L is 1, from D to C is 1, right? And then from G to G, I mean, we define it to be 1 because we assume that if you are in terminal state, you always, you know, remain in the terminal state forever, in a way, until you close the program, because the episode terminates. You know, it's just a convention. But this is another way to look at terminal states. They are states where you always keep looping and you receive no reward. This is also another way to model terminal states in code. And so the other terminal state also moves to itself with probability 1, and you never go out. Okay. Now the rewards, again, the rewards are like 0 for everyone, but B, the reward is 1, and for state C, the reward is -1, and that's because you only have one action, so you don't need to have an expectation over the actions because you already have one action. So the reward of state is already 1 for B and -1 for C, and that's what I put here. And for all the other ones, it's really 0, including the terminal states. Okay. Now here we assume that the gamma is 0.999. So this is just an assumption, the discount factor. You could assume the number you want. And here I define the inverse term. So you need to get I minus gamma p and then get its inverse and then multiply it by r. So this is just numpy. And if you do this, you actually find out that the numbers those are the value functions. So this is really the solution that you calculated in this line here, in this line v equals, you know, inverse term multiplied by r, and so the value function is like this, and this in a way makes sense, right? Since the discounting is very, very small, the value of d is roughly equal to the value of c, right? Multiplied by the discounting, because the reward is 0. So r is 0, and then you discount the value of c. So the value of c is now r is 0, and you discount the value is negative 1, and then the value of this is 0. So the value of c is definitely negative 1 under this policy, and the value of d is equal to gamma multiplied by negative 1, so it's very close to negative 1. Similarly, the value of a is almost 1, and the value of b is 1, right? Depending on the discount factor. So this is just a solution. I mean, now we have found the value function, right? We can try another policy and find the value function, and a third policy and find the value function, and then we could compare them and, you know, find a better policy across our policies. But there is something interesting, although it's not super important, but it's also interesting. Like, what happens if I come here and change the gamma value to exactly 1? If I do this, you will actually find a problem, right? Singular matrix. This is mainly because of the terminal states. Like, remember that we put the transition probabilities in the terminal states to be 1. So those are ones on the diagonal in the rows and columns that represent the terminal states. So when you subtract I minus this, you have 1 on the diagonal minus 1 on the diagonal, so you get rows of all zeros, and so this matrix is not invertible. So does this mean that we can never use gamma equals to 1 in this formulation? I mean, not really. We can still use gamma equals 1, although in reality we prefer to not use gamma equal to 1. So let's actually look how to solve it if gamma is equal to 1. So we will need to do some small change to this one. So let's just copy it and just put it right here. And in order to solve it, we need to separate the states right here into some terminal states and non-terminal states. Okay, so let's assume that in this example, let's assume that VA and B are non-terminal and VC is terminal, just for the sake of simplicity. And let's assume always that, you know, the terminal states come at the end. So in general, if this is, you know, n by n, let's just assume that the terminal states come at the end of the vector here. And we will use a trick called the block multiplication of matrices. So if you're not aware about this, I think you should check my linear algebra course. But it's really very simple. Like, I mean, if you are not sure why this works, you should check the other course because I prove it. But here, I'm just going to use it. So I can actually mix those two here, those two non-terminal states, into a vector that I call non-terminal. And in this specific example, it will be of dimension 2 by 1. So this is a vector. And then I'll put V terminal, which in this case, I mean, it's 1 by 1, but in general, it's a vector that is 1 by 1, right? I can similarly, so this is a block. This is a block like a 2 by 1 matrix in this case. And then for the rewards, I can do the same. So I need something of the same dimension. So the reward of non-terminal. And the interesting thing here is the reward for any terminal state is 0, right? So I here could put a 0, although it in general will be a 0 vector depending on the number of our terminal states. So it is a 0 vector. In this specific case, it is 1 by 1 because only VC is terminal in this 3 by 3 example. But in general, it could be, you know, multiple things. Then we use the same idea here, but we also let's also do here the same. So non-terminal, and then we have VT, and you know that the value of terminal states is also 0, right? But anyway, so this matrix, we can also partition it into blocks that are compatible with those blocks. So we can actually take all the non-terminal states into one block. Let's call it P non-terminal. And this is, in this example, it is a 2 by 2 matrix. Okay. Then here we can take those two and put them to be maybe P SC or something. Now, probability of A given C and probability of B given C, this is 0 since C is a terminal state. You can't move to anything other than C. So probability of C given C is equal to 1, right? Again, in general, this could be a vector, but in this example, it is 1. And here, this is a 0 vector, right? This is a 1 by 2, 0 vector. So if you look at it, this one here is 2 by 1, is 2 by 2, 2 by 2. This here is 2 by 1, 2 by 1, right? You can move into SC or into the terminal states from non-terminal states. So that's why this is not 0. But this one is 1, and here it is 1 by 1, and here this is 1 by 2, right? Okay. Now, the interesting thing about this is if you look at the last row and use this block multiplication of matrices trick, you see that Vt is equal to 0 plus gamma, and then here you have 0 multiplied by this one plus 1 multiplied by this one, and this is also like, it is 0, right? Like we know the value of a terminal state by definition is 0, so I mean we could just write 0 here and 0 here if you want. So the last row is satisfied and it poses no problems for us. But now we could expand the upper row. So the value vector of non-terminal states is equal to the reward of non-terminal states plus gamma, and then you just multiply this by this plus this by this. But this is already 0, so that's gamma, then P non-terminal multiplied by V non-terminal, right? And then this means that if you want to calculate V non-terminal, then V non-terminal minus gamma P non-terminal multiplied by V non-terminal equals R non-terminal. And again, you could like simplify this to be V to be I minus gamma P non-terminal multiplied by V non-terminal equals R non-terminal. So we got the exact same equation again, but without the terminal states completely, which means in order to solve this equation, if you have terminal states, you can just ignore the terminal states and have, this transition probability matrix, which in this case is not really a transition probability matrix, right? Like, I mean, it is just this block of it. So it is not a valid transition probability matrix because its rows don't sum up to 1 because we have effectively removed this part, right? So it is a block of the transition probability matrix. But however, you could just do that. And now this is the dimension of this is just the dimension of the terminal states. And if you do this, you will not have this problem where the terminal states have ones at the diagonal that get cancelled out by the ones on the diagonal of the identity matrix, leading to non-invertible matrix. Like instead, you will have just a solvable solution. So we can go back to our Python code. So here you can see that I converted the probability matrix to be 4 by 4 instead of 6 by 6, right? And then I removed any transition that goes into the terminal states. So I commented out the transition from B to G and from C to L and from G to G and from L to L, right? I kind of commented out those transitions that go into the terminal states. And that's because here in this matrix, we removed the probabilities that go into terminal states, right? So we actually don't use this. We only use this one, the probability of non-terminal states, or the transition probability of non-terminal states. So that's what I did here, and then I also defined the reward. Now it is a 4-dimensional vector instead of 6, right? So I mean the comment here is not updated, but yeah. And then if you use gamma equal to 1 and do the calculation, you'll get what you expect. The value function of A and B is exactly 1, C and D is exactly -1, which is anyway what we expected when we used gamma 0.999999. Now, what if we try another policy? What will it change if we try another policy? And let's assume the policy now is gonna be stochastic. So let's assume we have another policy, like let's take this with us and do something like this. And then maybe at state C, we have a policy where you could either go here or go here or go here with equal probabilities. Okay, so this is another policy that we could also try to evaluate. And the effect of this change in policy will reflect on the reward, the average reward R of S for this specific state, and also will reflect on the transition probabilities. So in this case, we actually need to be similar to the first example, not the last one. And the changes would be that the transition probabilities from C into B and D and L will be 1/3, right? So we can go again to this one. So from C, we are gonna go to L, 1/3 possibility. But then we also will go, let's actually, copy this 3 times. So from C, we can also go to D, and we can also go to B by 1/3 probability. And then the reward for this one, so you need to average out over the 3 rewards. So here you get the immediate reward if you go to B is 0, right? And here is also 0. Here is -1. So you have -1 plus 0 plus 0/3. So the reward for this state right now will be -1/3 instead of -1. So that's why here you need to put it -1/3. And now let's get gamma to be 0.9999 instead of 1, and let's solve it. The result will be equal to this. So does this make sense? Well, let's see. Like we have the value of A and B equal to 1. I mean, this didn't change, so it's fine. But the value of C and D are now 0, which is interesting. But let's see if they are correct or not. So to validate that they are correct, we need to see if they satisfy the Bellman equation. If they satisfy the Bellman equation, then that's fine. Okay. So let's look actually here at the value of C. So the value of C according to the Bellman equation is the immediate reward R of C, which you already calculated to be -1/3, right? And then you have gamma, which let's assume it's 1 for now. And then you need to, transition probability multiplied by the value of the next state. So we could go down with a transition probability of 1/3, but the value of this terminal state is 0 by definition. So you have a 0 here. And then you have another transition probability to the left, and the value of this one is equal to 1, right? So that's B, so the value of this is equal to 1. And then the value of D here from our calculation here is also equal to 0. So now you have 1/3 multiplied by 0. So if we believe this one, then the value of state C, let's put it here, is equal already to 0. So now this one is satisfied under those numbers. Now we need to do the same for the value of D. So let's actually do that, and let's remove this right here. So the value of state D is equal to what? The transition the reward is equal to 0, right? And the transition probability is 100% multiplied by the value of this one. And if we believe again what we got, then the value of this one is 0. So now this is also 0. So what I'm trying to say here is, as long as those calculations do not contradict each other, this is a valid solution. That's what I'm trying to say. It is not, I'm not doing anything shady by just assuming that the solution I got is correct. Because if I got solutions that are self-consistent with each other, then those are by definition valid solutions. That's what I'm trying to emphasize here. Self-consistency is key, right? So here I just assume that, you know, the value I got from the calculation here is correct for both C and D. I just plugged them into the Bellman equations and found out that they are self-consistent. And now if they are self-consistent, then they are by definition true. Okay, so I know this is a little bit subtle, but you need to understand it very well. Okay, so I think that's enough for this lecture. See you in the next one. So in previous lectures, we derived and introduced what we called the Bellman expectation equation for the state value function, V by. Bellman is the name of a man, by the way, like a scientist. In this lecture, I'd like to introduce some other variants of the Bellman expectation equation that also includes the action value functions, right? Remember we before introduced that concept like Q by of state and action pair, and the definition of this is the expected value of the return at time t or starting from time t if you were at time t at state s and you took an action a, right? So this is the definition, and then so you say I am at state s at time t, I take action a, and then I keep following policy pi until the end of episode, right? For the later, like, you know, steps or time steps, right? So this is the action value function. And similarly to the Bellman expectation equation for the state value function, you could do something similar for the action value function. And you could also get the state value function in terms of action value functions, and you can get the action value functions in terms of the state value functions, and also in terms of the action value functions in the next steps, right? Like this equation here is only one of 4 Bellman expectation equations that are all simple. They are all derived from each other, but I'd like to make that explicit. So this one maps the state at time step t to the states at time step t plus 1, right? This is what this does. So let's try to derive the other 3 Bellman expectation equations. First, what is the relationship between V pi of S and Q pi of S and A? If you think about it, the value function at state S is the expectation, you know, on average, what return will I get from this state S? So at this state S, I could take multiple actions, and every one of those actions has its own action value function, right? And this one is roughly the average over those, or the expectation over those, or like more formally, this is the definition of the action value function. Now V pi of S is defined as the expected value of the ground of the return given st is equal to S. So we can easily convert this to that by just marginalizing the action, like removing the action, and we always remove the action by, you know, doing an expectation over the actions, right? Because the value of a state is really the average, and I'm using average in quotes because it is an expectation, not an average, but roughly it is an average over all the values I could get from all the actions that I could do at state S. So formally, we could say that V pi of S is a summation over all actions, probability of A given S multiplied by Q of S and A following policy pi. So you could say that this is the second Bellman expectation equation, okay? So this is 1, and now this is 2. Okay, nice. By this equation, we have the state value function as a function of the action value function at the same time step, okay? So the next equation, we will try to get the Q value function in terms of the value function of the next state, in terms of something like this, like V pi of S prime. And to do that, we need to start with the definition of the action value function. Let's actually move those a little bit maybe down, or maybe you could just delete them, right? Now q by is again equal to the expected value over pi of gt given st is equal to s, and at is equal to a. So now let's use the recursive relationship for gt. So this is equal to expected value. Here you know that this is the immediate reward, so this is rt plus 1, right, plus gamma multiplied by gt plus 1 given st is equal to s and at is equal to a, and then you could separate them into two. So this is expected value over so rt plus 1 given st is equal to s and at is equal to a, right? And then gamma expected value following the policy of gt plus 1 given st is equal to s and at is equal to a, right? So this is similar to the original derivation of the Bellman expectation equation for state value function, but it is a little bit simpler even, right? So what is this one? I am at state s and took action a. What is the expected value of the return at the next step? I mean, this is the definition of r, s, and a, right? Because I already took action a, I don't need to have an expectation. I'm already at state s and took action a, so I receive r, s, and a, right? And this is still an expectation because maybe if I am at state s and take action a, the environment throws me at different next states. So I am kind of averaging over those next states or getting the expectation over them. So this is still an expectation, but it is really a compact form for this expectation, right? This is r of s and a, right? Or you could also have summation over next states, probability of s prime given s and a, and multiplying by r of s and a and s prime if you want. I mean, they are the same. Now let's look at this one. So here I am at state s and took action a at time t, but I want the return t plus 1, not t. So this is similar to the one we got before, right? We have a state, and then we could take multiple actions in this state, and every action you could go into separate next states, right? Something like this. So this is a state, this is a state, this is a state, and this is a state. So, but now we say that we took only one of those actions. So we want the expected return if we took this action. So we don't need to have an expectation over those. But even if you took this action, you could end up in multiple different next states. So you need an expectation over the next states, right? So that's why this right here, you should sum over all the next states, s prime, and then the probability of getting to s prime if you were at state s and took a specific action. So given s and a, right? And then for every one of those, you could get a different state, so a different value for those states. So you just need to multiply by v pi of s prime. So now this is really an equation for q, s, and a. So this is equal to q, s, and a, and this is equal to this one. We could just now take this here as a separate equation and call it equation 3 if you want. So this maps the action value function at time step t to the state value functions at the next possible states, depending on the environment dynamics. So this is the third equation we have. Now you could have one more equation. Now you have the definition of v pi of s prime or v pi of s. Right here you have v pi of s in terms of q pi of s and a. So you could substitute equation 2 into equation 3, right? So you could have another equation also for Q, and this is equal to R, S, and A plus gamma summation over S prime, probability of S prime given S and A. But then instead of V pi of S prime, you actually put another summation here over the next action. We could call it A prime, pi of A prime given S prime multiplied by Q of S prime and A prime, right? I need to use another A here since those are the actions that I could get from this state, right? So I need to sum over all the actions, while A is a specific action. Here I'm summing over, like getting an expectation over all the actions that I get in the next step, right? So that's why here we have A prime and S prime, not S and A. But this equation, this is the fourth like Bellman expectation equation. It gives you the Q at one step in terms of the Q value function at the following time steps, or at the following time step at t plus 1. So those four, you could call them the family of the Bellman expectation equations, and we will use them in different ways. Again, I have to repeat here that it might not be fully clear why do we need an explicit formulation for the action value function, but believe me, it will be clear quite soon. When we cover like model-free reinforcement learning, when we try to find the optimal policy without having a model of the environment, you will see why this is actually essential. Like most of the course will be working a lot, not necessarily more, but a lot with the Q value function, but we will also be working significantly with the state value function. Okay, so those are the Bellman expectation equations. You will often see people using those diagrams called like backup diagrams to visualize those equations, but really if you understand the equations you don't need those diagrams. Like in a way you have two diagrams. One here, this diagram B tries to represent this last equation in a way like you are at a specific state and took one action A, so you get a reward. So you get a reward, right? And then the environment could throw you at any of the next states because you don't control that, right? So you get a reward which is really the expected reward over all the next states, but here we write it in the compact form. We could also have written it in the more, R of S and A and S prime form. But then you could be thrown at any of those, and so to get the value of S and A, you really need to average or get the expectation over the two next states here, or all the next states, which is what we are doing in this equation right here. Now, for every one of those S prime states, to get the value of this here, S and A, you need to follow the policy pi from S prime and get the values of all those state action pairs and like average them together, like get the expectation. Why do we get the expectation here? Because we are following policy pi, and policy pi is stochastic, right? So from state S prime, we follow policy pi onwards, and that's why we have this expectation over the actions at the next state or at the next step, and already that's what we have here. So here you have an expectation over all the values of S prime A prime here, S prime A prime here, S prime A prime here, and S prime A prime here. So you need to have this for all the next states and all the actions from the next states, right? So this is really a visualization of this equation right here. This one is similar, but it is for the Bellman expectation equation for the states value. So it's really like this one. You could just copy it down with us again to see how to read the backup diagram. It's really not something complex. It's really just the same equation. So here you need the value of a specific state, but you follow policy pi. So in state S, you could choose any of the actions that the policy pi, allows you to do that. So that's why we have an expectation over the actions, or over the actions, yes. And then for every one of those actions, you have an immediate reward, right? And then the environment could still throw you at different next states. And that's why here you have an expectation over the next states for every one of those actions. So this summation is in a way inside this summation. And then you get the value of every one of those leave states, right? So those are called backup diagrams. They're really just visual representations of the Bellman equations, but you might prefer them as a visual tool. Okay, that's all what I wanted to say in this lecture. See you in the next one. Okay, this is a checkpoint lecture just to make sure we still understand the big picture, understand where we are, what we have covered and what we haven't covered yet. So we introduced the reinforcement learning problem, the MDP structure, and then we also introduced the concept of states and actions. We introduced the concept of a state value function and an action value function. So far, have we used any data at all? Have we done any machine learning at all? No. So far, have we found out ways to find out the optimal policy or to even improve our policy? No, not really, except for the fact that we can now, in a way, try out different policies at random and evaluate each one of those policies and choose the best one or mix them to get the best out of them. Sure, but this is not a proper algorithm to obtain the optimal policy. We still haven't covered anything to do that. So what we covered is called policy evaluation. We haven't covered what we call policy improvement, or it's called sometimes control. So policy control or policy improvements, we didn't cover anything for that. But even for the policy evaluation, we only covered the discrete case. We have discrete states and discrete actions, and the policy evaluation algorithm we covered can only work practically for small problems because we have a matrix inversion that is O of n cubed, and so if we have a huge number of states, this wouldn't work anyway, right? So far we didn't do any policy improvement, we didn't do any machine learning. Okay, we also covered this concept called the action value function, and we still didn't use it meaningfully, but we will use it meaningfully later on. In addition to that, even the policy evaluation algorithm we covered, the closed form solution, assumes we have perfect knowledge of the environment dynamics, of the state transition probabilities, and also the reward functions. And again, in real world problems, in a lot of real world problems, we don't know that, so we are overly simplified. What we covered is overly simplified. So we will start adding more and more complexities as we go through the course. This was the first checkpoint. See you in the next lecture. So this is one of those boring lectures where I introduce some terminology, but this is very important for us moving forward. So some of those terms I already defined before, like for example, the first one, policy evaluation. Policy evaluation is also called prediction or policy prediction sometimes, and this refers to any algorithm that we use to find the value function v pi of s or the action value function q pi of s and a. So this is called policy evaluation or the prediction problem in reinforcement learning. Okay, we already covered this, and we covered one of the algorithms to do it, even though it's not very practical. Now the second term is the term control, and by control we mean policy improvement. How do we control the policy? How do we control the behavior of our reinforcement learning agent in order to perform better and better in the world? So the word control means roughly policy improvement. Now we can do control and prediction, so we generally will do a lot of policy prediction or policy evaluation and policy control in the remainder of the course. So we can do that in a model-free reinforcement learning framework or in a model-based reinforcement learning framework. So model-based means again that we know the transition probabilities. Someone gives us the transition probabilities and the reward model, right? But while in model-free reinforcement learning, we are just thrown into the sea. It's like trying to teach a computer to play an Atari game, and you just give it feed of the video of the frames of the consecutive frames, and then you just ask it, please win this game. So it has no like rules. You didn't feed it the rules of the game. You didn't tell it that, you know what, if you bump into an enemy you lose points, and if you collect coins you get points. It kind of needs to learn that on the fly, or like via actual interaction with the environment. It should actually play the game. You know, another maybe simpler example, if you are, you know, playing karate or like any, you know, physical fight sport, and then you are just thrown into the arena with some opponent, and you know nothing about this opponent. You know nothing about their style. You know nothing about anything. You didn't watch like their previous games or something. So you don't know if this person, you know, uses their hand more or their legs more, or you don't know anything. But then you just, you know, via interaction in the actual game, you start figuring out, you know what, maybe this person, when this person like punches me with their head, with the right hand, I need to counter that, or the best action or the best policy is to counter that with some move from my left leg or something. You know, I really don't know anything about karate, but it's really this: you get thrown into the sea, you are not given any prior knowledge, you don't know anything, and you just learn from experience by trial and error. So we call that model free. So model free reinforcement learning is nice since you don't need the model of the environment, and you still could perform very well using the algorithms that we will cover later. However, the bad thing about model-free reinforcement learning is it is sometimes very expensive. Like, you need to interact with the environment. Now, for a video game, maybe that's fine, right? It's just a simulation at the end of the day, or a software. But if you are trying to teach a robot, like a very expensive robot, to, you know, cross the street using only model-free reinforcement learning, and this street has a lot of speeding cars and so on, then you might cause a lot of problems and do a lot of trials and errors until you learn something, and then you will lose a lot of money because you will crash a lot of those cars and a lot of those expensive robots, right? So sometimes trying to estimate a model first and solve the problem as a model-based reinforcement learning problem makes like more sense. Sometimes it doesn't, so this is really the job of you as an engineer. Okay, so let's move to the following term, the term planning. So planning is a way to do control. So control is policy improvement, right? You can do policy improvement by what you call planning in model-based reinforcement learning. So to think of planning, like, it's really, you know, suppose you are playing chess. Like, the rules of chess are known. So in theory, you could, you know, plan your game before the game happens, right? Like, you could run simulations in your head. You know, if my opponent does this, I can do that. Like, you could just, you know, learn the chess rules and then go to bed and just do like this, and then try to think, okay, what should I do in every single situation? Obviously, the number of states is huge, so you can't do every single situation. But in theory, if you know the rules of the environment, you can do planning. Like, suppose you are playing a game like, you know, Red Alert 2. I love this game. It's a strategy game where you have armies and try to win and so on. Now, you can just learn the rules of the game, and then you could, again, go to bed and think, how could I beat, you know, 4 brutal enemies at the same time? And then you try to design, you know what, yes, I could use aircraft in the following way. I could use navy in the following way, and, you know, those specific tanks and so on. So you can plan in your head or in simulations without interacting with the environment. And so planning is a way to improve the policy if you know the model of the world. And you could do some planning and then, you know, work in the actual environment, like play a specific Red Alert game, right? And then you find some more feedback. So you plan again and then do another round of interaction and so on. And this is useful if the model you have is not perfect. So you have some model that is reasonably good. So you plan using it and then interact, and then you could find some more problems. So you gain this knowledge and then plan using the updated knowledge. In a way, you update your model of the reward and of the transition probabilities, and then you do that again. So this is also one way that you could solve this expensive robot crossing the street problem, where you start with some model, even if it's not a perfect model, of the rules of the environment, of the physics, of what is the best ways to control your motors for all your joints and so on. You start with something, and then you start it in the world, and then it might fall a little bit. It's not great, but then it can learn from this experience, improve its model, and improve its policy based on this. So you could mix model based with model free somehow. Okay, so what I wanted to say is planning is a way to do control when you have a model of the environment. I would like to deviate a little bit from those definitions here and mention something more about the robot, learning to walk and also learning to cross the street and maybe learning to drive. I just want to mention that reinforcement learning could be done kind of in layers. Like the first layer could be just teaching the robot to walk. The robot is just, it doesn't know anything. So in this case, maybe the states and actions are defined at a very low level. Like the actions could be, some movement or some voltages applied to different motors. So if you are still teaching the robot to walk, then the actions might be in a very low level, just, rotor voltages or something. But then once the robot can walk perfectly, you could then have another, higher level reinforcement learning problem where you teach it to cross the road. And so the actions in this case would be, look left, look right, like make sure that cars are not, close by, measure the distance. Like it could be actions that are higher level than just the voltages. And maybe later on when you teach it to maybe drive, you have another set of actions that are maybe even higher level, and so on. So I just wanted to mention that you could do reinforcement learning, at different levels or different layers. You could also do reinforcement learning at different time steps. So maybe you teach the robot to, walk. So the time step here is very small, but you also teach it to do something else that, takes a larger time span, like deliver boxes to customers. So the journey from one place to another could be an hour, while for walking, maybe every time step is, maybe milliseconds or seconds to control the rotor voltages and so on. So you could also have, multi-time step reinforcement learning if you want. Although I will not focus so much on it in this course, I just wanted to be at the back of your head. Okay, so this was a deviation, but now let's come back to our problems here, or our terminology here. So let's talk about search. Search is interesting. You could think of it as a subset of planning. Like in planning, your goal is to find the optimal policy at each one of the states you care about, or the states of the system. In search, you are trying to ask a different question, like, given I am already at this specific state, what is the best plan moving forward, or what is the best policy moving forward? I don't want to solve everything. I just want to solve my current situation. It's more localized. Let's give a concrete example. Suppose you are still playing this strategy game, this red alert game, right? So planning would be, what is the best policy in all the cases? What is the best policy if my enemy is air force heavy or naval heavy or tank heavy? What is my best policy if this map has a lot of gold or money to extract from the ground, or oil? And what is my best policy if this land is very scarce? And what is my best policy if I am facing the allies forces or the Axis forces in the game? You need to solve everything. This would be planning. Or in chess, for example, planning would be, I need to find out the optimal policy for every one of those tremendous amounts of states. This is planning. While in search, you are playing chess, your opponent already did a move, right? So starting from this state, what is the best thing you can do? You don't care about the other state where the opponent didn't make this move, because the opponent already did that move. So it will be a waste of resources to try to solve everything while you already know that the opponent already did something, right? And this is especially true for cases where the state space is huge. Another third example would be, you are in a hiking journey, right? And you get stuck up of some of the mountains alone, then if you do planning, you need to plan what is the best policy where I could get back to camp from any of those different mountains. While search is just, you know what, I am already on this specific mountain, I need to get back to camp, what should I do, right? So this is search versus planning. In a way, search is a subset of planning, but in a lot of cases where you have tremendous amounts of states, search could be the better thing to try out, not find the optimal policy everywhere, okay? So I think this is enough for this lecture. See you in the next one. So this is another short lecture where I want to talk a little bit about non-stationary MDPs. So there's roughly two versions of this that I'd like to talk about in this lecture. One of them, or version 1, is what if the environment dynamics or the rewards of my MDP or even the optimal policy depends on the time step. So for example, you have a power plant, and the optimal operation policy of this power plant could be different based on whether you are in the winter or in the summer, right? So in a way, at time step winter, you do something different than time step summer or something. Or maybe a more, fun example is the agent you have is a kid, and this kid wants to go to the park, right? So he's trying to find out the optimal policy on how and when and where to talk to his father and ask him, please take me to the park or give me some money or something. And from this kid's perspective, he's a small kid, so he waits for his father to come home from work, and then he asks him, let's go to the park. So sometimes the father comes from work really relaxed, right? Maybe tomorrow is the weekend, so the father is relaxed. Sometimes he comes from work and he's very stressed because tomorrow is a customer meeting or something. So from the kid's perspective, at the same state, which is father just entered the house, sometimes he gets different rewards from the environment, which is his father. Sometimes he gets a yes and sometimes he gets a no, okay? So, how to solve this using our general MDP framework? I'm pretty sure you already, are thinking of the solution, which is if really the MDP is non-stationary in this format, then maybe the state definition itself that you chose for the MDP is not rich enough, and you need to enrich or augment the state definition. So for example, for this kid example, maybe the correct state is not just father just entered the house. Maybe the correct state should be father entered the house and tomorrow is a weekend. Or father entered the house and tomorrow is a work day, right? So maybe you need to augment the states in order for them to really follow the Markov property so they are rich enough. And for the power plant, maybe the correct state is not just the, the state of the plant itself, but you should maybe augment it as well to include, are we in summer or in winter? So this is an easy solution. But there is another form or another version of non-stationarity of MDPs, which is really the environment itself is changing maybe gradually over time. Like the environment is really not fixed, right? So maybe you are talking about MDP that describes, the world politics. So the world politics, the frameworks you use for the world politics, like before World War I is different than after World War I, and also different after World War II, right? Like the environment itself is really different. So the optimal policy really is not the same in those different periods, right? But you still need to act optimally in all of those periods, roughly, right? So one way for us to deal about this, and we will cover this actually later, is we try to not have a completely deterministic policy. Like we always need to keep some exploration in our policy, right? Even if we think that right now this policy is the best one, like, at some point maybe gold is the best, asset you could buy. So, and it rises in price like skyrockets and so on. So maybe at some specific part in time or region of time, gold is the best thing you could buy. But maybe in another region, real estate is better. Maybe in a third region, stocks are better and so on. So in a way, you need to always have some exploration in your policy and not have it a deterministic policy and like, stick to a specific set of actions and just, live with it forever. You need to keep some exploration to counter the fact that maybe the underlying environment changes somehow after some time, and you need to be able to notice that and changes. So in reinforcement learning, and change your policy, I mean. So in reinforcement learning, there is always this concept of exploration versus exploitation, and I will talk about it in the next lecture. So one of the most important concepts or balances we need to strike in reinforcement learning is the balance between exploration and exploitation. Like, remember that reinforcement learning, we try to learn via trial and error, via interaction with the environment, and we don't always have a perfect model of the environment that is perfect. I mean, we almost never have this, except for some maybe, board games and so on. So in the previous lecture, I already mentioned one reason why you would like to keep exploring like forever, right? Which is maybe the environment dynamics itself in real world could change like over time. Like maybe at some period of time, investing in gold is the best option, while in another case, maybe in like, 5 years later, maybe it is real estate, 5 years later, it might be stocks and so on. So the environment might change. And if you keep exploring and have what we say stochastic policies, or at least policies with some stochasticity, it probably will protect you better from the changing environment dynamics or like environment rewards, right? But there are other reasons why you might keep exploring, at least to an extent, even when the system is completely stationary, which is, even if the system is stationary, you might not have the perfect model of the system. Maybe your model is approximate, or maybe you do not have a model at all. In which case, like reinforcement learning, we learn from trial and error. We learn from interaction with the environment, right? So if you, try some things and find something good enough, you don't want to 100% stick with it or commit to it 100%, because there might be something even better and you never know about it, right? Like if you, for example, go into a restaurant and you find a decent restaurant, right? Maybe you could keep exploiting that restaurant and always eat in the same restaurant, or maybe you decide to explore other restaurants, maybe you find another one that is better, right? Or maybe if you are in charge of placing ads on a website or on the road, maybe you find some ad idea that's catchy and you use it, and then you could exploit it and use it all the time. But maybe you also need to try out different ideas, some crazy idea here and there. Maybe one of them will be even better. So this is exploration versus exploitation. Another example is maybe you graduated college and you got a job with a very decent salary, so you could keep just exploiting being an employee, or maybe you could try, what if I start my own company? What if I, work as a freelancer or something different? Maybe you actually could be better in one of those other options, even if the option you have is good. So in general, we need to keep some exploration, even if we got a really good policy, because maybe there is an even better policy. This is even more important when we are model free, because now we don't have a model of the environment and we need to keep trying different things until we are extremely confident that, this is the best we could do. Then we can switch into a greedy policy or like a deterministic policy. However, we should still keep some exploration probably, because we don't trust ourselves 100% anyway, even if we trust ourselves like 99%. And also because the environment in real world could be non-stationary a bit and change, and the reward model changes over time, and the optimal policy also changes over time. So this is the concept of exploration versus exploitation, and we will actually deal with this concept a little bit more in the future. So in this lecture, I'd like to talk about the concept of an optimal policy and optimal value function. So let's start with talking about the optimal value function. So we know the state value function v by s, and the definition is the expected, return if I start at state s at time t. What is the score I will get until the end of episode for episodic MDPs, right? Now, the definition of an optimal state value function, we call it v star, is really like starting from this specific state, what is the maximum possible value I could ever get if I am following the best policy, the perfect policy, the most perfect policy, okay? So an example, suppose you are playing an Atari game or Super Mario or something, and then you are at the initial state, at the beginning state, and you ask yourself, from this state, what is the maximum score I could ever get? So this would be the optimal value function for the initial state. Now, if you are at the middle of the game, suppose you are at the middle of the game and then you have, a huge pile of cash in front of you. Now, the value here would be high because you are very close to getting this huge pile of cash. But after you take this huge pile of cash, the optimal value function will actually drop significantly. And that's because the value function really is future looking. It says, from now onwards, what is the score that I could get, right? What's the highest score I could get? It doesn't take into consideration what happened in the past. And this is why if you are working with reinforcement learning and then you try to plot the value function over time, you might often do a really, really good action and you see your value function dropping significantly after you earned a lot of money or a lot of score. And this is normal. It might seem counterintuitive, but it is really like normal, right? So this is maybe a little bit counterintuitive, but I needed to say it. Now let's define another value, which is the optimal state action value function, or sometimes called just the optimal action value function, Q star. And this really means, suppose I am at state S, okay, and then I actually do action A. So this is not now under your choice. I already take action A. What is the maximum possible return I can ever get? Or what is the maximum value, or what is the maximum score I could ever get from the next step if I follow the optimal policy from the next step onward, right? Not from this step onward, but from the next step onward, because at this specific step or time step, I already took action A. It might be optimal, not optimal, I don't care. I already took action A. But now, if I become, disciplined from the next step onwards, and I always take the optimal policy from the next step onwards, what is the maximum value or maximum score I could ever get? So this is what this is, trying to tell you. And now this is interesting. This is super interesting, because if you have, the optimal action value function for all actions in a state, let's say A1, A2, and A3, right? If you have this, then, and you have, let's say, Q star of S and A1, this is equal to 10. Q star of S and A2 is equal to, let's say, 12. And then Q star of S and A3, this is equal to, let's say, 13 for now. Then you know that the maximum value you could ever get from this one, if you really react perfectly, optimally, later on, for all the next future steps, the maximum you could get is 10. For this one, the maximum you could get is 12. And for this one, the maximum you could get is 13. This means that the optimal policy at this state is to choose A3, right? This is really just act greedily according to those, assuming that those are the only valid actions in this state, right? So you could get the optimal policy, and in this case, it would be a deterministic optimal policy. And this is because, you can use this to choose the policy directly, because this Q is not really just the immediate reward. It really factors in all the future discounted rewards, right? So it is not something short-sighted. It is really far-sighted. And so that's why knowing the Q value function, the optimal Q value function for every state and action pair in all states and for all actions, you really know the optimal policy in this case. Okay, so this is very important, and I will come to this point like later in this same lecture. But let's actually talk about something different first. Like, let's talk about the optimal policy pi star. So for MDPs that are single agent, okay, and where the environment is stationary, it doesn't change over time. We talked about non-stationary environments before, but assume that environment is typical environment. Like, I'm trying just to cross the road. I'm trying to say the environment doesn't try to, you know, act in order to make you fail, right? Like, suppose you are playing against an opponent, you are playing rock, paper, scissors. Now the environment, which is the other agent, is really trying to make you fail. So whenever you get to a perfect deterministic policy, this other opponent will try to exploit it and make you fail. So this is what I mean when I say the environment is trying to make you fail. But what I'm trying to say here is, if the environment is really like neutral, it does not try to make you fail, and the environment is stationary, and you have a single agent, no multiple agents trying to make each other fail, then you can always find a deterministic optimal policy. Like in this case, I have this state, and I have those values. The optimal policy is just to act greedily and choose A3. So this is a deterministic optimal policy, and you can find at least one deterministic optimal policy, but you can find multiple deterministic optimal policies in some cases. And this happens if you have something like this. Suppose that the action value function here, the optimal one, is also 13. Then there is a tie, and whenever there is a tie in the optimal action value function, then you could really choose a policy deterministically of A2 or deterministically of choosing A3. But you could also have a stochastic policy where you say, you know what, pi of A2 given S, I just choose this like 50% of the time, and pi of A3 given S is another 50%, right? Maybe, or maybe 30% and 70%. Like anything of those like could work, right? Because they are equally good, I would say. So this is why I could say that you could have multiple optimal policies, and this is an example here. You have multiple optimal policies, and also they could be deterministic or stochastic. But at least for single agent MDPs, where the environment is stationary, you could always find at least one deterministic optimal policy, right? Another maybe concrete example is suppose you have a building, right? And you are at this state here, and you would like to reach this state here. So again, you have two different paths that cost you the same, really. So either go right, then up, or maybe go up, then right, right? So the policy here is there are multiple deterministic policies, or you could also define a stochastic policy at this state. So maybe pi of up given x, maybe you choose to do that, you know what, you are going to work. So 30% of the time you go up, then right, and then maybe 70% of the time that's given x, then maybe 70% of the time you go right. But here at this state B, the policy must be deterministic here. So the optimal policy, I'm talking about the optimal policy here, 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 and also here actually. This is the optimal policy, okay? Pi of up given B, if you are choosing the optimal policy, this is really 100%, okay? Now you could have multiple deterministic or stochastic optimal policies, but all of them must have the same optimal state value function, right? Because if you have two policies and one of them has a value of state S, like V of S under pi 1 is equal to, you know, 10, while V of S under pi 2 is different, is equal to 12, then pi 1 is not really an optimal policy. I mean, this is by definition not an optimal policy. So if you have different value functions, then one of those policies is not optimal, and only the other one is optimal, right? This also applies to the optimal action value function, although it might sound a little bit counterintuitive. Like, let's say I have, you know, state here, and I have this action, right, and this action. What does it mean when I say that the optimal, all the optimal policies will have the same action or optimal action value function? I mean, maybe one optimal policy only goes through this path. It never goes into A1's path. So what does it mean? And the answer to that is the optimal action value function. You think of it as a property of the map or of the system, not really of the policy, right? It doesn't care. This is the maximum value you could ever get. This is the maximum value you could ever get if you start from state S and choose action A1. It doesn't really care if the optimal policy never chooses A1. This is irrelevant. I'm just saying that if you already, for whatever reason, decided from state S to take action A1, this is the highest possible value you'll get. Or another way to look at it is, this is the value you get if you take this decision here, I mean for whatever reason, and then from whatever next step you end up in, you start acting optimally again, right? You start following the optimal policy again from time t plus 1. Now let's cover an extremely important point. Like I said here, that if you know the optimal action value function for all actions and all states, then you could act greedily and find the optimal policy. Now the question is this also the case if I only have the state value function, the optimal state value function, the star? Like if I know the optimal state value function, the star, can I get the optimal policy? And the answer is no and yes. I mean, it really depends. And it depends on whether you are model based or model free. Like if you are model based, you know the environment dynamics, and then yes, if you know the optimal state value functions, then you know the optimal policy, you can derive the optimal policy. But if you are model free and you don't know the reward model of the environment and the state transition, then just knowing the optimal state value function wouldn't help you much, because in this case, the different states are really just different like islands. Like you have those islands, maybe SA, SB, SC, and SD, right? So maybe you know that the best value for this island is really, 1000. Maybe for this one it's 10. Maybe here it's -10. And here maybe 100, right? So you know the optimal state value functions, but you really don't know how to get from one state to another. Those are islands in a sea. Like maybe you try to do something like this. Maybe you try to choose action AI or A1, right? But then you don't know the environment dynamics. So maybe if you try to do that, the environment will actually throw you here. You don't know. Or maybe throw you here. So here, let's say for 90% probability or 80% probability, you go here, and then 20% probability you go here. So you try to go to this island, but you really don't know what the sea does to you. The sea is very chaotic, and you don't know it. Or maybe even the sea doesn't try to throw you away, but you try to go here and you already go here correctly, but the reward or the cost you get along the way is like something like this. This is also possible. This is the reward model. Like maybe you try to go from one island to another, but the sea is completely chaotic and you just destroy your ship. And again, you really don't know. And the thing about state value function is, again, it is future looking. It doesn't really care what you did until you got here. It just tells you, if you are here, I'm gonna give you a treasure. If you are already here, in the future, expect a treasure, okay? But it doesn't really care what you paid until you reached here. So this is why, if you know the optimal state value function without knowing the model of the environment, this is not enough to get the optimal policy. But if you know the optimal action value function for every state and action pair, then this is enough to get the optimal policy. Our goal in reinforcement learning is to find the optimal policy, and then we will cover some ways in model-based reinforcement learning where we get the optimal state value function and use the model to get the optimal policy. So we'll cover this, and then we'll also cover ways where we are model-free. So we try first to estimate the action value function directly, and then use that to get the optimal policy. And then we'll also, towards the next half of the course or the end of the course, we'll try to cover ways where we try to optimize the policy directly, try to find the policy directly without first trying to estimate this proxy, which is the optimal action value function. We will try to design ways to just get to the optimal policy directly, and this is extremely important, and it's used in a lot of recent developments in reinforcement learning. So I think this is enough for this lecture. See you in the next one. So previously we introduced the 4 Bellman expectation equations under a generic policy pi or an arbitrary policy pi, and we also covered a way to solve for V pi. And since we know the model dynamics, you could also solve for Q if you know V, right? In the case we covered where we know the model dynamics, where we converted the MDP into an MRP and so on. But now we would like to have a version of those equations that really defines the optimal value function instead of a generic value function under a generic policy. So we need to do some tweaks to those equations to represent our optimal value functions. Like, I would like you to really remember when I introduced those equations, I asked you to think of them as really a definition of the value function, right? It is a recursive definition of the value function. If you could find some numbers that satisfy all those equations in a way that is self-consistent for all states and actions, you have found the true value function. So it is really a definition for the value function. And similarly, we would like to introduce a definition for the optimal value function that will allow us to find this optimal value function, like numerically, using this definition, if we are able to solve those equations. Okay, so actually let's try to work on those equations one by one. So the first one here, if we have a fixed policy, the value of this policy is really a summation over, or an expectation over all the actions, because this policy, for this policy you could choose multiple different actions, and then for every one of those actions you have a different Q value, right? But now for the optimal policy, you only choose one action and act greedily according to it. Again, we are assuming that we are single agent and in an environment that is really stationary, because you remember the rock, paper, scissors example. I didn't continue on it in the past lecture, but really if you are working rock, paper, scissors, the optimal policy is gonna be stochastic itself. It must be stochastic, because then your opponent will not be able to exploit you. But here we are talking about single agent and a stationary environment, so the optimal policy is deterministic, and we are trying to find this deterministic optimal policy. And that's why the definition here, we could say that the optimal policy here will be deterministic. So we are going to choose one action that has the most, the maximum value. So we say that instead of trying all actions and every action has a probability and has its own value, we really need to maximize over all the actions the value of this action. So we say that for a specific state, the optimal value of a state is really, the way we get it is we see all the actions and have a look at all the action value functions of all those actions and just choose the action that maximizes this one, right? So this is really the definition of the optimal state value function in terms of the optimal action value function at the same time step, right? So this is the Bellman optimality equation. It's called the Bellman optimality equation for the state value function. And let me clean this a little bit. So this is V star of S. Again, this is a definition, right? Now let's try to also think about the second equation. This says that the value of a state action pair in terms of the value of the next state is really the immediate reward you get and then a discounted return. And this term here is really the environment dynamics, right? P of S cap or S prime given S and A. This is the environment dynamics, and you can't control those. So you cannot remove this expectation and switch it with a max operator like you did here in this term right here. You were able to do this since you can choose the action. It is your policy, but you can't really do anything about the environment dynamics. And this really means that the optimal value function for S and A, if you want to define it in terms of the next state value function, optimal value function, is really going to be roughly the same equation. So you get an immediate reward because you already chose this action. You can't take that back, so you get that reward, and then you have gamma, and then you still need to have an expectation over the next state probabilities, because that's what the environment is able to do, right? You can't choose this, but you can choose what you do later on and you want the optimal action value function. So here you can choose the optimal policy from all the next states. So this is under your control, and this is how this equation like translates. In a way, you could think of this as a definition of the Q, the optimal Q value function. Okay, so this is the second equation. Now let's look at the third equation. It's a little bit bigger, but again, there are some stuff that you can't control, like this term here for the policy, but then the environment dynamics you can't really control. So again, if you want to map Q star in terms of the next time step actions, then you can define this as Q star of S and A is equal to the immediate reward, because you already took the action, and then a discounting. You can't control the environment, so you need to put this the same S and A. But now here you don't really need to try all the next state's actions and average them out. You need to choose the best one again. So you can convert this summation into another max, but now it's max over A prime, right? And then you have Q star of S prime and A prime, because this is under your control, and this is the definition of the third equation. This is the third Bellman optimality equation. And then the fourth one will do really the same. You can control the policy, so you can always choose the optimal policy or the action that is best with 100% probability, right? To have a greedy action. And so you could define V star in terms of, the V of the next state to be equal to maximization over all the actions. And then you have R of S and A. So you choose one action, and then for this action you see where the environment throws you. So B of S prime given S and A. And then from each one of those potential next states where the environment threw you, you need to work optimally from there onwards. So that's why you have something like this. Okay. So this is the fourth Bellman optimality equation. Okay, so our goal is to find, now let's assume we are model based, so we have the environment dynamics, right? So our goal is to really find the optimal state value function, right? And since we have the environment dynamics, then we could really find the optimal action value function if you want, given the optimal state value function for all states, right? Because in this equation you can convert the optimal state value function into the optimal action value function, and if you have the optimal action value function, then you really know the optimal policy. So in the next couple of lectures we will assume to be model based, and we will really try to only find the optimal state value function, at least for some time. And then we will see how to find the optimal action value function as well. But those are extremely important equations. You could think of them as the most important equations in reinforcement learning. They are called the Bellman optimality equation. So let me write that down just to let you know how important they are. So Bellman optimality equations. And in the next lectures, we will try to really solve those equations. We will try to solve them, which means we want to find values for all the state value functions that are self-consistent for all states, right? And if you could find that, then you have found a solution, because you need to think of this as a definition. Now you might be asking, okay, can we do the same? Can we just convert those from an MDB into an MRP and then solve it using the matrix inverse? And the answer is not really. This is more difficult because this is not a linear system of equations anymore, because you have those max operators, and the max operation is non-linear. I mean, the expectation is linear, and so that's why you got, in the end, you got some sort of assembled linear algebra solution. But now you have non-linearities, and so the solution is a little bit more difficult. But anyway, anyway, we didn't want to rely on matrix inversion because of the high cost of it. And anyway, we said that there are some iterative solutions that could work for slightly larger problems. They still couldn't work for extremely large problems, in which case we need to use sampling and machine learning. But for at least slightly moderate problems, you could still have some iterative solutions like that are just math at the end of the day, not machine learning, but they are just math, and those tend to work reasonably well in model-based problems where the number of states is still not huge. And that's what we will try to cover next. And then later on, we will try to see, okay, what if the number of state space is huge? And what if you don't have a model of the environment? In which case, we will revert to samples and, data-based kind of solutions using machine learning, but that will be like later, okay? So in the next couple of lectures, we'll try to solve those equations. So yes, our goal is to find an iterative solution to the Bellman optimality equations to find the optimal value function. Yes, but we can actually take a step back and try to find an iterative solution to the Bellman expectation equation first, like under an arbitrary policy pi. And we will find out that this iterative algorithm will also be very similar to the algorithm we find for the solution of the Bellman optimality equations later on. And the reason we do this is anyway, even for the Bellman expectation equation, we would like a method that does not require us to first convert the MDP into an MRP and then do this matrix inversion, because anyway it does not work except for very small problems, right? So let's actually try to do this. And in this lecture, I'm going to introduce an algorithm or an idea without proof. And then in the next couple of lectures, I will make a very, exact proof of why this works. So the algorithm is pretty simple in a way that might be, disturbing. So the algorithm really says, this is the Bellman expectation equation, and we will focus on V pi for now, not Q, but it really is the same for Q as well. The algorithm says, just apply this equation over and over again. Let's just start initialize with some random initialization of the value function for every state. For example, if you have 5 states, you could just define the 5 state values to be 5 zeros, like 0, 0, 0, 0, 0, right? And then just try to iteratively apply this same expectation equation for every state multiple times. Like convert this expectation equation into an update equation. Like in a way, the algorithm claims that one proper way to get to the correct value function is to do something like this, like, randomly initialize or zero initialize the values for all states. And then for every state, you really sum over, or like take an expectation over all the actions, pi of a given s, right? And r of s and a plus gamma multiplied by the summation here, s prime. So let's actually take this with me here. Probability of s prime given s and a, right? And then multiply this by the value function of s pi. And so you loop over all the states, and for every one you apply the this equation, right? And then you finish, let's say, the 5 states. Then you start over again, start from the first state again, and do this again, and then start again. So it's kind of an algorithm with an outer and inner loop. And the claim is, if you do this like a sufficient enough number of times, you will eventually reach the correct value function. So it seems like a very bold claim. It's not immediately obvious why this is the case. And this is why I will actually prove this in the next lectures. And it will be a little bit long proof. But I think it is necessary. It was necessary for me when I first saw that. Like, I need to know why this works. But in this lecture, I'll try to give an intuition of why this might work. And the intuition is, like, let's think about a special case of MDPs where you have one goal state And in this goal state, you actually, when you jump to this goal state, you really get a huge reward. And maybe there's also another, lose state where if you jump to it, you get an immediate, like a very big bad reward or bad penalty. Like in this case, you could think intuitively that when you do this algorithm, like some states are extremely close to those terminal states, right? So maybe one state is extremely close to the goal state, and this state will really get a huge reward. Like this R for this state will be huge. And so if you apply this equation to this state, multiple times, its value will really reflect the reality. It will be like grounded well enough in the reality. And then at later iterations, the states close to it or next to it will start getting more of that reality, right? Because every state that could reach this, very good state will also have high value, and this value will become more true in the next iterations and so on. So it is like the knowledge spreads from those, terminal states, either positive or negative, and then you could really imagine that this spread of knowledge will continue over time, and in a way, because those terminal states have very strong reward signals, they will be more grounded in reality, and so this will spread later on throughout the entire system. So this is the intuition. It is not enough for multiple reasons. For example, not all MDPs actually have terminal states, right? Some of them are continuing, and so maybe it's not really that simple. But this is a good intuition to have. But this doesn't mean we don't need the full proof, and I will provide the full proof. But before we go into the full proof, I would like first to give some concrete example of this algorithm, some numerical example, just to make sure that we all are on the same page regarding what the algorithm is really trying to do. So let's do that in the next lecture. So let's go through a numerical example of this algorithm, this iterative algorithm. So suppose we have this problem. We have, 6 states, 2 of which are terminal states, and we have some policy, and I chose a policy that is a little bit non-deterministic. I also define part of the MDP definition would be the gamma, the discount factor. So here I use it to be equal to 1. And then I define also the reward model, that R of D. If you are at D and go left, you get a reward of -10. If you are at R and if you are at C and go up, a reward of -10. If you are at C and go down, a reward of 10. Otherwise, the rewards are 0. And now when I have this drawing for the actions, I assume that they are uniformly distributed. So here, for example, you go to the right from A to B deterministically by 100% probability. But here you are 50-50. And here you are, third of the times you go up, third you go left, third you go right. Right? So this is what I mean. And finally, in this specific example, I assume that the environment dynamics are deterministic. Like when you try to move from A to B, you end up at B. The environment doesn't, throw you away randomly into D or C and so on, right? So this is just the definition of our world. And let's see how the iterative application of this equation right here at different time steps or iterations k of the algorithm will eventually lead to the correct value function. So first, actually, since the environment dynamics is deterministic, then probability of S prime given S and A is either 1 or 0. There is no need to have this summation. We can actually simplify this equation a little bit. So we can say that V by of S is equal to summation over actions, and we can't remove this since some of our actions are stochastic, so we have to have this expectation in general, right? And then you have R of S and A, and gamma is equal to 1, so we could just drop it. And here you don't really have this summation over next states, since it is deterministic. If you took action A from state S, you know exactly where you will land. You will land in one state that is just the function of S and A. So maybe just call it S prime of S and A. Like there is no need to have this expectation. So this is why we simplify the equation like a little bit. Okay, so now let's see how this algorithm works. We first at iteration like 0, we start by initializing the values with maybe value of 0. So let's just get this a little bit down here in order for us to be able to see it. And now I initialized my algorithm here. So let's just have this right here, and let's clean this up a little bit and have a... Okay, so at iteration k equals 0, right? You initialize all the values for all the states to 0, and by definition the value of the terminal states is always equal to 0 anyway, since the future return you will get is always 0. And here I have the same policy written just for simplicity, like to be able to look at it. So now the equation is going to be v at iteration k plus 1 is equal to this summation, and for all the values here to be at iteration k. So you could really say that v for any state s at iteration k plus 1 at the next iteration of the algorithm, and here you could just say iteration k. So now we have the values at iteration 0, and we want to compute the values for all states at iteration 1. So for example, you could say that the value of at iteration 1 here of state A is the summation over all the possible actions to be taken from state A, but you could only take one action, so that's nice. This now is simplified, and the reward you get is actually 0, right? That's by definition here of our rewards. And then you say, and you end up in state B is equal to v0, right, of state B. So this is equal to 0. So at k equals 1, which is, you know, my table down here, k equals 1, I know that the value of A will still be 0, right? But then I need to do that for all the other states. So I need to do that for state B as well. And state B is a little bit more interesting since from state B you could go to here or here or here, depending on those probabilities. So it is 1/3 multiplied by something for everyone. So 1/3. Let's look at going left first. Then we need the immediate reward, which is 0, and the value, which is also 0, the value of state A, which is also 0. So this is 0. But then plus 1/3, and you do the same for the other transition upwards. But again, the reward is 0 and the value is 0, so you get 0. And then also another one here. So you get this to be 0. So anyway, you put here 0 again. This is not updated. But now if you look at C, C will be potentially more interesting, because for the calculation of C, you need to, you can either also choose one of 3, and then you have 1/3 of. The reward of going left is 0, and the value function of B is 0, so that's 0, right? Now if you look at the next action, let's say the action up. So we still have 1/3 probability of doing that, but the reward of going up is -10, and the value of the terminal state at time 0 or at iteration 0 or at all iterations is still 0. So you do this, and then you could also go down and get a reward of 10 plus 0. So unfortunately this stays at 0 at iteration 1 again. So C, you will be 0. Okay, not very interesting. Now we could also try out D. So V at k equals 1 of the D state. Here you could have one of 2 actions. So it is 1/2. For the down path you will get 0. And then for the right path, you will finally get something that is not 0, which is actually -5, right? So here you get, yes, -5. And this means that D is the only state that got updated in this iteration. So, I mean, we have a long path ahead of us, but I hope that you understand what we are actually doing right now. And also it makes sense that the one state that got updated is the state that it is one of the states that are very close to one of the terminal states. I mean, C should have also been updated, but it got balanced out between this red square and this green square perfectly, so that's why it wasn't updated at this iteration. But now you need to really apply the same again for the next iterations, for k equals 2 now. And so we can just define here, okay, k equals 2, and then you do that over again. So let's do one more time. Let's do it one more time, and then we will switch to a Python environment so that we could really see where this ends up at. But I'm just trying to let you know the algorithm is really a nested loop algorithm. So at iteration 2, you still try out v2 of a, but now you know that for a you only go to the right, and the value of b at the previous iteration is 0. So value 2 of a will actually still be 0, and then v2 of, let's say, b is interesting now, I guess, because b you could go to D or A or C, but D was changed in the previous iteration, so B will start getting some value from D now. So you have 1/3 multiplied by 0 plus 1/3 multiplied by 0, but then you have 1/3 multiplied by the value of D, because the reward is 0. The reward is 0 here, but this value is equal to 5 or -5. So now you will get something like this. So this is -5 over 3. So that's, I guess, interesting. So this is 0, this is -5 over 3. Now if you look at maybe, let's actually look at D again. Or maybe let's go in order and look at C. So at C you have still 1/3 multiplied by the value of B of the previous iteration, not this iteration. So it is still 0, not -5 over 3. So this is called a synchronous update. You always kind of take a copy of the original or the previous value table or array or dictionary, however you implement it. And to update stuff at iteration 2, you look at the old table at iteration 1. You don't look at the current table, right? So this is, let's say, the vanilla version of the algorithm. Although, to be honest, it really doesn't matter. Like if you also use the same table without having this previous copy, it will work. But I will keep with the original algorithm because this is the one that I will actually prove later on, and it's really the original algorithm. But later on, people also proved that you know what, you could really use the same array here, and it will work anyway. This is also proven, but I'm not gonna prove every variant. I'm gonna prove the main variant. So here, 1/3 multiplied by the value of B from the previous iteration, which is 0, and then you get 1/3 multiplied by 10 and 1/3 multiplied by -10. So actually C will keep 0, unfortunately, for this iteration as well. So 0 plus 0, so this is 0. Now D is also interesting, but D you have 1/2 multiplied by the reward here, which is again -10, and then 1/2 multiplied by the reward to go to B plus the value of B, but again the value of B from the previous iteration, this is 0, so it will actually be like the same, so it will still be -5. So it will stay -5 as it was, and C will be like 0, and G and L will be 0, right? So I think you got the algorithm. Now you need to try it again for k equals 3, for k equals 4, and so on, until you find, a case where nothing is updated anymore. None of the states is updated anymore, in which case you have reached the end of the algorithm, because no update happens. And if you, after you reach this state, you actually try out putting everything into the Bellman expectation equation, you will find self-consistency, and you will find that all the values are, consistent with each other, and you will have solved for the value function. Okay, so this is the general idea. I hope I didn't make any more mistakes in the numbers, but let's look at the code now and see those in action. Like, I've written this code with the help of Gemini, obviously, but it doesn't really matter. It's a simple, very simple code. So I define the states A, B, C, D, G, L. I define the non-terminal states and terminal states and the actions. And then the transition probabilities are actually deterministic, as I said. And here, I mean, since we want the code to be generic, then actions that are not explicitly leading to other states are assumed to keep the agent in the current state. But I mean, this is really just an implementation detail. The transitions are defined in the same way that we said. So from A, you could only go to B, right? From A, you could only go to B. From B, you could go to D or A or C. So I mean, based on the action. So if I am at B and went up, I will go to D. If I am at B and I went left, I go to A, and so on. So those are the transition probabilities, and they are assumed to be deterministic here. Okay. And then if I didn't find anything, I'll just keep in the current state. But this is an implementation detail, just to make the code generic a little bit. And also for the rewards are what I said, like if you are C and go up, you end up in the red region. If you are D and go right, you end up in the red region as well. And C and down is the only, winning state action pair in a way. And then the policy again is defined similar to what I had. So A deterministically goes only right, but for B you could go either left or right or up, and for C you could either go left or down or up, and for D you could either go right or down. Again, this is the exact same thing. And then what we do is really just define gamma and define some iterations. We initialize V with the 0 in all states, and then we run this policy evaluation loop, and you could see that there are two loops. One is just for some max iterations, and then you always have a copy of the previous iterations values, since we are synchronous in this implementation. And then we really just apply the Bellman equation in the same way that I described. What I want to show you is and then there is a stop or a convergence condition. Like, you try to find the difference between V old and V new, and if the difference between the arrays at one iteration and the following iteration is really very, very small, then you say, you know what, maybe this is good convergence, and I converged. So let's actually see what happens if we run this. And we see that we converge after 62 iterations. So if I kept doing this, I would have needed to do it 62 times. To reach the numbers within the tolerance that we want. But actually, let's look at the first two iterations. So at iteration 0, we initialize all zeros. At iteration 1, yes, D is -5, which is the same thing we found out here. And then at iteration 2, you get -5 for D, and you get -1.6, which is really -5/3, I hope. Right? So -5/3, this is roughly, I think it's correct. So this was the algorithm. In the next lecture, I'll actually prove that this really works for any generic case. So in previous lectures, I introduced an algorithm for iterative policy evaluation, and I claimed that if you reapply the Bellman expectation equation over and over and over again, you will eventually converge into the true value function under a specific policy, right? And I also showed a numeric example, and it really converged, and you could very easily confirm that this is the correct solution by plugging the numbers we got at iteration 1262 into the Bellman equation, and you could see that they are really self-consistent, because otherwise you would have found a different number or different numbers at iteration 63. So the fact that you got a very small difference between iteration 62 and 63 really shows that this is already this already satisfies the Bellman expectation equation. But I also introduced some intuition on why this might make sense. Why does this work intuitively, using this idea of if you have, terminal states with really large value and then other states with maybe really low value, then those large rewards from the environment will start propagating first to those states closer to the terminal state, and then they will start propagating through the veins of the system or of the MDB until everything eventually works out. But this wasn't really a proof. I would like to provide a real proof, and this is, I think it is important, but you can feel free to skip it if you don't like proofs. But I think it is important because the ideas you will cover in this proof will first show up in subsequent proofs, but it is also mentioned, often, even in recent papers, because even if you work on complex real-world examples where you are not, tabular and you don't have those small discrete states and actions, you still try to get, closer or as close as possible to this idealistic case. And so some of the ideas in this proof, you will hear them quite often, even, when you work with real-world large problems and you have neural networks and everything. Okay, but I suggest you at least view the proof once. It is not a simple proof. It will take multiple lectures actually, but I think it's worth it to view it at least once. So the proof will be mainly two parts. One part of it is called the Banach fixed point theorem. So this is an important theorem, and I will actually prove this theorem itself. And then we will use this theorem in reinforcement learning to prove that the iterative implementation or iterative substitution into the Bellman expectation equation actually leads to the correct solution, right? So let's try to give a high-level overview in this lecture of the Banach fixed point theorem, and then I'll prove it later on, okay? So there are some terms in this theorem. This is just from Wikipedia. So this talks about something called a metric space, and it also talks about something called contraction mapping. So let's try to define those terms first. So a metric space you could define as some space where you could define a function that represents the distance. You can define a distance, and the distance has properties that the distance between x and y must be equal to the distance between y and x. Otherwise, this is not called a distance. It needs to be symmetric, and the distance should be greater than or equal to 0. It can't be negative, right? And the only case where the distance is exactly equal to 0 is if the two terms are the same. So this is the definition of a distance function. Now you could think of multiple spaces where you can define this as function. So for example, you could think about the space of, integer numbers, right? So if you have 1, 2, 3, the distance is just, the subtraction, but you need to put a modulus or absolute value because you want the distance between 1 and 2 to be equal to the distance between 2 and 1. So this is a valid space that is also, that's a valid metric space, I mean. But you could also talk about something like, the Cartesian 2D or 3D or 4D space, and then your inputs here are maybe points, so maybe point 1 and point 2, right? And the distance is just the Euclidean distance, even in dimensions, right? So those are some examples, but you could also have different spaces if you want, different metric spaces, and actually in reinforcement learning, the space will be a little bit different, but I'll cover this later. So this is the definition of a metric space. It is a space where you can define a distance function. Okay, now there is this concept of a contraction mapping. So the Wikipedia page says here that a contraction mapping exists if the distance between this is less than or equal q multiplied the distance of this. So let's try to give an intuition first. It really says a contraction mapping is just a mapping, a function, that takes as input one element of this space, okay, and produces another element in the same space. So it doesn't move you to a completely different space or anything, right? So you take, for example, a 2D point and you still get a 2D point, not something different. So that's why we say it needs to, point to itself in a way. So you apply a function to this point, so you get another function, maybe this, you get another point, sorry, maybe this one. So this is called T of P1. And you could also apply the same mapping, the same function to P2, and you get another point, T of P2. And the definition of a contraction mapping is the distance between the original points here must be less than the distance between the resulting points. So this is really the definition, but it is a little bit more stronger guarantee than this, because it says that the distance between the resulting points must be at most equal to q multiplied by the original distance, for q being a value between 0 and 1. So it's not just smaller, but it must be at most equal to q multiplied by the distance. So this is the definition of the contraction mapping. So let's look at some examples of this contraction mapping. I mean, we could have a fun example, like, if you have a map of the world, so let's say something like maybe this, then you have some, states here, something like this. And then maybe I could just take this and shrink it down a bit. So if I do this, I get, I'll try to put it exactly on top. I don't know, but if you shrink this down a bit, you will get a similar version, but the distances between all the countries are, smaller. Another example for a contraction mapping could be, a simple function that says f of x is equal to just half of x, right? Half multiplied by x. So if you have 2 points x and y, the distance of between f of x and f of y is really equal to the distance between 0.5x and 0.5 y, which is the absolute value of 0.5x minus 0.5 y, which is equal to 0.5, the absolute value of x minus y. But this one here is the distance between x and y. So distance between x and y. So here the distance after the contraction is at most equal to 0.5, the distance before the contraction. It's always equal to this, but now it really satisfies the equation, or satisfies the definition of a contraction mapping. So let's actually go back to the theorem right here. And the theorem goes on and says, if you have a metric space that is complete, and I'll talk about complete later in the formal proof, but it's really just a metric space now, and with the contraction mapping, then the theorem claims that there exists at most one value, okay, or exactly one value in the space where if you apply the contraction mapping to it, it doesn't change. So this is the claim of this theorem. It claims that there always exists a value that if you apply the contraction mapping on it, it doesn't change. So it proves the existence always. And it also proves the uniqueness, that there's exactly one value that satisfies this equation. You can't have two solutions. You can't have two values that do not change under the contraction. Okay? So this is the claim of the Banach theorem, and we'll use this claim a lot. It also gives you a way to find this specific value. It says, you know what, you could start with any arbitrary value, x node, and just apply the contraction multiple times. Like say, apply it to get x1, and then apply it again over x1 to get x2, then apply it again over x2 to get x3, and so on. And it claims that if you keep doing this, infinitely many times, or a lot of times, you will eventually get to x star. And this is what it says here. So as n grows to infinity, then you will get to x star. So this is what the Banach fixed point theorem claims, and I will actually prove this theorem in one of the later lectures. But let me give you an overview of why we need this theorem, or why it matters to us. Like, we will be able to prove in the next lecture actually that the Bellman operator or the Bellman expectation operator is really a contraction mapping over the space of value functions. Like, let me clarify this. It's a little bit weird, but you could think about this equation right here, right? This equation, if you apply it like iteratively, like it takes as input one value function, right? And produces another value function. So the input is the entire value function or the entire function, right? It's not a single number. And if we look at this iterative, maybe version of it, it might become clearer. Like for this algorithm, the input to the Bellman expectation operator is the value function at the previous time step, and then the output is the value function at the next time step. So it really maps a value function, an entire function, into another entire function, if this makes sense. Like, let me clarify this a little bit more. Like, suppose you have a single continuous state, like it is, you know, continuous state for this example, right? Or maybe even discrete, and you have different values for the state, but let's even say it's continuous. Then you have maybe an initial value function here, right? And the Bellman operator takes this value function, in this entire value function that is defined over this entire, you know, line here or number line here, and converts it or maps it at the next iteration to another function. And at the following, so this is vk, maybe this is vk plus 1, maybe this is vk plus 2, and so on. So the Bellman operator takes a function and converts it into another function or maps it into another function. And we will be able to prove that the Bellman expectation operator is actually a contraction mapping over this space. And we will define also what is the distance we use in this space. But the nice thing is, once you make that proof, then it really proves that you could start with any arbitrary value function or curve in this example, and you keep applying the Bellman expectation operator over and over and over again, and you are guaranteed to reach some value function that doesn't change anymore under the contraction. This is this result. So you will eventually reach something that doesn't change under the contraction. But if you reach something that doesn't change under the contraction, then this is really the solution to the Bellman expectation equation, right? Because now you don't change anymore. And also the theorem here guarantees that you will find it, right? This is a guarantee. It also guarantees that it is unique. Like there are no two solutions to the value function, right? So this is on a high level why we care about this theorem. But I think if you are not fully aware of this, or like you don't understand this fully, it will become clearer in the next lecture when I try to prove that the Bellman expectation operator is on itself a contraction mapping over the space of value functions. And then later on I'll also prove this theorem itself so that you get completely 100% satisfied. Okay, so I think this was an enough high-level introduction. So see you in the next lecture. So in this lecture, I'm going to prove that the Bellman expectation operator is a contraction mapping. And by the Bellman expectation operator, I really mean just applying this, you know, function here or this equation here to all the states. Like we map all the states to all the states. That's the entire mapping. Or we map the function itself to another function after we apply this to all the states, right? Like I showed this in a previous lecture, but I'm gonna show it like again. So suppose you have, you know, some continuous or discrete states. It doesn't matter, but let's talk discrete this time. In the previous lecture, I showed it like to be continuous, but it really doesn't matter, except that for continuous case, you might need to change the summation into an integration, but the proof still holds actually. But suppose you have, you know, some states, S0, S1, S2, S3, S4, for example, and everyone has some value. So maybe here this has this value, this is value, this value. It doesn't have to be like a correct value. I'm just saying some function, really, some function, some discrete function. And we call those ones the first function. So it's just a function of S, and I call it Vx, right? And then maybe with another color, I draw another function, maybe like this, and like this, and let's say like this and like this. So this yellow one, you could call it Vy of S. It's another arbitrary function of S. What I'm trying to say is the Bellman operator takes one function and maps it to another function, right? So the elements of the metric space we are gonna work with for this derivation are really functions, not elements, right? You map an entire function to another function. I really think that, you know, connecting those into some sort of continuous function makes it, you know, easier to visualize. So that's why I actually used a continuous function previously. So yeah, just bear with me. It is not really continuous, but just drawing it to make it clearer. So I really map this white function into this yellow function after applying the Bellman expectation operator, right? You are convinced of this, I hope. Okay, so this is the metric space, or that's the space we are defining. Now let's define the distance function, because we want a metric space. We want a complete metric space, but I will talk about this complete term in the next lecture. It wouldn't really matter that much because this is a complete metric space, but I'll talk about it like in more detail in the next lecture when I prove the Banach theorem itself. But in general, what is the distance between those two graphs? Those are graphs, and we want to calculate the distance between those two graphs. So we can define any distance we want that satisfies, you know, the distance properties, that the distance between the two functions is the same. It is a scalar. It is a scalar, that's important. And the distance is only equal to 0 if both graphs are the same. So we actually use what we call the, you know, max norm or the infinity norm, which is really the maximum distance between those two graphs. Like here you have this distance, for example, but here you have this distance. So you define this to be the distance, and this is called the max norm. So you can define it as the distance between, let's say, Vx of S and Vy of S as being equal to the max over all the states of the distance, or of Vx of S minus Vy of S, right? So we call this the infinity norm or the maximum norm or something like that. You could also see it written as, you know, the something like this, I think, something like this. So it is really the same, just the maximum distance between those two graphs. So this is, you know, the groundwork for our proof. And now we would like to really prove that this operator is a contraction mapping, meaning if you apply the Bellman operator to an arbitrary function or graph and also apply it to another graph, the distance between those two graphs after the application will be smaller, or a contraction will be smaller than the distance before the application, and at max it will be equal to some number between 0 and 1 multiplied by the original distance, right? This is what we said in the previous lecture. So now let's define our Bellman operator a little bit more formally. It is an operator that operates on value functions or on functions. So if you look at this equation right here, you could say that the operator is really this equation, like it operates on value functions and converts them into value functions, right? So you could say that the Bellman operator is, you could denote it something like this. It is an operator that operates on value functions, and for this equation you only look at one specific state S, right? But really the full operator is, you know, if you apply this to all states, to all the states you have in your system, then you have the full operator somehow, right? But the operator, you could just write it as this, TV. So it's just a notation, doesn't mean anything. It's not a multiplication or anything. It's just that this is the operator, right? And this is the definition of the operator, or what the operator does for every one of those states. So to update the value of a state S, you use the values of you know, all states in the previous iteration or something, right? So in a way, this is the Bellman operator for one state. And the goal that we want to prove is really that if you apply the Bellman operator to one function, let's call it Vx, okay? And then apply it also to another function, let's call Vy, another complete function, another graph. So you are operating on graphs, okay? So you apply the Bellman operator on one graph to reach a result, and you apply the Bellman operator on another graph to achieve another result, or to reach another result or another graph. The distance here, that's what we need to prove. The distance after the application, right? It must be less than or equal some number multiplied by the distance between the original graphs. That's what we really need to prove. So we start with any two arbitrary graphs and we apply the Bellman operator, and then we calculate the distance, and we need to prove that no matter how those two graphs were, you always have this relationship satisfied. That's what we want to prove. Or in maybe the better or like the more concrete case of using the infinity norm, you would really need to prove that tvx minus tvy, the infinity norm, is less than or equal q multiplied by vx minus vy, the infinity norm. So let's start this derivation by looking at the distance between the two graphs at an arbitrary state S before and after the mapping, right? At an arbitrary state, like you have those two graphs. Let's look at any arbitrary like state, and we will prove first that for any arbitrary state, the distance between the two graphs decreases after the mapping, and then we will go from there. So let's start with an arbitrary state, not the highest distance state or not the smallest, just any arbitrary state. It will be a general proof. So the operator applied to an arbitrary state is really this equation, right? So let's do that for two arbitrary graphs or two arbitrary functions. So let's say that tvx of s, I want the distance, so the distance here between tvx of s minus tvy of s, right? You could just substitute. So for tvx, you have summation over a by of a given s, and then for every action you have the immediate reward r of s and a, and then gamma multiplied by probability of reaching s prime given s and a multiplied by the value vx of s prime, right? So this is the first term, and I still have a distance, so let's just put it right here. Then minus another term, but we are still inside the distance. The term for tvy is summation over a by of a given s multiplied by r of s and a plus gamma summation over s prime p of s prime given s and a multiplied by vy of s prime, right? And then we are still inside the distance. But now a good thing here is this term r of s and a actually cancels out. It does not depend on the specific graph we are looking at. It is just the immediate reward, right? So it will simplify a little bit, and this is equal to, again, we have a distance, then summation over a by of a given s, and here multiplied by, you could take this as a common factor, so you have gamma summation over s prime p of s prime given s and a, right? Vx of s prime minus gamma summation over s prime p of s prime given s and a multiplied by vy of s prime. Okay, and all of that is still inside the distance. You can simplify this a little bit more actually. So let's put the distance summation over a by of a given s and then you have gamma summation over S prime, P of S prime given S and A, and then you just have this difference, Px of S prime minus Vy of S prime here, and then you still have this, and you still have the distance. Now here is an interesting fact, like this here is a difference between two quantities. This difference could be positive or negative, right? Like maybe at some point Vx is larger and so this is positive, and at another point maybe Vy is larger and so this becomes negative. So there is an interesting inequality called the triangle inequality, which really says that if you have the absolute value of the summation of some elements, this is guaranteed to be less than or equal the summation of the absolute values. I mean, it makes sense, right? Like if you have some values like -1, -2, 1, 2, and you sum them over, the sum of those is equal to 0 actually, and then you get the absolute value of 0, which is 0. But if you take the absolute value of each element independently, then you'll get 1 plus 2 plus 1 plus 2. So 0 is definitely less than this. So the right hand side, the absolute value of a summation, is always less than or equal the summation of absolute values. And we can use the exact same idea here, given that we know that all those terms, pi and gamma and this probability here are positive terms. So those are like positive weights of this term. But this term right here could be positive or negative, right? But everything else is really just positive term. And so given that, we can use the triangle inequality, and we can say that this here right here is less than or equal, and we can remove this, you know, distance up to the term that is not necessarily like positive, I would say. So you could say that this is less than or equal summation over all actions, pi of A given S, right, multiplied by gamma, and then this other summation, this is still a positive number, P of S prime given S and A, right? And then we can put the distance right here, Vx of S prime minus Vy of S prime. So we put the distance right here, right? Okay, now what can we do? If you look at this, this is the distance at an arbitrary state S prime, right? You still have those, you know, summations out here, but this is really the distance at an arbitrary state S prime. But the distance at an arbitrary state is definitely less than the distance at the state with the largest distance, right? Like if you look at the graph again, we now are working with an arbitrary state, maybe this one, but the distance here is definitely less than the distance here or equal to it if this is the state we are at arbitrarily, right? So we can really change this into the infinity norm that we talk about. So this is still less than or equal summation over A, and the reason we can substitute them is we have this less than or equal. So this one is again at least this less than or equal this one. So pi of A given S. Then you have gamma. We could also move gamma outside if you want. P of S prime given S and A. And then here we could just remove this and put Vx minus Vy, the infinity norm, right? And the nice thing about this is a constant. This is really a constant number. It's just the maximum distance in this graph right here. It doesn't change based on S prime or based on the action. It's just a constant number. So we can move this constant and this constant gamma outside those summations if we want, because this is just a constant, right? So this is really the same as, or maybe now this one is equal to something, but I'm just using less than or equal. I'm referring to the original value here. I'm referring to this still, okay? So you could put gamma, and you could put this here Vx minus Vy, the infinity norm, which are constants, and then you could have the summations y of a given s multiplied by another summation over s prime, b of s prime given s and a. But now if you look at this one, this is just a summation over s prime of this probability, and those probabilities must sum up to 1. So this term is 1, right? And once you have 1 here, you can move 1 outside of the summation, and then you also have the summation over the policy over all actions in a given state, and again this summation is 1. So in a way, we have kind of reached the conclusion that this term right here, this distance at an arbitrary state, is less than or equal gamma multiplied by this term, right? This is what we have proven so far, and this is still the distance at an arbitrary state. However, if this is the case for an arbitrary state, then it is also the case for the state with the maximum difference, which means we can actually convert this into tvx minus tvy at the infinity norm. So this distance is less than or equal gamma multiplied by this distance right here, which is really what we wanted to prove. So this is the distance between tvx and tvy, or after the application of the operator, is less than or equal gamma multiplied by the distance of vx and vy, right? So this is really the proof. This is what we wanted. However, you need to make sure that gamma is less than 1. It can't be exactly 1 for this proof. Now, in reality, in reinforcement learning, if you have a gamma equal to 1 and you have, episodic tasks, it kind of still works. It kind of still converges if you apply this, Bellman expectation operator over time. But I'm just trying to say that the proof that we presented here works until gamma is, 0.999999, but not exactly 1, because if it is 1, you will not have a correct contraction mapping. Okay, so that's why actually we try to favor always using gamma less than 1 for those proofs to work. Okay, so now what we have proven is the Bellman expectation operator is a contraction mapping. Nice. And now by the Banach fixed point theorem, this guarantees to us that if we start with any arbitrary v node, any arbitrary value for this graph, any arbitrary graph, and we just keep inserting it into the expectation function or the expectation equation over and over and over again, we will eventually converge into a value where t of v is equal to v, and I don't want to use this, maybe not star here to avoid confusion with the optimal value. So a specific, value, we will reach a specific value where subsequent application of the expectation operation will not change anything, and the only way this could happen is if all the numbers are now self-consistent. So we will have reached a solution that satisfies the Bellman expectation operator or the Bellman expectation equations, and this will be the true value function. And the Banach fixed point theorem guarantees that we must reach this solution and that this is a unique solution as well, right? So this is really what we wanted to prove, and we proved it. In the next lecture, I will prove the Banach fixed point theorem itself. See you in the next one. So in this lecture, I'd like to prove the Banach fixed point theorem itself. Now, this might sound like a math lecture, not very relevant to reinforcement learning, so you might feel free to skip it if you want, if you trust Banach well enough. But I think it's actually interesting to see this proof, since a lot of reinforcement learning is really built on this idea of contraction mapping, and we will see this idea over and over again. So it might make sense for you to just be satisfied. Why did Banach say what he said, right? So Banach is still talking about this idea of a complete metric space. We defined what a metric space means. We didn't cover the word complete, and I think really for our purposes, we don't need to spend so much time on it. But let's just think of complete as being, you know what, if you have maybe this Cartesian 2D space, every part of the space is part of the space. Like every region here in this graph, for example, is allowed. You are not excluding this region and, you know, defining the space as everything except for this region, for example. So this is what is meant by complete. Like there are no elements here on this graph that are not allowed or that are not considered part of the space. I mean, it doesn't really matter that much for our case, since we are talking about the Bellman operator and we're talking about, you know, those graphs. And in our special case, all those graphs are like allowed. So we don't care about the case with incomplete spaces. This is really pure math. But yeah, like that's just for the sake of completeness. So now for our reinforcement learning, what are we trying to prove really? We would like to prove that if we have a space with a distance function and we have a valid contraction mapping, we need to prove that really if you keep applying this contraction function over and over again and get a sequence out of it, like you start with like x0, right? And then you apply the contraction mapping to get x1, then you apply it to get x2, x3, and so on, and then you get to xk in the middle, and then you get to xm, and so on. Keep applying this forever. You eventually reach, you know, a convergence. You eventually reach a point that doesn't change, which is called the fixed point. Like more visually, if you have again the 2D space, you start with some point, you apply the contraction mapping function, and you get another point, and another point, and another point, and so on. Like this is x0, x1, and so on. And then eventually you reach something in the limit at infinity that, you know, stops, and then you never move past this again, right? So this is what we're trying to prove really. And the way we will prove it is we will get a general like form equation for the distance between 2 points in this sequence here, and let's call those points xm and xk, right? With some distance between them. And we will prove that eventually in the limit, in the infinity limit, the distance between xm and xk will become exactly 0, right? Now, there is an important point I'd like to mention as well. Like sometimes you might have sequences where the distance between every 2 consecutive elements gets smaller and smaller, but the sequence as a whole never converges, never reaches the point and stops updating. Like you could, you know, find something like this. You have the distance here gets smaller and smaller and smaller and smaller and smaller, right? But it keeps moving forever. Like you at let's say at iteration 1 trillion you are here, right? And then at iteration 4 trillion you still move to be something here, even though the distance between every 2 consecutive elements gets, you know, smaller. It's like, you know, a snake or like a worm that is extremely slow and gets slower over time, but then it keeps running forever for trillions of years. And so eventually you could find a sequence where the distance between every 2 consecutive elements gets smaller, but if you give it enough time, you still get big distances between iteration 1 trillion and iteration 3 trillion, right? So in this case, this is not really convergent, even though it looks like it is convergent. And one example for those cases, you could look it up, I'll not cover it, but you could look at the harmonic series and the partial sum of harmonic series, like Sn, right? You could search for this and you will find out that the partial sum of harmonic sequences, like the harmonic sequence is really 1 over n, like you start with 1, then 1 over 2, then 1 over 3, 1 over 4, and so on until, you know, 1 over n, right? And then you could define something that is the partial sum, like partial sum of this series. So S1 is equal to 1. The partial sum S2 is the sum of 2 elements. So this is 1.5. then S3 is this one. So you kind of define a new sequence from the sequence, the partial sums. So S3 is 1 plus half plus 1/3 and so on. And you will see actually that the difference between every consecutive elements in the series gets smaller. So the distance here is 0.5, the distance here is 1/3, the distance between S3 and S4 is 1/4, and so on. So the distance between every consecutive elements gets actually smaller. However, this one never converges. This actually diverges to infinity. If you write S1, S2, S3, S4 until S, 1 trillion, S2 trillion, you will still be growing. So this is an example of what I'm saying here. But for our case, we want to prove that the distance between xm and xk for arbitrary m and k, where m is greater than k, under a contraction mapping, under the iterative application of the contraction mapping, the distance there will really be 0 in the limit, and not just between every element and the following one. Okay, so this is really what we are trying to prove in this lecture. So we want to prove three things. First, that the sequence converges, like the sequence converges, which is what I was really saying, right? Converges, right? So this is the first point. The second point we would like to prove is that it converges at the fixed point, which really means if you keep applying the contraction to the same point, you will get the same point. So I mean, it's kind of the same really. And then the third thing, we need to prove uniqueness. That no matter where you start, if you start with any arbitrary value, you will always reach the same unique solution. There are no two possible solutions to the same problem, right? Like if you start with any arbitrary initial value, you will anyway always reach the exact same solution. So this is really what we're trying to prove in this lecture. So let's actually start by defining our contraction mapping. So again, the contraction mapping means that the distance after the application, let's say of x, the application of the mapping function on x and y is less than or equal some q, or maybe some gamma in our case, the distance between the 2 points before the application. So we assume we already have a contraction mapping, and then we start from there. Okay, so let's start with x0. So we have x0, right? And then you apply it so that x1 is equal to t of x0. Okay, then the distance, and then x2 is, you apply this to x1. Okay, so now the distance between x2 and x1 is really equal to, it is the distance between t of x1 and t of x0. That's by definition. And again, by definition of the contraction mapping, this is less than or equal to gamma multiplied by the distance of x1 and x0, right? So this is clear. Now, if you do this again, the distance between x3 and x2 is the distance between t of x2 and t of x1, right? And this one is less than or equal, this one is less than or equal distance between x2 and x1, but multiplied by gamma, right? So this is less than or equal gamma multiplied by this one. But we already know that this one here is this one, and this is already less than or equal gamma multiplied by dx1 and x0. So in a way, you could also see that d of x3 and x2, it must be less than or equal gamma multiplied by this, which is also another gamma multiplied by dx1 x0. So gamma squared d of x1 and x0. Okay, nice. Now you could actually see that you could generalize this to whatever k you want. So the distance between any xk plus 1 and xk is gonna be less than or equal, you know, here this was a 2 and this was a 2, so now this is gamma bar k d of x1 and x0. So this is one important equation. It's not the final equation, but it is an important equation. So now this actually says that the distance between any two consecutive elements will be 0, because gamma here is assumed to be less than 1. So gamma bar 0, bar k as k goes to infinity is really 0. So the distance between two consecutive elements like tends to 0, or like gets close to 0, closer and closer to 0, as k goes to infinity. And this is very nice, but this is not enough to prove that we converged. Again, remember this equation here, this harmonic series here, or this partial sums for the harmonic series, the distance becomes smaller, but actually it can be proven that this series will diverge anyway, right? It will never stop. So what we really need to prove in order to show that this really converges is we want to find d of xm and xk, right, where m is greater than k. So in a way, we have some you know, sequences here, you know, in the space, right? And then at some point here you have maybe, so here you move to this one, and here you move to this one, then you move to this one, this one, this one, this one, this one, and so on. And you are looking at maybe this is m here, and maybe this is k here, right? Okay, maybe this is xk and this is xm. And you want to prove that the distance between xm and xk as k grows to infinity is also going to be 0. So this is what we're trying to do right now. So we want the distance between xm and xk. But now this is interesting because we have something called the triangle inequality. Again, we used it in the previous proof, but it really says that the direct distance between 2 points is the shortest one. So if you have point 1 and 2 and 3, then the distance between 3 and 1 is less than or equal the summation distance of 3 and 2 plus distance of 2 and 1, right? So this is the triangle inequality, and it also applies here. So in a way, this distance is less than or equal the distance between xk and xk plus 1, or like xk plus 1 and xk, plus the distance between xk plus 2 and xk plus 1, right? Plus the distance between xk plus 3, xk plus 2, and so on, until you get distance between xm and xm minus 1, right? So this is the triangle inequality, but every one of those we know how to calculate, right? Because we have it here, right? So let's actually do that. So d of xm and xk is less than or equal, so let's substitute everyone. So here we have gamma bar k multiplied by d x1 x0, and then here you have gamma bar k plus 1 multiplied by d x1 x0, and this again, this is gamma power k plus 2 multiplied by d x1 x0, until you get to here, which is gamma power m minus 1 d of x1 x0. Now we can take d of x1 x0 as a common factor, right? So here we have d of xm and xk is less than or equal d of x1 and x0 multiplied by something which is gamma power k plus gamma power k plus 1, and so on until gamma power m minus 1. Okay, and from this one we can take k as a common factor, or gamma power k as a common factor. So you could say gamma power k d of x1 x0, and then here you have 1 plus gamma squared plus plus gamma power m minus 1 minus k, right? But now we have this inequality, and this is a summation. So this summation is less than or equal the same summation applied until infinity instead of at until this point, right? So you could also say that this is less than or equal gamma power k multiplied by d x1 x0, and then here you have the summation until infinity, and actually you have a term for this. You know that the summation of 1 plus gamma squared until infinity is really equal to 1 over 1 minus gamma, right? So this is the geometric series. So this means that this distance is less than this one, and here you have 1 minus gamma. Okay, so this is the geometric series. You could look it up if you don't know this summation, but this summation is extremely important. We will face it over and over and over and over again in reinforcement learning throughout this course, and this is actually one of the main reasons why we insist on gamma being less than or equal to 1, because this definition that the summation converges to 1 over 1 minus gamma is only valid if gamma is less than 1. If gamma is exactly equal to 1, you get 1 over 0, and this really doesn't make sense. And if gamma is greater than 1, it doesn't make sense for the reinforcement learning formulation as well. So the interesting thing about this is if k tends to infinity, then this one will go to 0, and so this means that the distance will converge to 0. The distance between any two arbitrary points, if you start at a very large point or as k tends to infinity, will actually be 0, and this is enough proof that this converges. And this is called the Cauchy sequence. Cauchy sequence, like it is a sequence that converges like I described, but I mean you could ignore the naming convention. So this is again the reason why we talked about a complete space, because maybe in some other problem you could reach a point, at infinity you could reach a point that falls into this non-supported region or not allowed region, in which case, yes, the sequence looks like it converges, but it converges to something that is not really part of your space, and so that's why Banach, said this is only valid for a complete space. But maybe this is also a detail that we don't care about this much, because we have complete space in reinforcement learning. This is really the proof that any contraction mapping will lead to some series that actually converges. Now, we need to prove two more things. We need to prove that this is the fixed point, that if you apply again at this point, if you apply the contraction mapping, you will get the same point. So it is a fixed point, and then we will need to prove uniqueness as well. So now let's also prove that the point we converge to is the fixed point, meaning that if you apply the contraction mapping again, it doesn't change. I mean, it's really, you could actually convince yourself without proof or anything using this right here, that as k grows to infinity, this term is anyway 0, and so you stop changing. So I mean, this is valid, but people sometimes want to do something sometimes want to do it a little bit more formally, and so they say that what you want to prove is x star, which is the limit of xk as k is goes to infinity. They want to prove that if you apply t of x star, you get x star again in a little bit more formal way. It's not necessary, not strictly necessary, but let's also do it. And the way we do it is, let's look at xk plus 1, or the limit as k goes to infinity of the next term, which is equal to the limit as k goes to infinity. This is by definition t of xk, right? So those are two parts of an equation, two sides. If you look at this left side itself, you could make a substitution like q is equal to k plus 1. So left side is equal to limit q is equal to k plus 1, so you could just do this. And if k is infinity, then k plus 1 is necessarily also infinity. So q to infinity, and this is equal to x star by definition, right? It's the same equation here. And then the right hand side is more interesting because you have limit of a function of a value, and there are some cases where limit so this is k of a function of, you know, some number here is equal to the function applied to the limit right here, okay? And this is one of those cases. I'll show you why. But if you are satisfied that we can do this swapping in this specific case, then actually this one here is still x star. So this is t, and the thing inside the parentheses is like x star. And so this is the right hand side. So right side. So the right side is t of x star, the left side is x star. So you kind of proven that t of x star is equal to x star. You know, maybe it is too much of a proof, but yeah. So now let's talk why this is actually the case. You could swap the function and the limit if the function is continuous. And by continuous, we mean that, you know, you have those graphs and then you have a function. By continuous, we roughly and like informally mean that a small change in x, if this is x and this is y, a small change in x does not lead to an infinite change in y. Like you have, you know, this is the x and maybe this is the y. You know, I need to draw better, but really we say a function is continuous at a point if you change x by a little amount, y does not, you know, grow infinitely in a way. The dy by dx is not equal to infinity or negative infinity. It is still bounded. And this is for any continuous case. But every contraction is also continuous by, you know, it is even a stronger guarantee than being continuous, because you kind of guarantee that dy is less than dx, right? This is the definition of the contraction. You apply something to two numbers and then you get something that's smaller. So you actually, in a contraction, is even stronger guarantee for continuity than, you know, general continuity. So this is why you can do this swapping here. And this is because, you know, you could take the limit at a specific x first and then apply the function. Okay? Or you can apply the function first and then get the limit, and you will get the exact point either way, right? This is not necessarily the case for non-continuous functions where you could have a sudden jump and you have you know, x at x minus dx you have something, and then at x plus dx you have completely different things. So it matters the order. If you apply the limit to x first and then apply the function, could lead you to a different result than if you apply the function first and then get the limit on the other dimension, or on the vertical dimension in this case. But for continuous cases and also for contractions, it really doesn't matter the order where you apply the function first and then get the limit, or limit first and get the function. Okay, so this proves that this is a fixed point. Now the last thing we need to prove is the uniqueness. And this is actually important for us in reinforcement learning. And the proof for uniqueness is pretty simple. We will do a proof by contradiction. So let's assume first that there are multiple possible you know, fixed points. So we could say that there is x star, this is equal to t of x star, this is the first fixed point, and you also have y star, which is t of y star, right? So this is a proof by contradiction. If this is the case, then the distance between x star and y star is equal to the distance between t of x star and t of y star, right? But then this is really, by the contraction mapping, you know, definition, this is less than or equal to gamma multiplied by the distance of x and y star, right? So if you look at this one and this one, the distance is by definition positive. so you can divide by the distance without changing or flipping the equality or inequality signs. But this means if you divide this by this, you get 1, which means you get gamma is greater than or equal to 1. But now this is not possible because we already defined gamma to be exactly less than 1. So this means that we have a contradiction, and x star and y star must actually be the same point, and you can't have two different fixed points for the contraction mapping. Okay, so this was the proof for the Banach fixed point theorem. I hope it was clear enough. See you in the next lecture. So we managed to find an algorithm for policy evaluation through the iterative application of the Bellman expectation equation, and we proved that this actually works. It converges to a fixed point that is the correct true value function. But this is not really what we want eventually, right? We want to find the optimal policy, or if we know the environment dynamics, we at least want to know the optimal state value function, from which we could get the optimal action value functions, from which we could also get the optimal policy, right? So that's what we are trying to do really. And in this lecture, I will introduce an algorithm called value iteration that will allow us to find the optimal value function finally, at least for the cases where we know the environment dynamics and we are discrete and so on. But it is the first time we will be able to find the optimal value function and an optimal policy. Surprisingly, it will look very, very similar to the policy evaluation algorithm, in the sense that instead of we iteratively applying the Bellman expectation equation, we will instead iteratively apply the Bellman optimality equation for the state value function, and magically this will lead us to the optimal value, to the optimal state value function. Again, it might look weird. Why would this happen? And that's why we will prove it in the next lecture. And surprisingly, the proof is also going to be a contraction mapping proof. So we will prove that the Bellman optimality operator is also a contraction mapping. And this means that we can use the Banach fixed point theorem again, and it will prove to us that we will eventually reach a fixed point. If we start with any arbitrary value function, we will apply the Bellman optimality operator over and over again. We will reach a fixed point that will satisfy the Bellman optimality equation, and hence by definition it will be the optimal value function. Also the Banach fixed point theorem guarantees that this solution is unique, and this already is in line with what we know. The optimal value must be unique. Okay, so that's what we'll do in the next lecture. But in this lecture, I would like to again give some numerical example to really understand what's going on under the hood. So let's actually do that. I already prepared something, so let's talk about this scenario, this MDB, this world. You have a grid, you have A, B, C, D, F, E, H states, and then you have a losing state and a winning state. I still choose gamma to be equal to 1 for simplicity of the numeric calculations. And I define the rewards as follows. So I say that the reward of anything going into the losing state is going to be -1. The reward of anything going through the goal state or going to the goal state is equal to 10. So this is -10 and this is 10. And then for any other movement in the system, I still penalize unnecessary movement. Like if you move from any state to another, I just penalize you by -1. And this is interesting because this instructs the reinforcement learning algorithm to find the shortest path. Like I would like at the end of the learning to have, or at the end of the optimal policy finding, I would like the path to be from A to B to C to G. I don't want it to go A, B, C, E, F, E, C, G or something. I want it to choose the optimal path, which is the shortest path. And the way you really make sure it is the shortest path is by penalizing unnecessary movement. Okay? So here on the right, I also wrote the Bellman optimality equations again. So the optimal state value function is really a maximization over all actions that you take from any state. So there is of S here and of S here and of S here, I guess, and of S here. And then if you expand this Q value function, you get the immediate reward plus the discounted, next state value. And then you weight them, or you weigh them by the probability, the transition probability of the environment. But in our environment, we assume the transition probabilities are not random, like the environment doesn't throw you in places where you do not expect them. So that's why we could actually simplify gamma, put equal to 1, and also remove this probability and just use one next state. This is very similar to what I did in the policy evaluation numerical example, so I'm just moving through it very quickly. And then we say that for this value iteration algorithm, we convert this equation or this identity or this definition into an iterative update. So at step k plus 1, we really maximize over actions. Maximize over actions of this thing at iteration k. Like here you plug the value at iteration k, and then you get the value at iteration k plus 1. Or if you want to use this one right here, you say that vk plus 1 of s is equal to the maximization over a qk of s and a. Okay, so this is the iterative form of this algorithm. So let's try to implement it. So let's actually take those two equations with us. So let's copy them and paste them and just take them with us down here, because we will use them in our iterative application. Okay, so how do we do it? So we initialize a table, a value table with all zeros or any arbitrary initial value, and then that's the value at iteration 0. Now we would like to apply this equation for all states. But now there is something interesting. In order to apply those equations, you actually need for every state to find the action values for all the actions that are doable from the state first. And then after you do that, you need to take the one with the maximum value, and this will be the value of the state if you do this Bellman optimality operation. So let's see how this works. Like, let's start with state A. State A, you only have one action that is not illegal, which is go right. So you calculate Q of A and right, and this is Q at iteration 0, so K equals 0. And this value here is actually equal to R of S and A, which is -1, plus the value of the state you land in, which is B, which is 0, because you have 0 here. So this is -1. Now, since there is only one possible action from A, then we could say that V of A at iteration 1 is equal to -1. So this is the simple one. It will become clearer in the next ones. So now let's move to the next state, B. And for B, we have 3 legal actions. So we need to calculate Q0 of all of them. So Q0 of B and left is equal to the reward you get here, which is -1, plus the value of A, which is 0, so -1. Okay. Q0 of B and up is also going to be -1 in this first iteration, and Q0 of B and right is going to be -1, right? So now the maximum over them is like any one of them. So you could say that V1 of B is equal to -1. So, I mean, okay. This is for the next iteration. Now let's try out C. So for C, you need to calculate the Q for all directions, and C has 4 directions actually. So you need to calculate Q of C and left. Now you know this will already be -1, right? And then Q of C and right, this is also going to be -1. Now Q of C and down will be more interesting, because it's equal to the reward you get if you move down, which is 10 plus the value of G, and the value of G is always going to be 0. So Q of C and down is going to be 10, and similarly Q of C and up is actually going to be negative 10 since you move into the losing state, right? Okay, and then this means that, and this is Q0, so at iteration 0 if you want, and the V1 of C is going to be the maximum over all those, which is going to be 10. Okay, that's nice. I feel like I need to get those a little bit down in order for us to not keep going up and down. So let's just move them down a little bit. Probably need to move everything down, but let's try to squeeze it. So for D is this one. D has two actions, and the Q value of D and going down is gonna be -1, and here it's gonna be -10. So Q of D and down is gonna be -1. Q of D and right is gonna be -10, right? And so the value of D at iteration 1 is gonna be -1 because we take the maximum. Nice. Now for F, actually we could look at this one. Nice. Q of F and left is gonna be -10 at this iteration, and then Q of F and down is gonna be -1. So V of F is gonna be the maximum, which is -1, right? And then for H, Q of H and left is gonna be 10, and Q of H and up is gonna be -1. So the value of Q of H, sorry, gets high, and it is actually the maximum, which is 10. Okay, so I think this means we did everything. So let's fill in this one. So K equals 1, the value of G and L is always going to be 0. H is going to be 10 because it is close to this one. E is going to be -1. And what else? C is going to be 10. Right? And D is going to be -1. F is going to be -1 as well. So I mean everything is -1 except for two values that are 10, which is C is also is 10, and then B is -1, and A is -1. So we did the first iteration. Now we need to do the iteration again. So let's do that. I just moved stuff a little bit down, but let's do that. So for the next iteration, we do this again. So for K equals 2, you need again to calculate for state A, you need to find out Q of Q1 of A and going right. And this is equal to the immediate reward you get, which is -1, plus the value of B from the previous table, right? From K equals 1 table. And this is actually -1. So now you get -2. Right, you still have an immediate reward, and then you add the value of B, so now you get -2 now. Now for this means that the value of A is actually going to be -2 since you only have one thing. Now let's go for B and let's calculate Q of B and going left is equal to the immediate reward plus the value of A in the previous table, so it's gonna be -2 as well. But then you could also find out Q of B and up. This is equal to -1 plus the value of D. And the value of D is -1, so this is also -2. Then Q of B and C is, I guess, going to be interesting because it's -1 plus the value of C. And the value of C at the previous iteration is 10, so it's going to be 9. Okay, nice. Then this means that now the value of B is going to be 9 for the second iteration for K equals 2, which is nice. Now let's go for C itself. So C, I think you could be convinced that the value of C will remain as it is because you will try all those actions and then you'll find out that C is going to be, the value of C is going to be 10, so I don't want to waste your time. So, I mean, V3 of C is also gonna be 10. It is gonna be 10 forever actually, because this is the maximum you could ever get from C. And the same for H. So for h also, let's go a little bit faster. It is 2, so sorry, this is 2, not 3. But it's always going to be like this. So v2 of h is also going to be 10. It can't be bigger than this. Like this algorithm only will update the value if you could find some better action value function, really. So you can never change c and h in this example. But let's try f, and f as well. For f, we need to do a calculation actually. So for f, let's find q of f and down. This is gonna be -1 plus the value of e, and the value of e was -1, so it is -2, right? And for e, so here you say that v2 of f is going to be -2, and then for e you have this option, and this option, and you could already know that what will win is this option. So q of e and down is going to be -1 plus h plus the value of h, which is going to be 9. So v2 of e is going to be 9. So here at k equals 2, you could have e is equal to 9, h is going to be 10, c is going to be 10, and b is going to be 9 as well. But a is going to be -2, d is going to be -2, f is going to be -2, and those are zeros. I hope this is correct. I hope I didn't do any mistake, but I don't think so. So you could already see that the value from h is now propagating to e, right? And also the value of c is propagating to e, so that's why e is from both sides, it is 9. It has a value of 9. Now you could apply this another iteration, so let's do this. I know it's getting a little bit boring, but I think this will be the last iteration. So let's do the last iteration. So q is for a, q of a and right is going to be -1 plus the value of b from the previous iteration. So now it's going to be 8 actually. Now that's interesting. Now the value of a jumped suddenly from -2 to 8. Okay. The value of b will not change, and the value of c will not change. So this is v3. You could convince yourself that it will not change because this is the maximum you could get. So v3 of b is gonna remain at 9, and v3 of c is gonna remain at 10. Now for d, the value of d is going to be -1 plus b. So it will be 8, similar to the value of a. So nice, it will gonna be 8. And then the value of h is still gonna be 10. And the value of e will remain at 9. Of e will remain at 9, right? And the value of f, it will be equal to -1 plus the value of e, which was 9, so it will be also 8 this time. So now that's very interesting, and this is actually the final number, yes. So let's fill this at k equals 3. At k equals 3, the value of h is going to be 10, then those are zeros, then anything that reaches to h is gonna be h minus 1, so, or like 10 minus 1, so e is gonna be 9. And now anything connected to c is also gonna be 9, so c is gonna be 10, b is gonna be 9, d is gonna be 8, we calculated it, and a is also 8. Now f is connected to e, which is 9, now this is also gonna be 8. So this is actually the final value function. And you know it is the final because if you try applying the Bellman optimality equation again, you will actually find that those are the numbers you get. So you will find no update, you have converged, and it makes sense. I mean, intuitively, if I just asked you before doing all of this, put a value in every cell, those are the exact values you should put. Like anything that connects directly to the goal will have 10, and then anything that connects to this one will be like 9 and 8 and so on, because we have this penalty of -1. So This is the optimal value function, and we got it by just applying the Bellman optimality equation over and over again. Now, can we use this to get the optimal policy? The answer is yes, and that's because from the optimal value function, you can get the optimal action value function. From the optimal state value function, you can get the optimal action value functions, and from the optimal action value functions, you can get the optimal policy. So really, the equation that governs this is the Bellman optimality equation for action value function. So the optimal action value function here is really the immediate reward, right? And then the discounted summation over S prime, P of S prime given S and A, multiplied by the action, by the optimal state value function, right? And in our simplified case, this simplifies really to just the immediate reward plus V star of whatever state you get if you take this action from this state. And so you could actually find this optimal action for all state action pairs. So let's actually do this. For state A, for example, it's only one action. So the optimal policy of state A is just go right because there is no other action. So pi of go right given state A is going to be 100% because no other actions actually exist. But now for state B, you could either go left or up or right? And then you could say that Q of B and up is, for example, -1 plus the value of D, and the value of D is 8, so it's going to be 7, while Q star of B and going right is better because it's -1 plus the value of C, so it's going to be 9. So 9 is better than 7, and obviously you should also calculate Q star of B and going left, which is equal -1 plus the value of A, which is also going to be 7. So the best action here is going to be 9, and hence you say that by of probability of right given B should be 1. This is the optimal policy at B, okay? And this is also the optimal policy at A. And you can do the same for like C, obviously the optimal policy is to go down. For H, the optimal policy is to go like this. And note that this is always a deterministic policy in this case. For F, the optimal policy is definitely to go like down because you don't want to go here. For E, the optimal policy you could either go left or down. That's because let's calculate it for D. So Q star of E and down is going to be -1 plus the value of H, which is going to be 9, and the optimal value for E and left is also going to be -1 plus the value of C, which is also going to be 9. So now you have a tie, and whenever you have a tie, you could do whatever you want really. So you could define the greedy policy to be just go down or just go left, or you could have a stochastic policy that is 30% down and 70% left. It doesn't really matter. So by this you could actually define the optimal policy for all those states, and if we wanted to do this, we could just draw it here like this, and yeah, I'll just draw it for the sake of completeness, and then we will move on with our lives. So the optimal policy here is this, here it is this, here it's really anything out of those two. Here it is down, here it's also down. At B you should go here, and at A you should go here. So we could find the optimal policy successfully. In the next lecture I will prove that the Bellman optimality equation is a contraction mapping, which is the reason why this algorithm works. So in this lecture, I'm going to prove that the value iteration algorithm that I introduced actually works. So I will prove this by proving that the Bellman optimality operator is a contraction mapping. Now in this one, I'll go a little bit quicker because I assume you already saw the previous proof that the Bellman expectation operator is a contraction mapping. This one's pretty similar, so I'm not gonna redefine everything from scratch. So this is the equation for the Bellman optimality equation, right? And now we can again define the Bellman optimality operator now as an operator that works on functions. So again, it takes a graph or a function, a value function, and maps it into another value function. And we will define this for a specific state S to be equal to this thing right here. So max over A of R and S and A plus the discounted next step optimal value. I put a prime here by mistake. I'll just remove it. So something like this. Okay, so this is this operator applied to one state, but the full operator is really applied to the entire graph or the entire vector of states if you have, you know, discrete states. Okay. Again, we define the distance in this example or in this proof to be the max norm distance, okay, or the infinity norm distance, which is really, again, if you have those value function graphs, and so you have this graph and maybe this graph, you define the distance between the graphs as the maximum distance that could ever happen. So maybe not this one, maybe it's actually right here. This is the maximum distance. So roughly, this is what we did before. That's why I'm moving very quickly here. Now, our goal is again to prove that this operator right here is a contraction, meaning that we want to prove that if you have two different graphs or two different value functions, then if you take, you know, the infinity norm over all the states minus tvy infinity, you want to prove that this is less than or equal gamma multiplied by the distance of the original graphs. You know, so that's what we want to prove under the mapping that is this equation. So let's start our proof by applying the operator on a specific state, and then we will generalize or like apply it on an arbitrary state. So what we really want to look at now is the distance between the operator applied on the first graph at specific state minus the operator applied on the second graph but at a specific state. So this is really the vertical distance after the graphs are transformed, and we want this distance. So let's see how we write it. So this is the distance between the subtraction of two terms. The first term is this one, right? So I could maybe take it because this is now the operator. It has the max embedded in it. So I have this term, but I need here to say that this is actually Vx because we start with arbitrary value functions. We do not start with the optimal value function or anything. So you have the distance, and then let's actually remove this one because we need another subtraction here, and then we need something like this again, and here we just need to change this to be y, right? So this is the distance. So we want this distance. It is a max minus a max, but we have an interesting thing called the max inequality, which really says that the absolute value or the distance, let's say the absolute value of max over, let's say I, AI, minus max over I, BI, this is less than or equal to max I over the absolute difference. So this is called the max inequality. We could look at an example for it. So suppose you have, you know, a set A that has three numbers. Here both sets need to have the exact same number of elements. So let's say you have like 10 and 0 and maybe 20, okay? And let's say that B is another set that is maybe -10, 0, -20. So if you calculate the absolute value of max of AI minus max of BI, then you like first here you get max of AI is 20 minus max of BI is actually -10, So this is the, or 0 actually, it is 0. So you get here 20. While the second part here, you take the difference first. So for the second part, like diff is another set, which is 10 minus 10, which is 20. 0 minus 0 is 0, and then this one is 40. And then you get the maximum of this, of the absolute of the diff, and this will be actually 40, right? So the maximum of the absolute of the diff is gonna be larger than or equal the absolute value of the difference between the maxes. So this is called the maximum inequality, and we would like to use it here. So let's again copy this and go down here. So we can say that this value that we want, minus tby of s, this distance at an arbitrary state, is actually less than or equal the max over a, and we can move the distance or the absolute term here to be inside, and now you have r of s and a plus this minus r of s and a plus this, so r of s and a will cancel out, and then you will have gamma summation over s prime. So here you have s prime, b of s prime given s and a again, and here you will have vx of s prime minus vy of s prime. Okay, so this is a nice trick. Now this is really the distance, and similar to what we did in the previous proof, since gamma is a positive number and since this is also a positive number, then we can move the distance operator inside, and that's because this term right here, it is, you know, the vertical distance at different like s prime states, and this could be sometimes positive, sometimes negative, right? You could have a graph like this, maybe something like this and something like this. So sometimes you are positive, sometimes you are negative, but this value is definitely less than or equal to the case if you take the absolute distance for all those cases. Like maybe here you have a distance of 10 and a negative distance of negative 10. So if you take the difference, those will cancel out, maybe, right? Because you sum over those differences. But if you sum over the absolute distances, then this value will be larger than if you sum over the distances directly. And here we have a less than or equal operator, so we don't mind if we increase this value. So this is why we can say that this is less than or equal the maximum over a, and then you still have gamma and the summation b of s prime, s and a, right? But you could move the distance operator inner, and then you have this thing here, right? And now this one is again, this is the distance at specific state s prime, but again this is less than or equal the maximum norm, right? Because now you have those, maybe I could put something like this. So this is a graph and this is a graph. Here we are at a specific s prime, so maybe the distance here is something, but this something is definitely less than the maximum norm, which is a distance at the state that has a maximum difference. So you can change this into a constant, and that's what we are trying to do. So you could say that Vx of s minus t Vy of s as a distance is less than or equal, again, max over a, and then gamma, this summation, multiplied by the infinity norm. Now, since this distance is a constant and gamma is a constant, you can actually move them outside of the max operator because they don't depend on the action. So this term here is still less than or equal. You could move gamma outside and then maybe move Vx minus Vy. This is a constant now outside. And then you have max over a of this summation, right? And this summation is equal to 1, and the max over a of 1 is just 1. So you could actually now say that this is less than or equal to gamma Vx minus Vy, the infinity norm, right? Now again, similar to what we did in the expectation proof, this here says that the distance between any arbitrary two states is always less than or equal to this quantity. But this means that if we could find the state that has the maximum distance, it's still the same relationship must still apply, because it applies to all states, which means that we get what we want really. So Tvx minus Tvy, the infinity norm, is less than or equal to gamma Vx minus Vy, and this actually proves that this mapping right here is a contraction mapping, and this is what we want, right? This is really what we want, because now given the Banach fixed bane theorem, we could say that if we keep applying the Bellman optimality operator over and over and over again, we will eventually converge to something. We are guaranteed to eventually converge to something, and this something will not change anymore, which means it will actually satisfy the Bellman optimality equation, which means it is really the optimal value function. And we also know from the Banach fixed bane theorem that this is a unique solution. Okay, so by this we actually have proven why value iteration algorithm works. So we covered one algorithm to get the optimal value function and optimal policy, and this one was called value iteration. Now we will cover another algorithm. It is called policy iteration, and it is another algorithm to get the optimal value function and optimal policy as well. So think of it as an alternative, although later on we will actually find some connection between the two that will let us believe that value iteration is kind of a special case of policy iteration, but we will do that later. So as usual, I'll just introduce the algorithm now, and then I will prove actually why it works, why this is true. And this algorithm is interesting because the same idea we cover for this algorithm, we will face over and over and over again throughout the course. So it's really a fundamental algorithm. So the algorithm really is very simple. It's weirdly simple. It says, first, start with an arbitrary policy, like start with an arbitrary policy, okay? It could be like stochastic, it could be deterministic, it could be anything, like just a random policy, just some action for every state. And ideally, we actually start with a deterministic policy because it's just easier to calculate. And then evaluate this policy. Right, so the second step is evaluate it. So evaluate the policy, and you do the evaluation using the policy evaluation iterative algorithm, right? Where you keep using the Bellman expectation equation over and over and over again, and until you get changes below a specific tolerance you decide, and then you are satisfied. So you evaluate this policy. So when you evaluate the policy, you get V by, right? So you get V by, we are still using the state value functions, so you get V by. Now given V by, you could actually get the action value function as well for all the actions in every state, and then you can act greedily according to those actions to get a greedy policy. So the third step, we could say calculate action value function like Q by, and then choose another policy, let's call it pi 1, because here you could start with pi 0, right? Greedily, and we will see this using an example as well, with respect to Q pi. So you get, for every state, you get the Q value for all the actions in this state, and you just choose the action that maximizes Q, okay, or that has the most value, and then you repeat actually again. So using this, you evaluate the new policy again and calculate Q pi again, and then choose pi 2, and so on. So maybe you could just have pi I or something. I'm not writing it in a perfect way, but you get the idea. So you choose an arbitrary policy, you evaluate it, which means you get the state value function according to this policy via the iterative implementation or the iterative calculation of the Bellman expectation equation, right? And this could be, you know, this is in itself a loop. And then you converge, you get vpi, and then you act greedily according to qpi to get another policy. And then you evaluate it again and do this step again and then evaluate again and so on. So you could think of it as having two for loops, like it's a nested loop structure, where the first one, you know, loops over different policies, and the inner loop just does the Bellman expectation equation iterative algorithm for policy evaluation. Now, this actually looks a little bit more complex than the value iteration algorithm, and this is actually true because the value iteration was like, it kind of had a single loop in a way. This one has two loops, but this framework is really good to think of because we will keep using this framework over and over again, where we do policy evaluation followed by policy improvement, then policy evaluation, then policy improvement, and so on. So you will often find people visualizing this in a specific way. So let's just do it. It's really something like this. People do something like this. They draw two lines like this, and you could say that this is the value line and this is the policy line. So they just say start with any arbitrary policy and then do some steps to do policy evaluation, right? So you get vpi. And then after you get the policy, the value function, you actually change the policy. So you act greedily, so greedy. You act greedily with respect to Q, and then you do another policy evaluation, and then you act greedily again, another policy evaluation, and so on until you eventually reach a point here where the value function is optimal and the policy is also optimal. Now we are going to prove that if you keep doing those steps over and over again, you are actually guaranteed to reach an optimal policy and also an optimal value function. And this proof is not going to be a contraction mapping proof again, but contraction mapping will play a tiny part in this proof, but it will not be the main part of it. It's a different proof. I think it is a simpler proof actually. It's called the policy improvement theorem, and we will prove it later on. But for now, let's just have another, you know, numeric example, and then we will do the proof later on. So let's do a numeric example by hand, and this one will be a little bit long. So you can feel free to skip this entire lecture if you don't like those examples by hands, but I think it's very useful to at least do it once so that you are really sure you understand what's going on under the hood. Every step is actually crucial. So I suggest you keep like watching this lecture. So let's actually do the same example that we did before, the same grid world example. We did this using value iteration, and now we do it using policy iteration, which is a different algorithm. So we have the same states A, B, C, D, E, F, G, H, L, right? And we have those rewards. We still put gamma equals to 1 for simplicity. And we assume that our state transitions are deterministic, right? And this is why probability of S prime given S and A is assumed to be either 1 or 0. It can't take anything in between. The reward of just moving without going into L or G is -1, and this is the way we use to penalize longer unnecessary paths. Or you could also think of it as penalizing longer time steps if you want. So this algorithm is based on you start with any arbitrary policy, and then you do policy evaluation until convergence, which could take multiple steps using the same policy. And then once policy evaluation converges, you act greedily according to the action value functions, and then choose another policy, and then calculate the value function again, and so on. So it's a bit of a two-loop algorithm or nested loop algorithm. So again, we start with the Bellman expectation equation because now we want to do policy evaluation. But in our specific case, we will choose our policy, our initial policy, to be deterministic because we want to get rid of the summation and we can choose anything. So why not choose something that's simple for us? So let's start a deterministic. So let's try a deterministic policy that is actually very bad, but it's still deterministic. So maybe we do the most wrong things. So this is the policy we do. Here we can only move like this, but here we maybe choose something like this, and here let's also do something bad, and here let's do something bad. So we chose as by 0 the most horrible policy to choose. Okay. So what we need to do is to calculate now the value for all the states. So let's actually do that. And let's start v0 as the value is all 0. And here I have a slightly different, drawing for the value function table, but it's really the same. Instead of drawing it like as just one table, now I'm drawing it on the same shape as the world or the states, but it doesn't really matter. It's still the initial value. And we have vk plus 1 is equal to r of s and a plus v by of the next state in our simplified case, right? So let's try to do that according to our policy now. So let's say v1 of a, it's equal to -1 plus the value of this one, so it's really -1, right? And then v1 of b we move into d, so it is still -1 because the value of d is 0. But v1 of d is going to be the reward of going into L, which is -10 plus the value of a terminal state, which is always 0. Nice. And the VA of v1 of f is also equal to -10 for the same reason. And then v1 of c is also going to be -10 for the same reason according to this policy, right? So A, B, C, D, F, v1 of h is going to be -1, and v1 of c of e, sorry, is going to be, so e is -1. Okay, so in the next iteration you can actually take this as maybe no, so yeah, anyway, so v1 here, you have here -10, -10, -10, right? And the remaining are -1. I think this summarizes what we found. We have 3 -10s and the remaining is -1. But this is only the first step of policy evaluation. So we actually need to do another step. So let's copy our policy with us a little bit down, or maybe also this one, so that we don't lose track of where does each state exist. So let's actually do that. And now let's do it again. So v2 of state A is equal to the reward plus the value of B, and the value of B in the previous one is actually -1, so it is now -1, -1, it is -2. Now the value of B, I think it will be worse because now it is going to be under this policy -1, -10. So it's going to be -11 if I'm not mistaken. Then v2 of C, it is going to be the same, so -10. And v2 of D is also going to be the same, -10. And then v2 of E, again, it's -1 plus the value of this, so it's -11. So it's getting worse. And then maybe v2 of H, I think that's the one that's remaining, is equal to -1, -1, so it's -2, right? So A, B, C, D, E, H, and then we have v2 of F is gonna keep being negative 10. So this means we can go here. Sorry, this is not what I want, although it's fine, but I actually want this one, and I want it without any values inside of it, so that I could just say that this is v2. So let's just remove those, or maybe just actually keep this one, but remove the ones that change. So we said that a is going to be negative 2, this one was negative 11, this one negative 11, and this one negative 2, and this is v2. Now we need to do another step, right? So let's actually take those again with us down, and let's do a third step for policy evaluation. All of that is still under the first policy. So I mean, you could see that this is gonna be longer than the other ones, but let's actually try to do it until the end. So let's say now v3 of A is gonna be negative 1 plus the value of B. So now the value of B is actually negative 11 from the previous one, so it's gonna be negative 1, negative 11, it is negative 12. And then v3 of B, I think, is gonna be the same, so it's gonna be negative 11. And then v3 of C is gonna be the same, negative 10. v3 of D is gonna be the same, negative 10. And then of F is also gonna be negative 10. v3 of E is going to be negative 11, so I think this is actually the same. And then v3 of H is now going to be negative 1 plus the value of E, which is negative 11, so it's going to be negative 12. And I think this is it, and we can find out that this is it really by just doing another iteration, finding out that things didn't change. But I want to come here and copy one of those empty ones, but I think this is it actually. So here, this is v3, I think, for the first policy. So this is v3 of pi 0, so it's gonna be a long road but let's actually do it. So this is this one is negative 12, negative 11, negative 10, negative 10, negative 10, negative 11, negative 12. And I think this is actually the convergence, because if you try it one more time, none of the states will change value. So now you have done policy evaluation for pi 0. The next step is to calculate the action value function for all states under those numbers. Now remember that the value function actually of S and A, Q pi of S and A, is equal to the immediate reward. And in our case, again, we have we have deterministic state transitions, and we have gamma equals 1. So it will actually be R of S and A plus V pi of S prime of S and A. So it actually looks very similar to the definition of the state value function in this specific simplified case, which means that you could, if you want to do it like in an algorithmic way, you need to actually find Q of A and going like right, and this is going to be negative 1 plus the value here, so it's going to be negative 12, which is really the value of A. And then for other actions, I mean, in general, we try to allow every state to have all the actions. So in this specific problem definition, we can actually assume that if you try to take an illegal action, you still incur the reward, you still get a reward of negative 1. So in a way, I'm trying to say that Q of A and going left, you will still get negative 1 reward, but still end up in A, right? So this is at least the understanding here. So it's gonna be negative 13. That's what I'm trying to say. And similarly for all other actions that are not legal. So this is why any illegal action, actually you could just ignore it and not write it. But algorithmically you need to define it, so that the algorithm can work without trying to check for every state what are the allowed action. We generally would like to always have all the actions allowed in all states and control this either by the rewards or by the policy or something. But now you need to calculate the action value function for all allowed actions, because then you would like to act greedily according to them, right? So this is why you need to try everything else, and if you write this in code, you will try to do everything. But you could also now, so it is really clear to us that the greedy action for the state A is just to go right because it's the only action. So if we try to write here by 1, which is the next policy, here this is the only action really. Now let's look at state B right here. So you have 3 actions. Let's calculate the Q value function for B, and going, let's say, left, it will be -1, -12, which is -13. Obviously not so good. Q of B and going up is going to be -11. Not so good as well, but you'll find that also Q of B and going right is also the same. So Q of B and going right is also going to be -1, -10 is going to be -11. So it's really, no, those have tie and those are still better than this, so you could choose anything. So let's keep it as it was. I mean, it was like this and it actually stays like this in the new updated policy. So far the policy didn't really improve. It is the same so far. But now let's do the same for Q of state C, which is this one, C. And again, you can go left, right, up, or down. So this is the interesting part. You try for all the actions, not only for the actions, that are doable by the policy. And it's obviously gonna be go down, right? Like Q of C and down is really going to be 10. And obviously this will be the max, so I don't need to calculate the other ones. And so the updated policy will really do something like this. I mean, there's no other way, right? Now let's go for D. So again, D, you either go here and incur -10, or you go down and incur -1, -11, which is -12. So actually for D, it prefers to keep going into the losing state, which, sounds weird, but according to the algorithm, so far, this is still the best you could do, okay? Now for H, this state here, again, you try out those 2 actions. One of them will give you a value of 10 and the other will give you a value of -12. So here it will also still improve and go right in this direction. So this is another improvement in the policy that happened already. Now let's actually see this one. I think this was F, right? So for F, you are either gonna get -10, or again, it's similar to D, so it's still gonna do something like this. Now for this one here, which was E, for E, you could either get -11 here, or -11 here, or -13 if you go here. So you have a tie between this one and this one. So let's keep it like it was. Okay, so this is the first policy improvement step. Now what we need to do is to run policy evaluation again using this one, right? But we already see that this one is better than the previous one. So we seem to be moving in the right direction, but let's actually do it again. And really, I really understand that you might be very bored right now, but yeah, I mean, you could skip if you want. I mean, no one is forcing you to watch, but I would like to do another step at least for this algorithm, and maybe a third step to show you that it really works line by line. We could also use code, but I think there is a lot of intuition or a lot of delicate details that you might lose if you just say, okay, yeah, I understand the algorithm without actually doing it yourself. So I'm doing it for you, I guess. So let's actually do that again for another step. So we need to define an initial value for the state again. So we are working now with V0 again, right? So we re-enter the loop that calculates the policy value, or the value function, sorry. So we start with v0 again, and then we try to do policy evaluation. So we try to get, okay, now v1 of a, again, under this policy is going to be -1. So I mean, you always start with the same, I guess. And then v1 of b is going to be, under this policy, it is still -1, because -1 plus 0, right? And then v1 of c, this one is finally going to be a good thing. It's going to be 10, because under this policy it's 10. And then v1 of d is going to be -10, actually. And then v1 of e, under this policy, is going to be -1. And then v1 of f is going to be -10. And then v1 of h is going to be 10. So this one is actually better as well. So if we have something like this, I should have copied the one without any values, but you could really see now that the value of h, this one is going to be 10, this one is going to be 10, this is -10, this is -10. I think all the remaining are -1s. So this is the first step of policy evaluation. So we have 3 -1s. Yeah, sure, it sounds right. So let's do v2. So v2 of a is going to be -1 plus the value of this one, so it's going to be -2 again. v2 of b, we need to look at the policy, so b goes up, so it's going to be -11 again. And then v2 of c, it will keep at 10. v2 of d, it will keep at -10. v2 of b, c, d, e. So where is e actually? E is this one, so it's going to be -1 plus -10, so it's going to be -11 like b. And then v2 of f, which is this one, is going to be -10. And then v2 of h will remain at 10, right? So now we could go way up here and calculate one of those, or like copy one of those, sorry. And because we want to put v2 now, so let's do this. So v2 of b is -11. I think of a it was -2. This is -10. This is -10. This is 10. This is 10. This one was e, so it was -11. So is that right? I think it is right. I hope it is right. I mean, if I'm mistaken, I don't think I'm mistaken, right? I hope I'm not mistaken. So this is v2. Now let's actually copy those with us, because we don't want to keep going up and down. So this is still the policy we try to evaluate. And then I think we need to do a v3. So v3 of a, this is going to be -1, -11 is going to be -12. Then v3 of b, I think it's will remain the same, because -1, -10, right? v3 of c, it will be the same, 10. v3 of d is going to be -10. And this is v3 of e is this one, it's going to remain -11. v3 of f is going to be -10. And then v3 of h is going to be 10. And this is the final, again, iteration of value iteration. You could try another one and see that they will not change anymore. So I'm going to do the stupid thing again and just, you know, remove those things, because I forgot to copy the free one. And this is v3 of the second iteration. So this is v3 of by 1, really. And let's just put the numbers. So -12, -11, -10, -10. I think this was 10, this was 10, and this was -11. And this is really this converged, so policy evaluation converged. Now we need to do another step of greedy movement. So let's try to do it maybe more quickly this time. So I'm actually gonna go up here and still copy another one. So let's actually copy two because we might need more of them later on. So let's copy those two, and yeah, let's just put them here. And then let's do a policy improvement now, okay? So for every state, we again look at which path is the best, and let's see if any improvement happens this time. So now for this state, it will always remain down now, and this will always remain like this, right? But now this state here, if you look at it, you will find out that you can either move up and have a cost of -11, or here and -12, or here, which will be -1 plus 10 actually. So the Q value function of this state and going right is -1 plus 10. And this is 9. So it will actually decide to change its direction finally to go here. This one will keep going here because this is the only action. Now let's look at this one. This one is either -10 or -1, -11, which is -12. So it will still prefer going this way, unfortunately. This one here will choose again between going up and having -11, or going here and having a 9, or going here and having a 9. So it could go either way. It could choose either way. So let's actually just say we choose this at random. So this improved and this improved, right? This one here will choose between -10 and -12, and it will keep the same. So this is by 2, okay? So we have now done another policy improvement step, right? So now let's do the last one. I know I'm getting very boring now, but we could do the last one. And if you could think about it, that every one step in our specific example, every iteration actually improved one, layer around the one that improved the previous time, roughly. But I can't guarantee that this is what always happens for all problems and all policies and all dynamics. But this is really what happens. So you could really from now see that in the next iteration, those ones will improve as well. Like I think this is those are the only ones remaining actually. So let's do this for the third time. But this time let's do some hacks or tweaks. I mean, we always start with A, B, C, D, and so on, but in reality, we could choose where we start, and this is really, a different algorithm, but it's also proven to work. So you could start at any state you want, and if you know that one specific state is actually better to start with because it has more information, then you could start with it. It is not the standard policy evaluation now that we've proven to work under contraction mapping and so on. It's something different where you choose a state where you start the algorithm, and you also work not synchronously. So you don't look at the values in the previous table or in the previous iteration, but you really look at the values in the same table, in the same iteration, right? So let's actually show you how this works. It will be quicker, and let's actually do it. So let's start with V0 again, and let's initialize to 0. But now when I do policy evaluation, I will always refer to the same table. So maybe I could just update this one in place if you'd like. We could do this. We could do this if you want. So let's do that. Let's update in place. Let's start with the value of the ones that we know already. So this one and this one, like C and H. So we can say, let's just update this in place. The value of C under this policy is going to be here. It's going to be 10. And this one is going to be 10. Okay. Now the value of this one here, which was E, if I remember correctly, under this policy is going to be -1 plus the value of this one. But this is a completely new iteration. So if we are doing standard policy evaluation, we would say -1 plus 0. But now we are doing this asynchronous update, and we are doing everything in the same array, which is also valid, and there is a proof that it works, but I didn't cover this proof. I only covered the synchronous case, the contraction mapping one. But it is also proven that this could work, and it's much faster. So instead of doing -1 plus 0, we could just say -1 plus 10, and directly put here 9. So it will save some time for us. And then when you evaluate this one, actually this one is still unfortunately -10, because I mean it's looking left and we are evaluating this policy, so it's -10. And this one unfortunately is also -10, right? So this is -10. This one we are going here again. If we are doing synchronous value evaluation or policy evaluation, we would have said -1 + 0, so it's -1, and then in the next iteration we would update it. But now we could just say -1 + 10 directly. We are updating things in place, so this is now 9, right? And now this one is -1 + 9. It is gonna be 8. And I think that we have now finished this step. I think so. Like we could do another one to make sure that that the policy evaluation step converged after this asynchronous update. But I think we are already done. So this is 10 and this will never change. This is really 9 and this is -10, -10. This one is -1 plus this one and this one is, yeah. So I think this is actually fine. So we got it in maybe one iteration. And we used two things. We started from the most interesting states. That's the first thing we did. And we acted asynchronously. We didn't keep a copy. So now this is the value actually. And now we should act greedily according to this value. So if you look at this one, the action value function Q of this one I think was F of F and going down. Let's actually make sure that this is really F because I tend to forget. Yes, it is F. Of F and going down is now going to be -1 + 9. It's going to be 8, and the value of F and going left is going to be -10. So finally, this one will prefer going down, and the same will happen for D. So it's go down. This is gonna go here, and those will not change from the previous iteration. And finally, this is by 3, and also this is by star. How do I know that this is by star? I mean, you could just look at it and this is really the optimal policy, right? Everything now goes into the goal with the least amount of steps. But algorithmically, if you are implementing this as code, you'll actually need to do another iteration. You need to do another iteration of policy evaluation and then policy improvement and find out that by 4 is exactly equal to by 3. So the stopping condition for the policy iteration algorithm is you find two consecutive policies that are exactly the same, which means that now you're done. And in the proof that we will find, that we will show later, this actually is proven to be VPy. So there is a proof that says that once you do all those steps in a tabular case, then if you do this, you actually end up with pi star. Okay, this is the optimal policy. So in the next lecture, let's actually show this proof. So in this video, I'd like to prove why this policy iteration algorithm actually works. Why am I guaranteed that if I choose any arbitrary initial policy and then evaluate it and then act greedily according to or with respect to the action value functions that I get after the policy evaluation, I am guaranteed to get a better policy in the next iteration. And then I'm guaranteed to do this again and again and again until the algorithm converges. I also need to prove actually that once the algorithm converges, which means the policy doesn't change between one iteration to the next one, why is this guaranteed to be the optimal policy as well? Maybe it is just a local optimal or something, right? But this is not the case. It's actually guaranteed to be the optimal policy really, and this requires its own proof as well. So we would like to make this proof, so let's make some stuff concrete. So first, when we define the policy after the greedy step, really, we call this pi prime, and the definition of pi prime at a specific state is this is equal to argmax over all the actions of the q value functions according to the previous policy pi. So this is what we did in the numeric example, right? We evaluate the policy, we get vpi, and then from vpi and the environment dynamics, you can get qpi for all state and the action pairs, and then really the policy is just to deterministically choose the action that maximizes this quantity, right? So this is a definition of pi prime, and our goal in this proof is to prove that v pi prime of s is at least as good as v prime of s at all states. Now, I'd like to say that we consider a policy better than another policy if it is better even in one state, as long as in all the remaining states it's not worse. So it could be, it could have the same value for all states except for one, and for this one state it is strictly better, and if this is the case, then we say that the new policy is better than the old policy, right? It doesn't have to be better at all states, but it has to be not worse at all states, okay? So this is the goal. So this is the goal of the proof. So let's see how we will start this proof. So first, let's actually define vpi of s. Remember that for an arbitrary policy, this is something like this, right? So probability of taking this action, and then multiplied by the immediate reward, so r of s and a, and the discounted next state value, but you can't control the environment, so you have something like this, multiplied by vpi of s prime, right? So we did this a lot of times before. So this is the definition of vpi of s. Now let's compare this one to another term, which is q pi of s and pi prime of s, which really means you are at state s, you take the first action according to the greedy policy pi prime, and then for the next steps until the end of the episode, you keep using policy pi. So we want to expand this term and then compare those two terms. So this is really just the reward at state s if you take action pi prime s again, plus the discounted next state value still, and then probability of s prime given s, and here you have pi prime of s, this is your action, right, multiplied by the value of s prime according to the policy pi, not pi prime. So this is how we define this term right here, okay? Now it is actually clear that v pi of s is less than or equal to q pi of s and pi prime of s. And the reason is really simple, like this looks exactly like this one, right? But the first one, you get an average over values, and in the second one, you act greedily, so you are choosing the action that gets you the maximum value, and definitely the maximum of some numbers is better than the average of the same numbers. So this is really what's happening. This is kind of a weighted average, but this is just the maximum, and the maximum is always better than the weighted average, except for one case when they could be equal, if the maximum is already the weighted average. So I mean, in some cases it could be equal, and this will happen if this policy is, you know, the greedy policy, and you have pi equal to 1 at one specific action and like zeros otherwise, or maybe all the 4 actions, if you have 4 actions, maybe all the 4 actions have the same value and this is just some average. So in some cases it could happen that this is equal to this, but generally speaking, this value function, the state value function or state value, is less than or equal to this one, okay? So let's actually write that in the expanded form. So let's say that v pi of s is less than or equal the expanded form of this one, which is r of s and pi prime of s plus gamma summation over next states probability of s prime given s and pi prime of s multiplied by v pi of s prime. Now the interesting thing is this equation right here applies for all states, for any arbitrary state s. So it also applies for v pi of s prime if you want. And since this is an inequality right here, this is an inequality, we can replace this with anything that is bigger than it. So we can replace this term right here with anything that's bigger than it, which is really the corresponding Q term if we want. So we can do this, we are allowed to do this since we have an inequality, not an equality. So we can also say that V pi of S prime is equal to the reward, immediate reward starting from S prime. If you take the greedy action, so by prime of S prime plus gamma summation over S prime, it's double prime now because you have the next state to the next state, so S double prime, probability of reaching S double prime given you start at S prime and use the action, the greedy action at S prime, and then multiplied by the value of the S double prime state, right? And then you can also do the same for V pi of S double prime. This is the last one. I am not gonna do it to infinity, but I think it makes sense to do this. So V pi of S double prime is gonna be equal to the reward if you start at S double prime and take pi prime of S double prime, right? And then you have another gamma here, summation over S triple prime, unfortunately, P of S triple prime given S double prime and pi prime of S double prime, and then V pi of S triple prime, right? And you can do this forever up to infinity, but I just really want to extract a pattern here. It will look a little bit ugly at first, but it will simplify. So let's actually now do this substitution. Let's substitute this one into here and then substitute this one into whatever we will find out. It will be a long equation, apologies for that. So this is equal to, or like is now less than or equal to R of S pi prime of S plus gamma, and then you have this summation over S prime, probability of S prime given S and pi prime of S, and then here you need to put something, and this something is this one here, so R of S prime and pi prime of S prime plus gamma summation over S double prime, probability of S double prime given S prime and pi prime of S prime as an action, and then you multiply this by V pi of S double prime. Okay, so that's interesting, I think, but now we also need to change this one, but let's do some simplification first. So you can say that V pi of S is less than or equal R of S and pi prime of S, right? Plus gamma multiplied by this summation, so S prime, P of S prime given S pi prime of S, multiplied by the reward, so this is the reward at the next state or at S prime state, pi prime of S prime. Okay, and then you have gamma squared, so you have gamma squared multiplied by this probability, so you can have summation over S prime, and you could also have the other summation directly, S double prime, right? S prime given S pi prime of S multiplied by probability of S double prime, here this one given S prime and pi prime of S prime, and then you multiply by the value of S double prime. Okay, now we can expand this term, so let's actually paste this here and let's try to expand this term. But before doing this, let's take this, maybe make it here and maybe make it a little bit smaller, and then let's try to expand this term. So V pi of S double prime, we calculated it to be the reward, so it is really the reward if you are at S double prime, right? And you take the action V prime of S double prime, I think this is correct, plus another gamma summation over S triple prime, right? Probability of S triple prime given S double prime and pi of S double prime, right? Multiplied by V pi of S triple prime. right? So this is this value. So this means that we can do another, you know, simplification if we want, and we could say that v pi of s here is going to be equal or less than or equal this, and then you can get the gamma squared and have this term. Can do this. So you have plus gamma squared summation over s prime summation over s double prime, and then you have two probabilities. So p of s prime given s and by prime of s, right, multiplied by probability of s double prime given s prime and by prime of s prime, multiplied by this reward, which is really s of double reward of s double prime and by prime of s double prime. Okay, and then we have another term where we multiply this whole thing by this whole thing. So you start getting gamma cubed, and I think you see where this is going. So this is gamma cubed, and then you have this term multiplied by this term. So you have now three summations multiplied with each other. So maybe you have s prime summation over s double prime summation over s triple prime if you want, and then you have p of s prime given s and by prime of s, and then multiplied by p of s double prime given s prime and by prime of s prime, and then multiplied by p of s triple prime given s double prime and by prime, this is a prime here, of s double prime, right? And then multiplied by v pi of s triple prime. Okay, now I'd like you to have a better feeling of what this equation is trying to tell us. It is trying to tell us that the value of state s following policy pi is less than or equal to this huge quantity right here, but every term of those quantity has a very specific meaning. So this is really the reward at time t plus 1, or the next reward, if you start at state s and use policy pi prime. Okay, so this is really rt plus 1. Now this one becomes more interesting because now you have a probability multiplied by a value. So this is really an expectation, right? This is an expectation because you can't control the environment. So you have some randomness, because if you take action A, the environment can throw you anywhere. And so you have this expectation here, but it is still an expectation of the reward at time rt plus 2 or at time t plus 2, right? Now, if you look at the third term, it is yet another expectation as well, but it's an expectation of the reward at time t plus 3. And here you multiply it by two probabilities, but you sum over them, and that's why you have an expectation. What this is trying to tell you is really, you start at state s, then you use pi prime to go from s to s prime, then you use pi prime again to go from s prime to s double prime, and then you get some reward at time t plus 3, right? And the same happens here for the last term, although the last term has a value function. So let's actually look at the first three terms first. We can actually simplify this a little bit by converting those probabilities into a compact expectation notation. And the expectation would be over the trajectories that happen or that exist if you follow the policy pi prime for a couple of time steps. Here we only follow this policy for like 3 time steps, and then we estimate the rest of the value using the current value function. But really, you could say that v pi of s, if you want a compact notation, is less than or equal the expectation over all the trajectories that happen according to, or all the trajectories that you could get if you follow pi prime. So you can imagine that you are really trying out trillions of trajectories from state s, okay? Trillions of trajectories from state s, and you just record the reward at time t plus 1, and record the reward at time t plus 2, and t plus 3, and t plus 4, and so on. And for the first term, you just average the rewards at time t plus 1. For this second term, you really average all the rewards at time t plus 2. So you run a trillion trajectories, so you have trillion values of rt plus 2, you just average them. And if those trajectories are sampled according to the proper environment, then this average will actually be a good representation or a good estimate for this quantity right here. And similarly for RT plus 3, you have a trillion trajectories, you have a trillion RT plus 3, so you could just average them out. Just average them to get this value right here. Now, we don't have samples since we are model based and we know the environment dynamics, so this is why we calculated like mathematically, but I think this image of having trajectories and just averaging out could help sometimes. But at the end of the day, you could think of those three terms here as just an expectation of the rewards. So we could replace this here with RT plus 1. And note that I'm now using a capital letter R because this is a random variable, right? And it will become clearer here because I have gamma multiplied by RT plus 2. So I removed those probabilities because those probabilities, those environment dynamics, I assume are now embedded or included implicitly into this expectation, right? So this is the expectation over the environment dynamics if you follow, or the expectation that respects the environment dynamics if you follow by prime for your actions. So it's in a way this probability is now consumed here. And for the next term you have gamma squared, and again you could consume those probabilities into this expectation because it is still the same environment dynamics and the same policy. And then here you have RT plus 3, right? And don't forget that all those rewards assume that at time t you were at specific state S, right? So this is still a conditional expectation, right? Because at time t we start at state S, which is this S right here. Now this last term right here is another expectation, right? Because you have probabilities multiplied with each other, so this is just a probability, and then you sum over all the possibilities for S prime, S double prime, and S triple prime. So this is another expectation, and what it really means is, again, if at time t you start at state S, you follow by prime, you reach S prime. Then you follow by prime, you reach S double prime, and then you follow by prime, you reach S triple prime, and then you get a value. So again, you have a trillion trajectories, and then for every one of those trajectories, you reach a random state at time t plus 3 now. You get its value according to the policy pi, and then average all those. So this is really what this long equation is trying to tell you. So in a way, it is really plus gamma cubed, and it is still an expectation over pi prime. But here you need a value function, and you need a random variable because now you have an expectation. And this random variable is going to be S capital T plus 3, right? Because S triple prime is just an instance of this random variable if you want. And all of that should be conditional on ST being equal to S. So let's actually take this with me here. For space purposes, I need to have it conditional on ST is equal to S. Okay, so now this is, the complete inequality right here. Now, I'm pretty sure you can imagine that we can, instead of having 3 terms, we could have 2 terms, or 3, or 4, or 5, or 6, or k in general, before we come to this term that summarizes the rest somehow. So you could actually write the general formula, and we are pretty close to being done. So if you use k steps, or if you follow by prime for k steps arbitrary, then you have this expectation here, and then you have a summation. Let's say from I is equal to 0 until I is equal to k minus 1, maybe gamma or I, because we want the first one to be 1, and then you have RT plus I plus 1 given ST is equal to S, right? So then let's double check, like if you want 3 terms, then this will give us 3 terms, right? K is equal to 3, so from 0 to 2, and the last reward will be T plus I, which is T plus 2 plus 1, so it's correct, and gamma power 2, so it seems correct. And then the last here, so this is gonna be gamma power K, right? And then expectation over pi prime of V pi of ST plus K. Okay, so this is the general form, but now we actually can choose K to be equal to infinity. So we can take the limit. And the nice thing about this term right here, if is k is equal to infinity and gamma is guaranteed to be less than 1, this term will actually go to 0 since v by is bounded. We don't allow v by to be infinity because again we have this discount factor, so v by can't be infinity. So you multiply 0 by something that is not infinity. So at infinity, this term goes to 0. So if k goes to infinity, which you could do, then v pi of s is really less than or equal, this is expectation right here, so expected value over p pi prime, summation from I to 0 to I to infinity, because k is equal to infinity, hence k minus 1 is also infinity, gamma power I or t plus I plus 1 given st is equal to s, and this term is 0. But now, if you finally look at this one, this really says follow pi prime from start to end, from 0 to infinity, and accumulate the discounted rewards. And this is actually the definition of v pi prime of s. Okay? Like this is the definition of the value function. So we have proven in a very long way that if you act greedily according to pi prime, you get a value function that is either better than the previous one or exactly equal. So this is really the end of the very long proof. Now the last part remaining is for us to consider the equality case. I claim now that if those are equal for all states, then v is really v star, the optimal value function, and the policy is also pi star. So let's try to see why this is true. The proof is actually short. I mean, we started this whole proof by saying that in general the value of a specific state under policy pi is less than or equal to the maximum value over a q pi of s and a, right? This is what we started with. But now if this equality holds, then we have this for all states. And if this applies for all states, remember that this is actually the Bellman optimality equation that maps the state value function to the action value function. So this means that if this applies to all states, then the Bellman optimality equation is satisfied, okay? And we know from the contraction mapping proof that there is a unique value for the state value function that satisfies this one. This is through the Banach fixed point theorem that we already proven, right? So this is the only value that satisfies the Bellman optimality equation, which means that this must be the optimal value function, okay? So this is it for this proof. See you in the next lecture. So we introduced two different algorithms to reach the optimal policy and the optimal value function for an MDP. One of them was called the value iteration algorithm and the other was called the policy iteration algorithm. As a reminder, value iteration depended on the iterative substitution into the Bellman optimality equation, and policy iteration had two steps, where first you start with any arbitrary policy that could be deterministic or stochastic, but we prefer deterministic for simplicity. Then you do a policy evaluation step followed by a policy improvement step. The policy evaluation step is done via the iterative substitution into the Bellman expectation equations. And then the policy improvement step, you just act greedily with respect to the action value functions. Then you get another policy, do again another policy evaluation step, then another policy improvement step, and so on. Now, a natural question that might arise is, why would anyone choose to use policy iteration over value iteration? I mean, looking from a very high level, it seems that policy iteration has an extra loop, right? You loop over the different policies, and for every policy you do a policy evaluation which is also iterative in nature, right? While in value iteration you only have one of those, or you have one less loop. And of course, I'm ignoring the fact that in the algorithm itself, you still loop over all the states, and then for every state you loop over the next states. But I'm really speaking on a high level that this has kind of two loops and this has one, but in reality you have more loops. So why would anyone choose policy iteration? Doesn't it always converge like slower than value iteration? And the answer is, it is not that simple. Like, it really depends on the MDP, on the discount factor, on the number of states, number of action, and so on. And the reason is, while here we apply iteratively the Bellman optimality equation, and here the Bellman expectation equation until convergence, remember that the Bellman expectation equation is, at the end of the day, a system of linear equations, while the other one has this max operators, so it is really non-linear, so you can't compare their convergence time like apples to apples. And in fact, for policy iteration, for maybe smaller problems, you might even use the closed form solution, right? So the fact that this applies the Bellman equation iteratively until convergence, and this does the same, is not a strict sign on which one of them will take more time. It is not guaranteed that they will take the exact same time. Maybe this takes more, maybe that takes more. You can't guarantee this without knowing all the details and the specific problem at hand and so on. So what I'm trying to say is, it is possible that even that the policy iteration has those nested loops, it actually reaches the result faster. It is possible. And the intuition about this is, if we draw again this diagram we drew before for the policy iteration algorithm, where this is in a way the value line and this is the policy line. You start with any arbitrary policy, and then you do policy evaluation, and then you do policy improvement, and then another policy evaluation, and so on. It is theoretically possible that if you do policy evaluation to the end and then do this policy improvement step by acting like greedily with respect to the value function, and then do another policy evaluation later, that you get to a better point on this line quicker. Like, you could think of this acting greedily as improving the policy in a way that results in you reaching a better value estimation much quicker, even though in value iteration you are still moving here on this line, but you are moving a little bit slower. It is possible. It's not always the case, but it is theoretically possible. So you could think of this policy improvement step as being something like a portal that really moves you faster into a better place on in the value line, if you want. So this is roughly an intuition. Now, someone might still say, you know what, but you kind of proven that the Bellman optimality equation is a contraction mapping, and also the Bellman expectation equation is a contraction mapping, and they both have the same contraction constant, lambda, right? So doesn't this kind of mean that they will converge to the fixed point in the same number of time or number of iterations? Again, maybe, maybe not. The contraction constant kind of puts a lower limit on the amount of improvement that could happen. Like, if you have a contraction mapping constant or gamma of, let's say, 0.9, then you are guaranteed that at every application of the operator, the improvement is not going to be less than 10%. But it doesn't really put an upper limit on the improvement. So maybe, again, it is possible that policy iteration, you improve by more than 10%. It is actually possible. So it's not really a strong objection. However, I also need to emphasize that the other situation might also happen. You might have value iteration converge faster or better depending on the problem, especially for cases with maybe smaller number of states. So in general, you have those two different algorithms. One of them could work in some cases better, and one of them could work in another case better, or in other cases better. And this is a situation where engineers and researchers try to get the best of the two worlds. And this is why researchers actually decided to design like a hybrid algorithm that is a middle ground between value iteration and policy iteration, and this algorithm is called modified policy iteration. But in order to understand this algorithm and why it is really a middle ground between value iteration and policy iteration, we need to first understand the relationship between value iteration and policy iteration, and we will do that in the next video. So before we dive into the modified policy iteration algorithm, let us try to establish a connection between value iteration and policy iteration. So I'm now gonna make a claim that value iteration can be thought of as a special case of policy iteration. And here is how this goes. So my claim is, if you do policy iteration, but instead of doing the policy evaluation step until you converge to a valid policy, you can just do exactly one sweep of policy evaluation over all the states, so exactly one here, and then directly go into a policy improvement step, and then do another evaluation but only for one sweep. So by a sweep, I mean you pass through all the states and update every state once. One sweep, and then again act greedily and do another policy improvement step. Then do one sweep and then act greedily, and so on and so forth. And my claim is, if you do this, you will actually be doing something equivalent to value iteration. So let's see why this works. So to understand this, we need to write the equations maybe next to each other. So the equation for value iteration was really at iteration k plus 1, for a specific state, you update the value based on the maximization over all the actions of R of S and A plus gamma multiplied by this quantity, so probability of S prime given S and A, multiplied by the value at the previous iteration of the state S prime, right? So this is the Bellman optimality equation, but converted into an iterative form. This is the value iteration algorithm. Now let's see what happens for policy iteration if you run the policy evaluation only for one sweep. So the update rule for policy iteration for the policy evaluation step was something like this, right? Vk plus 1 of S. Here you have a specific policy you are evaluating, so you are really doing R of S and A, and here I'm assuming that this policy is like deterministic, not probabilistic, and this is why I'm not really summing over all the actions, right? So you have one greedy action still, and then you still have summation over S prime, probability of S prime given S and A, multiplied by the value at iteration k of S prime, right? So if you do this for exactly one sweep, and then you do policy improvement, then you get a new policy. You could call it maybe by new to avoid so much notation. So by new at a specific state, although you apply this for all states, you do one sweep, but then for any arbitrary state, the new policy is really defined to be the argmax over action. So it's really an action of this quantity right here, or of the Q value function, but the Q value function is really going to be this quantity right here. So you can write it again, maybe R of S and A plus summation over S prime, probability of S prime given S and A, and the value, right? So now you did this policy improvement, and then in the next iteration you are gonna do another policy evaluation step, right? So you could call it maybe V new as well to avoid too much notation of S. Is really an evaluation of the latest policy right here. But you chose this policy such that you choose the action that maximizes this quantity. So if you choose the action that maximizes this quantity, you really get the maximum of this quantity, right? I mean, this is just what happens. So you really get the maximum of this quantity over A, So R of S and A plus summation over S prime, probability of S prime given S and A, multiplied by Vk of S prime. So this is what really happens, and this equation is exactly this equation right here. So we kind of proven now that those two are equivalent if you do the policy evaluation step for one sweep, okay? But there is a little small thing that I need to say right here. In the numerical example I did for policy evaluation, or for policy iteration, sorry, whenever I started a new evaluation for a new policy, I set the values to 0, right? I reinitialized the state value table to all zeros, and this is valid, but it is not required. I could initialize it to anything, and I could really just leave it as the table that I got at the previous iteration. So I could leave it as it is without resetting it to 0, and in this case, in this specific case, we get this equivalence. If we always reset the table into zeros, we don't get this same equivalence between value iteration and policy iteration. So what I was trying to say now is that really policy iteration and value iteration, you could think of them as 2 points on a spectrum. Here you do the policy evaluation for only one step, so could call it k equals 1, one step, and at policy iteration you do it until convergence. So this convergence could be, you know, whatever number of steps, or until a specific tolerance is defined, or maybe you just run it for, you know, 10,000 steps, you know, whatever. So here this is k is large, let's call it maybe until convergence, so until convergence. And if this is guaranteed to converge, and we actually proven using the policy improvement theorem that this is guaranteed to give you the optimal policy and the optimal value function. And also we actually proven that using k equals 1, or the value iteration algorithm, is proven to also work and to reach the optimal policy and the optimal value function through the contraction mapping proof. Then it might not feel extremely weird to you that we could actually choose any arbitrary k we want. And this is what the modified policy iteration algorithm does. It really tells you, you know what, you don't need to only use one step. You don't need to wait until convergence. You could choose another k, like maybe k equals to 5 or 10 or 20 or whatever, depending on the problem. So this is really what the modified policy iteration algorithm tries to do. It tells you, I mean, let's draw this line here again. So it really tells you that you can start with any arbitrary policy, and this is the value line, this is the policy line, and then you do policy evaluation, but for k steps, maybe k equals anything, so k steps, and then do a greedy improvement. Then have a new policy, and then evaluate this policy for k steps, and then do an improvement, greedy, and so on, until you converge. And this algorithm also converges to the optimal policy and the optimal value function, although I will not prove it. So I did prove the two extremes. There is a proof also for this modified policy iteration algorithm, but I'm not going to cover it. But I hope that if you really understand the two extreme proofs, it doesn't make it very confusing that anything in between could also work. And this is called the modified policy iteration. And in reality, people prefer it because it's really a good mix between those two extremes, and it really gets good results in practice. There is actually a small nice example in the famous Sutton and Bartow reinforcement learning book that shows you why doing the entire, you know, policy evaluation steps until convergence could actually be a waste of time. So I mean, this is a very simple grid word example like the ones we did by hand. I just didn't want to do it again by hand from scratch, so I'm just showing you the final result here. So during one iteration of policy iteration, the policy they started with, or maybe this is the first one, is a random policy, okay? And all the left hand side column is really just policy evaluation of the random policy. So it converges after some time. So at infinity, it reaches those values for every state. However, they also plot on the right column right here what would happen if we just update our policy greedily with respect to whatever value function we see here. And they just try to show you that while policy evaluation needed at least 10 steps, maybe more than 10 steps until convergence, actually the policy was better or was already optimal even after just 3 steps. So in this case, they didn't even need to do multiple iterations of policy evaluation, policy improvement, policy evaluation, policy improvement. They just did one policy evaluation, and at the middle of this policy evaluation, at k equals 3, they already got the optimal policy. So they are trying to argue here that doing all the computation, is really redundant and doesn't make a lot of sense. But yeah, I mean, it really depends on the actual problem. Maybe this is oversimplified, because even if they didn't truncate at k equals 3, they wouldn't need more than one policy evaluation followed by policy improvement step anyway. So it's really anyway a simple problem, but it's just a good example to keep in mind. More importantly, what I would like to emphasize is this whole idea of policy evaluation followed by policy improvement and so on will appear a tremendous amount of times in this course. It's really a fundamental idea in reinforcement learning. Sometimes this is called the modified policy iteration algorithm. Sometimes it's also called the generalized policy iteration as well. So it really appears in those two terms, and this idea of oscillating between evaluation then improvement, then evaluation then improvement really happens a lot. Think of it as you like working in one company for some time, like a couple of years. So you are now evaluating your skills in terms of salary or something, and then you decide to do some policy improvement or some self-improvement, and you do some master's program or something. Then you work for another company again, evaluating your new skills and so on. So it seems that this is a good way in life in general to improve or to reach your best self in life, by doing some evaluation and then finding out how to improve. So improving a little bit, then doing some evaluation and then improve a little bit. So it is really a fundamental idea in reinforcement learning and possibly in life as well. See you in the next video. So the second term, which is dynamic programming, will actually take a little bit more time to explain. It is a little bit of a confusing term, but if you look at the history of it, you will find out it is actually confusing by design. So this term was coined by Bellman. So the same Bellman we are talking about in like 1940s or 50s, sometime in this period. And he coined this term because he was working in some research company, and he wanted to secure some fund. So he wanted his work to sound like it is something very practical and not just pure math. So he designed the term dynamic programming to relay this feeling that this is something extremely practical. He was working for the army, so he wanted something that convinces the army people that this is really something related to army efforts. So at this point in time, programming didn't necessarily mean programming languages that we are aware of today. It simply meant like planning or scheduling. And also dynamic just meant that there are multiple time steps involved. So to the hearers or to the listeners of this term, it really meant planning or scheduling some army work over time, something like this. So he wanted to secure funds, and that's why he used this term and made it vague by design. But this is for history. For now, dynamic programming is actually like used in multiple domains, not just reinforcement learning. It is simply, you could think of it as a general framework that is able to solve specific kinds of problems that have some specific structure to them. So think of this term as just, a solution method to some specific type of problems. And those problems generally have two main characteristics. One of them is called the optimal substructure, and the second characteristic is called overlapping subproblems. So let's explain what this really means. So optimal substructure means that in order to solve a bigger problem, you can really divide and conquer. You can try to separate it or partition it into multiple smaller problems and then solve each one of those sub-problems optimally and then combine the solution, and then you get an optimal solution to the bigger problem. So one example of this would be, you know what, I want to earn $1 million. So maybe I can earn, you know, $400,000 and then earn $600,000, right? So if I solve this one and then solve that one, then I have solved the bigger problem, right? Or maybe another case would be, I want to go from city A to city C and there is a city B in the middle. So I could say, to solve the bigger problem of reaching city C from city A, I could first solve the first problem of how to go from A to B, maybe by a bus, and then how to go from B to C, maybe by a boat or something, and then I have solved the bigger problem by solving the smaller problems. So some problems have this optimal substructure, and this is one characteristic that says, you know what, maybe we can use dynamic programming methods. Now let's see maybe a more mathematical example that everyone is probably aware of, which is the Fibonacci series. Remember, the Fibonacci series is something like, you know, starts like 0, then 1, then 1, then 2, then 3, then 5, then 8, and so on. And it follows this relationship that the Fibonacci series at a specific time step n is equal to Fibonacci at n minus 1 plus Fibonacci at n minus 2, right? So this is a definition of the Fibonacci series, and this has this optimal substructure because I want to compute Fibonacci of at time n, or at element n, or at index n, and in order to solve it I really need to find this one and this one. So this is optimal substructure. The Fibonacci series also has the second property that we didn't talk about yet, which is called overlapping subproblems. Overlapping subproblems means that the same, you know, quantity you might need to compute over and over and over again, all will appear like over and over again. And again, if you use the Fibonacci series here, let's say you want Fibonacci at index like 0, 1, 2, 3, 4, 5. So f of 5 is really f of 4 plus f of 3, for example. But then if you calculate f4, this is really f3 plus f2, right? And again, if you calculate f3 itself, it is f2 plus f1, and so on. So you could see that if you act naively for this computation, you could define a recursive function, just a recursive function in Python or something, and then you, for any index you get, you calculate from scratch. But then to calculate f5, for example, you see that you calculate f3, you know, 2 times. One because you need to calculate f3, and another one because you calculate f4, and f4 will need calculation of f3 again. And now for f2, you also have, you know, calculated multiple times, and so on. And this will be like even more apparent if you do f6, which is equal to f5 plus f4. So now you calculate f4 multiple times, and for every time you calculate f4, you have to calculate f3 and f2 from scratch, and so on. So this is a very natural problem that also have those overlapping subproblems, which means the subproblem appears multiple times. So in programming, if you want to have an optimal solution, or like a good solution or a good function to calculate the Fibonacci series, you have maybe 2 solutions. One of them is to keep a global array or something that has, or dictionary that has pre-computed values. Like whenever you compute f4 once, you store that in the dictionary or in the array, and so that when you encounter it again, maybe you calculated it here, but now you are calculating F6, you just query the array or the dictionary in order to not recompute it again. So this is potentially one way to do that. Another way would be just to start from 0 and then calculate F0, F1, F2, F3, you know, sequentially, and create a very big table and just store this table to avoid computation entirely. But what I'm trying to say is, if you have those, you know, characteristics of the problem, you need to exploit them. There are ways to exploit them in order to reduce the amount of computation and you know, do things more optimally. The problem will be really screaming to you, please use dynamic programming to solve me. So those ideas that are represented here, like maybe having this caching or something, you could think of this as one way of doing dynamic programming if you want. Okay, so now there is maybe a question like, are there problems with non-optimal substructure? Like, are there problems where if you partition it into subproblems and then solve the subproblems independently, completely independently, and then merge those solutions, this solution is not a good solution for the bigger problem, or not an optimal solution for the bigger problem? The answer is actually yes, and maybe you can curate a toy example for this case. So suppose you want to go again from city A to city C, okay? But you have some constraints. So you want to go from city A to city C through B, and suppose you are in a country where you are allowed one free train ride per year or something, okay? And there is a train from A to B, and there is a train from B to C. But you have one free train ride. Otherwise, non-free train costs maybe $20, and then there's a bus that always costs $10 and it's always not free, okay? Now I want to go from A to C with the least amount payment possible. So if you solve it, you solve the subproblems independently, completely independently, then the solution would be to go from A to B via train because it is free, right? I am really blind to everything that happens. So from A to B, I use a train which is free. From B to C, I also think that I can use the train because it's free, because I am really working very independently, right? So if I do this, I will use train here and train here. But when I merge those together, I'll actually end up paying $20 because if I solve every subproblem independently, the solution to the bigger problem is not really the same. In this case, a better solution would be to use train from A to B and then bus from B to C, in which case I will pay only $10, right? So there are some cases where this optimal substructure exists and some cases where it doesn't exist. When it exists and when you have overlapping subproblems, then really using some dynamic programming methods or ideas would be very useful. And now let's revert back to reinforcement learning. So MDPs. Do they have the two characteristics of problems that should be solved using dynamic programming? And the answer is definitely yes. Because in an MDP, we have established the fact that if you can get the optimal action value function at every state action pair, you have really solved the entire MDP, right? Like we have showed this multiple times. We need to get Q star of S and A for all state action value functions. And if you know this, you can get the optimal policy by acting greedily at every state, right? So it has this optimal substructure, yes, definitely. And also it has the overlapping subproblems, because if you look at, let's say, the Bellman expectation equation, so we have V by of S is equal to maybe summation over actions by of A given S, right? And then for every one of those, you get the immediate reward plus gamma multiplied by probability here, V by of S prime, right? So this is the Bellman expectation equation, and you can see again that there are overlapping subproblems because maybe multiple states could reach S prime, right? And S prime here could show up in the Bellman update for multiple states, right? You could have, a grid world like this, right, where you can move also diagonally and in north, south, east, west, and diagonally. So this state, for example, you could reach from here, from here, from here, from all directions, for example. And so this one right here will show in the Bellman expectation equation of all those states. So you have this overlapping substructure, and we actually made use of that in our algorithm, like policy iteration and policy evaluation and so on. And we actually already keep a table for the value function, right? We keep this table and we update it. So in a way, we are using this idea of caching that we also introduced in the Fibonacci example. So in fact, the MDPs are a very great case of using dynamic programming, because it has the optimal substructure, and it also has the overlapping subproblem. And those algorithms, like policy iteration, policy evaluation, you could think of them as algorithms that make use of this substructure via this, this equation right here, and also the equation for the policy, for the value iteration algorithm. And also those algorithms use the idea of bootstrapping, of updating an estimate towards an estimate. Now, if you look at the Fibonacci example, you will see that we are using the idea of dynamic programming, but we are not using bootstrapping, because we are not updating an estimate towards an estimate. We are updating, based on ground truth, based on, calculations that are not estimations. So I just want to say that bootstrapping and dynamic programming are two different things. Sometimes they exist together, like in the MDPs, but sometimes you only use dynamic programming, like the Fibonacci sequence, and sometimes maybe you have examples where you can only use bootstrapping without using dynamic programming. I mean, it is possible to have it like this. So in the world of MDPs, there is another angle where you can look at this optimal substructure idea. So I did mention that one way to look at it is, because if you find the optimal action value function at every state, you have solved the entire system and you have found the optimal policy, right? So this is one angle to look at this optimal substructure. You solve, smaller problems. If you could find the optimal action at every state, then you have solved the entire MDP. Maybe this is one way to look at it. Another angle may be to look at it through value functions. So if I ask you to find the value of state A, which is, the expected return from A until the end of episode, and instead of solving it directly, you could decompose it into, finding the immediate reward on average between A and B, and then finding the value function of state B. And maybe for some reason state B is easier to compute the value function for, because it is maybe closer to the goal state or something. So the important thing is we could decompose the bigger problem, which is finding the value function of a state that is very far away from the goal, and we can decompose this into finding the immediate reward and the value function of maybe another state that is closer to the goal. So this is just some intuition about where this optimal substructure shows up in MDPs and why dynamic programming methods make sense in MDPs. So I think this is enough for dynamic programming. See you in the next lecture. In this lecture, I'd like to give some random notes and variants to what we covered so far. Some of those notes I actually covered before, but I'm saying them for emphasis. So the first one is, let's call it no zero initialization or reinitialization. What I really mean is, when I did the numeric example for policy iteration, and whenever I entered a new policy evaluation step, I reinitialized the value function table to all zeros, and this is fine, but we don't really need to do that. We could just leave it as it was in the previous iteration and it will still work, because the contraction mapping argument says that no matter where you start, you will still reach the fixed point. So you don't need to start at zeros, and actually starting at the previous value would actually make a lot more sense compared to starting from zero, because starting from zero says, you know what, lose everything you have learned before, lose any sort of relative, you know, importance or relative value between the states. And this might have some value even if it was, you know, via a little bit older policy. So, I mean, this is just a note. You can do whatever you want. But a good benefit of starting from the previous one and not zero initialization is you have this, you know, mapping between value iteration and policy iteration. If you use k equals 1, this, you know, correspondence is only valid if you do not reinitialize to zero every time you do a policy iteration. But every time you do a policy evaluation, sorry, but you know, you can do whatever you want. So this is maybe the first note. The second note I also talked about, which is you don't need to use the values from the old iteration k when you do updates at time k plus 1. Like what I did again in the vanilla policy evaluation is I've always kept 2 copies of the policy array or dictionary or whatever, right? And then at iteration k plus 1, when I am updating state A, and state A depends on state B and C, I used the value of B and C from iteration k, not the ones I just calculated for iteration k plus 1. And this is valid, but also that one is valid. So you could really do what you call in place update. So you don't necessarily need to keep 2 copies of the array or of the dictionary. You could just update stuff in place, and then it will also work. The proof we provided for the contraction mapping argument used the vanilla or the standard algorithm where you have 2 different copies. However, there's also a proof that proves that in-place update also actually works. So in-place update while doing policy evaluation or value iteration is also valid, even though I didn't cover the proof formally. So this is another point. A third point I wanted to talk about is called prioritized sweeping. So again, if you know some specific information about the MDP and you are not really completely blind, it might make sense to do what's called prioritized sweeping, where you start the update from the most interesting states. For example, the states that are closer to the goal states, because those ones carry the most information and the most, you know, potential rewards or penalties. And this information that is grounded in reality, if it spreads through the system early on, you will get, you know, better results like sooner. So this is the idea of prioritized sweeping. If you, for example, could start from the state that is closer to the goal state, you will actually do better or faster conversions. Both those items right here are sometimes labeled as asynchronous updates. Okay. Now, there is another idea that is slightly related, which is called real-time dynamic programming or real-time updates, which is a little bit interesting because it actually involves an agent working directly in the environment. I mean, for dynamic programming, you don't really need an agent to solve the MDP because you know the model dynamics, you know the reward function, you know the state transitions, and you know everything. So you could just do what we called like planning, if you remember, where you do this simulation in your head while you are, you know, in your bed. But if there are a lot of states and you are really not sure which states are important to update, like you want to do prioritized sweeping, but you don't know really which states to update first, there is this idea of real-time dynamic programming where you could have the agent actually interact with the environment and you just record which states and actions it ends up doing, or which states it ends up in, let's say based on some specific policy. So you know which states happen more often and so you call those states like higher priority, and so you try to update those specific states or the values of those specific states more often, even if you are in control of the actions. And this is called like real-time dynamic programming. So it's kind of not entirely model like based, because you still are data driven, but it is still also model based because you only use the interaction with the environment to gather states. So it is really model based, even though it doesn't look like it. It's also data driven in a way because you collect data from the environment. Now it looks like, let's say an example would be you have your kid with you in the kind of an amusement park, and you want to ensure the maximum safety for this kid, but the amusement park is really large, but then maybe you notice that your kid spends almost all of his or her time in the water park or in the aqua park. So you need to really prioritize being safe in the aqua park. Maybe you buy some swimming vest or something, right? So this is really real-time DB. You could think of it as a form of prioritized sweeping as well. Okay, one other idea I'd like to talk about is why not compute Q directly. Like in our numeric example for value iteration, for example, we used the Bellman optimality equation for the state value function, and converted it into the iterative form and so on. Why did we do that and didn't like use the Bellman optimality equation for the action value function directly? I mean, the answer is, if you have dynamic programming, if you know the model like dynamics, it is actually more efficient, much more efficient, to calculate the state value functions first and then recover the action value functions after you are done finding the optimal state the optimal state value function, sorry. That's because the computation for the action value function will just be larger. Like for every state you would like to try all the actions, so this array you keep, or this dictionary array this dictionary you keep will actually be much larger, and you will do more computations for a lot of iterations, and then you will reach the same result. So actually in a couple of lectures I will do an example using the action value function directly, and it will become clear why using the state value function is faster. But it really makes sense, right? For every state you have multiple actions, and if you keep track of every one of them, then your storage needs to increase. I mean, it just makes sense. Now this is only the case for model-based reinforcement learning, where you actually know the transition probabilities and the reward functions and the environment dynamics in general. However, later on, when you go model-free, we will actually have to estimate the Q value function anyway. So don't just throw those Bellman equations away. We will need them pretty soon. And lastly, in this lecture, I'd like to again remind you that those dynamic programming methods still work with those discrete state and action space, and they work for medium-sized problems. So they are a little bit better on average than using the closed form solution that we did before. However, they are still heavy. Like we will see in the next lecture actually that for value iteration, if you calculate the optimal value function, the optimal state value function, the complexity is roughly equal to O of the number of actions multiplied by the number of states, like square. So this is a complexity of value iteration if you use it to calculate the optimal state value function. And if you compare this to the complexity of the closed form solution, where you do a matrix inverse, which is O of S cubed, right? So if the number of actions is smaller or much smaller than the number of states, then this term right here is actually much smaller than this one. And this case happens a lot, right? Like if you are playing an Atari game, you have a tremendous amount of states, tremendous amounts of levels, but the actions are just maybe up, down, left, right, and fire. So maybe 5 actions, but the number of states could be insanely large, right? So in those cases, using dynamic programming is actually more efficient than using the closed form solution. Maybe in other cases it will not be the case, But again, in a lot of problems, this happens. And in a later lecture, I'll do some more, timing and convergence and complexity analysis on those algorithms. But what I'd like to say here is, while we are a little bit better than using just, the closed form solution timing-wise or complexity-wise, those dynamic programming algorithms still don't work very well in huge state space problems. Like, if you want to solve chess or Go using dynamic programming, that will not really work well. Okay, so we will still anyway need to design better methods, and those methods will be sample based, they will do search and so on, but they will not be direct, naive dynamic programming where you try to solve the value for every state in the entire state space. This will not really work. Okay, see you in the next lecture. So let's formalize a little bit the complexity analysis, or the big O notation for the algorithms we covered, like policy evaluation, value iteration, and policy iteration. So let's start with value iteration. Let's find the big O of this one. So suppose you are doing value iteration, then for every state you need to run this entire thing. And the first thing you do is a maximization over actions. So you need to calculate this term for all actions and then have, a maximization operator. So you really need to loop over all the actions. And this is why you have something like this. So you need to loop over all the actions, and we are calculating for the worst case scenario. Big O is for the worst case scenario. So we assume that all actions are doable from all states, and we also assume that if you take an action from a state, then all the other states in the MDB are also, reachable in the worst case. So to calculate this term, you still need to loop over all the next states, which are all the states in the worst case scenario. So this is why here you have another, number of states. And you do this for every different state. So you have another loop here over the states in order to calculate. So you have another number of states here. And this is the complexity bare iteration. So this is the complexity bare iteration. But then you actually repeat that multiple times because you don't converge in one iteration. So you might repeat that k times for value iteration, right? So maybe here k times if you want. But we put the big O notation per iteration, not for the entire algorithm. Okay, now for policy iteration, you actually have another loop, right? Where you loop over the policies. So maybe this is for value iteration. Maybe for policy iteration, you have something, similar, even though instead of the maximization, you have, summation, or you get the expectation, but it is still, the same complexity. So it is still the same right here. If you are working with state value functions, right? And then you repeat that k times, and then you repeat this entire thing maybe y times, because you do this for every different policy you get after the policy improvement, okay? Now, an interesting question would be, okay, what is the number of policies that you could try? And the upper bound on the number of discrete deterministic policies you could have in a discrete MDB is interesting. Like you have, let's say, those states. Every state, suppose you have A actions, like 4 actions. So in a way, every one of those states could have either 0, 1, 2, 3. If you have 4 actions, could be either 0, 1, 2, 3. So to calculate the total number of possible, combinations, it's really similar to the way you do it with binary numbers, where you have, let's say, 4 bits, and every bit could be either 0 or 1. So in this case, you have 2 power 4 possible combinations. In this case, you have A power number of states possible combinations. So this is the number of, possible policies, discrete policies. Although in reality, this is a huge number. In reality, policy iteration converges much, much faster. Maybe converges in, 10 iterations, 20, 40, even 100. But in no way it will be, you will not need to try out every single policy combination in most cases. So, this is the worst case, but maybe it doesn't happen that often. So in general, people use this big O for a single iteration to compare like algorithms. Now let's do something more interesting, which is what if we use the Q value directly. Do value iteration, but for the action value function. So let's actually see the complexity here. So again, for every state and action, you do first get the immediate reward, and then for every one of those, you have a loop over the states. So this is why you have the number of states, right? And then here you have a maximization over Q values of all the actions. So you still maximize over all the actions in the next state. So this is another loop over the actions, right? So you have the number of actions. And then you do this for every state and action pair. So this is why you have something like this. Okay, so the complexity per iteration, if you do the same value iteration algorithm using the action values, actually increases by a factor of the number of actions. And this is why in dynamic programming environments, it is really better to use the this one, the state value, not the action value, if you know the model dynamics. Okay, let's see you in the next lecture. So in this video, I'd like to answer this interesting questions. How many value iterations are needed so that the error from the optimal value is less than theta? Like, remember, value iteration, we try to reach the optimal value, and I would like to know, if I am okay with the difference from the optimal value of, let's say, 0.1 or 1 or something, how many iterations are needed so that I reach something good enough? Okay, so let's try to formalize this a little bit more. Let's first define the error. So the error, we define it using the maximum norm or the infinity norm between the value at iteration k minus the optimal value. This is the infinity norm, and I don't use of s right here. I just mean the difference between the two graphs, if you remember what we did in the Bellman contraction mapping proof. So we have two graphs, and I just want the maximum error between them. So this is a shorthand notation. So what I really want is, I want ek to be less than a specific tolerance theta, and I want to find k to achieve that. Okay, so let's see if we can do this. Remember that the Bellman optimality equation is a contraction mapping, and this means that the distance between two consecutive iterations is going to be, so ek is going to be less than or equal gamma multiplied by ek minus 1. This is because this is a contraction mapping, and this is actually the distance. This is the same distance we used in the contraction mapping proof, right? Now, if you do this from the first step, you find out that ek is really less than or equal gamma power k multiplied by E0, which is the error at initialization. Now, at initialization, you have more control because you actually initialize the values to be all 0, for example. So you have more control at initialization. But let's actually finish the computation without caring about E0. What is this value now? And then you'll find out a formula for E0 as well. So what we really want is, we want to find k such that gamma power k multiplied by E0 is less than theta, right? And we can do that. Actually, we could take the logarithm of both sides. So you could say log of gamma power k E0 is less than log of theta. And then you could just say, you could expand this, because log of AB is log A plus log B. So you could say that log of gamma power k plus log of E0, this is less than log of theta. And again, this actually you could do k log gamma. So k log gamma is less than log theta minus log E0. Okay, now you can divide by log gamma, but this is actually a negative number, and if you divide by a negative number, you need to flip the direction of the inequality. So we need to say that k is greater than log theta minus log E0. This is actually log theta over E0 by the logarithm rules divided by log gamma. And this is actually the formula we want. We found that you need at least k iteration where k is equal to this quantity. And everything in this quantity you know except for E0, right? So theta, you just put it, it's arbitrary, so maybe 0.1, it is what you want. And gamma is the discount factor, and you also know it. But you don't know E0. So our next step right now is to find out what E0 could be. And to do that, let's actually imagine we have an MDP and we would like to, you know, find the value, the true optimal value for a specific state. And this is by definition, you know, the summation from k equal to 0 until infinity of gamma power k, and then r t plus 1 plus k. Now you don't really know those rewards because they depend on the policy, and you still don't have the optimal policies. Those are just, you know, random rewards you get while you move through the system if you are acting optimally. So you don't know those, but you actually can put an upper limit on this quantity because you know the reward model in the environment, and you know just the maximum reward. Like, you know, in this MDP, the maximum reward you could ever achieve is, you know, 10. Or negative 10, in which case you take its absolute value. So you could put an upper limit on this one. This is definitely less than or equal the same summation, but if you replace every r by something that is bigger than it, which we call r max, and again this is an absolute value because sometimes maybe all the rewards are negative. I really want the absolute value of the reward. And now this is interesting because you could get R max outside of the summation because it's just a constant now. So here this is less than or equal R max, and then the summation of gamma from gamma power 0 to infinity. So 1 plus gamma squared and so on. And we already said that this is equal to 1 over 1 minus gamma. So here you could put 1 minus gamma, right? And this is, you know, an upper limit on the value function or the optimal value function for any state, or for the maximum state if you want. Now at the beginning of the algorithm you can choose vk where k equal to 0 to be just zeros. So in a way you could actually define E0 to be this quantity, right? Or to be less than this quantity, but you could also just be careful and extra careful and just say that, okay, I'll just, you know, define E0 to be equal to this quantity. In reality, it will be a little bit less than this quantity, but this is fine since you are trying to find, you know, an upper bound on the error E0. So you have this here, and now R max you know, and you know gamma. So given this one and this one here, you actually could find k. So let's do some, you know, numeric example. Suppose you are in an MDP where you want the tolerance to be 0.1. Let's say gamma is equal to, you know, 0.9, and let's say that R max in this specific MDP is just, you know, 1. So in this case, E0 is going to be R max 1 over 0.1 is actually going to be 10, right? So E0 is going to be 10, and so k is bigger than log 0.1 over 10, which is really 0.01, and here you have log 0.9. Okay, I calculated this before, and it's roughly 43 point something. I think it was 43.7, and so k, you need at least 44 iterations if you would like this this tolerance. Okay, so I think it's pretty neat that you could put this specific, you know, number on the number of iterations you want if you need a specific tolerance while doing value iteration. Okay, I think this is enough for this video. See you in the next one. So in this video, I'd like to do one more numeric example for policy iteration, but this time I'd like to use the Bellman expectation equation for action value function when I do the policy evaluation instead of the Bellman expectation equation for state value function. Okay, so it might be not super clear why I'm doing this right now, but it will actually become super relevant later on when we cover model-free reinforcement learning. I'll actually refer back to this specific problem then, but we'll know why, when we go to that part. So it is actually useful if you stick around for this video, but you could also skip it if you'd like. So we have this MDB. It's a simple MDB. We have only two states that are non-terminal, and then you have three terminal states. And now I define gamma to be equal to 1. The reward of going into G1 is 10. The reward of going into G2 is 100. And the reward of going into L is negative 10. And the reward for any unnecessary action is actually going to be negative 1 in this formulation, because I don't want to take more steps than needed. Okay. So this is the Bellman expectation equation, right, for action value functions. It maps the value of a specific state and action pair to all the values of the state and action pairs at the next time step. Okay. So let's actually simplify this a little bit, because here we know the environment dynamics, they are deterministic. So this term right here will just collapse. And also we can choose for policy iteration. We can start with any arbitrary policy. We can start with a deterministic policy. So let's just do that in order to also move this term away. So we could say now that Q pi of S and A, after those simplifications, is going to be the immediate reward plus really the value of where you end up at. And the gamma is equal to 1, so it also simplifies. So we simplify into this equation. So now let's try to find this value, and now we need to find this for every state and action pair. So the array that we keep, or the dictionary that we keep, is not only 1D dictionary of the value of the states, but now it's going to be a 2D dictionary or a 2D array, because we have all state and action pairs. So this is, more work really than the state value function calculation, but it's still going to be useful, and we will see why soonish. So I chose this, initial policy to be, just go up here and go down here. So I can choose anything I want. Now let's calculate Q of, let's say, A and maybe action up, right? So I initialize this table here to all zeros, arbitrary initialization as well. So Q of A and up, this is going to be just this reward. So it's going to be 10, right? And then the value of any terminal state is 0 by definition. So Q of A and down is actually interesting, because now we assume that if you take any illegal action, you incur the reward or the penalty, but you stay at the same state. So if you do this, you really get negative 1, and then plus the value of the state you end up in, which is going to be A, and the action you would take in this state according to the policy, which is really up, right? So now that's interesting, because now if we use asynchronous updates, this means we just use the same table in place. We don't use the value from the previous iteration. I just use it from the same table. And so I just updated this to be 10, right, in the previous step. So this is going to be actually 9. Now this is interesting. Now here we put 9. Also from A, if you go right, this is also an illegal action. So it is really negative 1 plus the value according to pi of A and up. And this is also going to be 9. Okay. So if you go right, this is also going to be 9, which is interesting. Now if you go left, you will have negative 1 plus the value of state B according to the policy. So now you go down, right? But Q of B and down so far is just 0. It's just 0 in the table. I'm just following the table. So this is going to be just negative 1 in this iteration, which is fine, I guess. Now let's go for B, okay? And again, we are moving asynchronously, or we are doing in-place updates. So the value of B and going down, this is really negative 10, right? And the value of B and going up, this is by definition equal to the reward, which is 100 in this case. The value of B and going left, this is an illegal action, so it's going to be -1 plus the value of B and following the policy. So I go down, but we already just calculated this one, so let's actually update them. Let's not forget to update them. So here we have -10 already, here we have 100 already. So this is going to be -1 plus -10, so this is going to be -11, right? So this is going to be -11. So -1 plus this value, so -11, and then Q of B, what's remaining is going right. This is going to be -1 plus, you get to state A, and according to the policy you need to go up, right? So Q of A and up, this is going to be 9 here as well, right? So here you get 9, and here you get actually -11. So this is very bad. So this is the first iteration of, you know, policy evaluation, but policy evaluation hasn't converged yet. We need to do another step, right? We need to do another step of policy evaluation, and then after that we will act greedily and improve our policy and then repeat again. So I mean, it's a long algorithm, but I think it is simple. So let's do this again. So Q of A and up is going to be the same, so it's going to be 10. Q of A and down, this is going to be -1 plus Q of A and up, so this is going to be 9, so no change here. Q of A and maybe going right is going to be the same, 9, right? But I think Q of A and left, this is going to be -1 plus Q of B and whatever action the policy tells you to do. So Q of B and down is actually -10. So this is going to be -11 now, right? So you need to update this. Instead of -1, it is going to be -11. Now let's do Q of B and up. This is still going to be 100. Q of B and down, this is grounded, in reality is going to be -10. Q of B and left, the legal action is going to be -1 plus Q of B and down, so it's going to be -11. So again, no change for this. Let's see if Q of B and right will change. So Q of B and right, this is going to be -1 plus Q of A and up. So I think this actually is not going to change as well. So I think we have reached convergence now for the first policy evaluation step. I'd like you to note something very important. Here we evaluate all the state action pairs, even the ones that are not explicitly visited by the policy. So at state A, the policy says always go up, but you still are able to evaluate all, you know, the actions in the state. We can only do this. Because we know the reward model and the environment dynamics. I know that even though the policy is saying, you know, go up, I know that if I go right, I will get into state B. I know this for a fact. I know what reward I will get, okay? So this is the main reason why we can do this. So the visitation of state action pairs in the table, or visiting those specific cells in the table, is actually independent from the policy we operate under. Like, we can still visit all the cells in the table, and this is only valid because we know the environment dynamics. Later on, when we are model free, we will not have this luxury and we will need to do something about it, okay? But let's do that later. I'm just trying to let you know why I care so much about this example. It's because of this specifically, okay? So let's now act greedily. So let's choose a better policy. So let's just do it, and do it by acting like greedily. So let's say that this is by 1. Okay, so for A we need to choose one action. For A, it is the action that has the maximum reward. In this case it is still up actually, so here this is up. For B, the one that has the maximum value is 100, so it is also up. So the policy did improve, but we know this is not the optimal policy, because we really know that the optimal policy is for A to go, you know, into B first. So unfortunately this means we need to do another iteration of policy evaluation, and this time I'm gonna start from this table here, and I will not reinitialize everything to 0. I mean, we are allowed to initialize to any number, so I'll just start from, you know, this table. And now let's actually you know, maybe not like this, maybe just put it a little bit down. And now all the two policy, or the two actions in both states, is to go up. So let's actually go again and evaluate in place. So Q of A and up, this is gonna be the same, it's gonna be 10. Okay, no change. Q of A and down, I think it is still gonna be the same, so it's gonna be 9. Q of A and right, it's gonna be 9. Now Q of A and left, this now is going to be -1 plus Q of A and Q of B and up, because now the policy says in B, please move up. Q of B and up is actually 100, so this is going to be now 99. Now this is an interesting change, right? So instead of -11, you are suddenly going into 99. Okay, that's very interesting. Now for B, I think nothing will change for B. Like if you check it, like Q of B and right is going to be -1 plus this, so it's 9. Yes. Q of B and left is going to be -1. No, I think actually it might change. So Q of B and left is equal to -1 plus Q of B, because you end up in B, but then you need to go up. So this is going to be 99 as well. Okay, so this is going to be 99. Q of B and up and down will be the same, and I actually think we have converged for this iteration. So let's choose the optimal policy again, or not the optimal policy. Let's choose the, you know, policy improvement. So by 2, like let's act greedily. So here at A, now the best action is indeed to go left at A, which is great. And then for B, the best action is still to go up. And so this is actually the policy you end up in, and this is the optimal policy indeed. So we managed to get the optimal policy and the optimal action value functions using the iterative policy iteration algorithm, and in the policy evaluation step of it, we used the Bellman expectation equation for action value function. See you in the next video. So this is another checkpoint lecture where I try to summarize what we covered and what we did not cover so far in the general reinforcement learning world. So far we are still working with discrete action spaces and discrete state spaces. We have not covered any algorithm to work with continuous states or continuous actions, right? We are still in the world of small to medium MDPs. We can't still cover or solve very large MDPs, even via dynamic programming. We covered multiple ways to do policy evaluation. One of them was to convert an MDP into an MRP, then solve the MRP using the closed form solution. But another method was the policy evaluation algorithm, which is an iterative dynamic programming algorithm where you iteratively substitute into the Bellman expectation equation for the state value function or for the action value function. We also finally managed to get the optimal policy and the optimal value function, and we used dynamic programming to do that. again, we had two different methods. One of them was called value iteration, where we just iteratively substitute into the Bellman optimality equation. Another algorithm was called policy iteration, which had those two steps where you choose a policy, evaluate it, then act greedily to improve it, then evaluate the new policy, then act greedily again, right? We also covered that value iteration could be thought of as a special case of policy iteration, where you do this policy evaluation step only for one step and then do policy improvement right after this. We also covered an intermediate, middle ground between the two algorithms called modified policy iteration or generalized policy iteration. So this is also a good thing. This whole thing was to do the task of control in reinforcement learning, where control means trying to get to the optimal policy. Now, so far, we still didn't do machine learning. We didn't use any data, except for this one tiny case where we talked about real-time dynamic programming, where we potentially could use some data just to give priority to different states, but we are not really doing machine learning yet. We will start doing machine learning kind of really soon, because in the next section, I'm gonna try to start talking about model-free reinforcement learning, where we do not know the model dynamics. So everything we covered so far, all the dynamic programming, methods that we covered, like value iteration and policy iteration and so on, so far depended on us knowing the environment dynamics, knowing the transition probabilities, knowing the reward models. But in the next section, we will start exploring what will happen if I really don't know what's in the environment, and this is called model-free reinforcement learning. And in a way, this is where we start using data or samples directly and try to learn something useful from them. So that's it for now. See you in the next lecture. So let's switch gears a little bit and start talking about model-free reinforcement learning. So far we have managed to do prediction and control using model-based reinforcement learning methods. Specifically, we used dynamic programming. But we emphasized that using dynamic programming doesn't really work if you are model-free, because you use those iterative substitution into the Bellman expectation equation and the Bellman optimality equation, and those have the model transition probabilities and reward functions like embedded into those equations. For example, v pi of s is equal to the summation over all the possible actions according to the policy, and then for every action you have the reward r of s and a, and then the discounted next state value, so b of s prime given s and a multiplied by v pi of s prime, right? So we can use dynamic programming if we know the R and if we also know this transition probability, but if we are model free, we can't really use that. So dynamic programming fails even at small systems where you do not know the environment dynamics. But at the same time, dynamic programming also fails if you know the environment dynamics, but the system is extremely large and the episodes are extremely long, and the branch factor is very large, and I will tell you what I mean by the branch factor right now. So in some cases, like dynamic programming even fails with large systems, right? Even if you know the environment dynamics. So let's suppose you are at a specific state, maybe this state, right? And you want to get the value of this state, so you want value of s. But now let's say from each state you can have 3 actions, which is really a small number of actions. So this is action 1. Now, if you take action 1, the environment could throw you maybe at one of 3 states on average per action. So you could go into those, but then you can take another action, and also the environment maybe could throw you here, maybe just 2 states in this one. And then here you take another action, and then the environment could throw you in one of 3. And now every one of those you can actually do the same. So this is what I mean by, like you have a tree in a way. So in this state you can do another action, and then the environment could also maybe throw you here or here, and the same here, right? Environment could throw you here, or maybe also here, and so on. And if the length of a typical path is like very long, and also if the branching factor is large, and the branching factor, I mean roughly from every state how many actions you can take. So maybe here this is 3, but in another example it could be 100 or 1,000. I mean, it really is arbitrary depending on the MDB. And then also from every action, how well the environment respond and how many states can it throw you into, right? So if those branching factors are large, and I ask you to get the value function of the state, then it's really not that easy to do this using dynamic programming, because to get the value function of the state, you really need to evaluate all those paths, and then to evaluate all those paths for every one of those states, you still need to evaluate all the paths from the state and so on, until you eventually, for example, reach a terminal state or a goal state where you could get grounded in reality and then have backup through the entire MDB, right? So using the Bellman equations or dynamic programming in those super long MDBs is not really super efficient, and this is why we need a more efficient way. Now let's switch our mindset a little bit, and if I tell you what is the value of this state if I follow a specific policy pi, another thing you could do is to generate samples from this MDB. Now, even if you know the environment dynamics, you can still use trajectories if you want, if this is easier than using dynamic programming. So if you know the environment dynamics, I could ask you just try to generate random trajectories. So trajectory is, a sequence of states, actions, rewards, states, action, rewards until the end of episode for episodic MDBs. So maybe a trajectory could be something like start from the state, then maybe, choose this action, right? And then go into this state, then choose this action, and then go into the state, and then maybe after a couple more steps, you reach a terminal state. So the trajectory doesn't take into account all the possible variations. It is, in a way, one instance of those variations until the terminal state. And the good thing about trajectories is it doesn't really take into consideration this huge branching factor, and it doesn't need to do those, heavy backups. It is really one instance, and you could do this in two ways. Like if you know the model of the environment, you could just, sample from that model without doing any action in the real world at all. You just say, you know what, I am following policy pi, so I'm gonna choose an action based on this policy, and then I know the transition probability B of S prime given S and A. This is the environment dynamics, so I could just sample one of those next states S prime based on this probability distribution, right? Or like following this probability distribution, and then in this state I follow the policy again and so on. So you end up with a trajectory like maybe something like this, like S0, and then you take an action in this state, and then you receive a reward at the next time step, right? And then you reach also a next state, and then you take another action A1, and then you receive a reward R2 and get to a state S2, and so on until you get to some terminal state. So this is one way to generate trajectories if you know the model. But now if you do not know the model, this is an even more important reason to use trajectories, because you don't know the model, but you can interact with the environment. You could throw the agent into the world, right? You could throw the agent into the woods, right? And then the agent will take some action, and it will move from one state to the next, and you could just record those trajectories. So you say, I was at this specific state, the robot took this action and then received this reward and moved into this next state. And again, this happens over and over again until, for example, it crosses the jungle or something. But then after it does this, you have one trajectory. Now you could have then another trajectory. You could start from the same start state or from any other state depending on the MDB. Some MDBs have a fixed start state, like chess, for example. You all start from the same state, but maybe some other MDBs start from multiple start states or something. So again, you have another trajectory. So in this format here, this subscript, I mean, like this is time. So this is t equals 0, t equals 1 and 2 and so on. But if you want to be more explicit, you should use, you know, explicit states. Like I was at state SA, and then I took a specific action. Maybe the action is left, right? So I took action left. I received the reward of -2. Then I got into some state SB. I took action, you know, right this time, and then maybe I received the reward of +3, and then I went into state SC and so on. And maybe then I took another action, let's say right again. I received the reward of 3 again, and then this is the terminal state. So this is one trajectory or one episode. Then another episode, maybe it starts with SD, you know, completely different state, and then I took action right according to the policy, because I have some sort of maybe stochastic policy if I want. I got a reward of 2, and then I got into SC, and then I took an action of left. I received a reward of -1, and then I reached a terminal state. So this is another episode or another trajectory and so on. So you could really find a lot and lots of trajectories. And now if I tell you what is the value of this state here, using the trajectory method, you need to remember that the value function is really the expected return, right? It is really r at time t plus 1 plus gamma rt plus 2 and so on, given that you start at state S, right? You need to remember this equation. It's a very important equation. So v pi of S, this is really the expected return. So given that st is equal to S, and if you expand it a little bit, gt is really rt plus 1 plus gamma rt plus 2 and so on, right? Given st is equal to S. So if you record those trajectories and record those, you know, rewards, and if you have, you know, 1 trillion trajectories all starting from the same state, then you could understand that you could just, you know, get this expectation, just average all the rewards. Or for every trajectory, for example, you could calculate rt plus 1 plus gamma rt plus 2 until termination. And then you have one value, one return for one trajectory, and then you have 1 trillion trajectories, so you just average all of those, and then you will get an estimate of v pi without going through the path of dynamic programming at all, and without having to run all those, you know, sweeps over all those actions and all those states. So having trajectories helps you in those two cases, if the model is too large, and also if you don't have a model at all, in which case you are in model-free reinforcement learning. So in the next few lectures, or in the next few sections actually, we will focus more on model-free reinforcement learning. First, we will cover how to do prediction or like policy evaluation using those trajectories. There are a lot of different ways to do this. Some of them are efficient, some of them are less efficient, and so on. And then we will also cover how to do control or like policy improvement, or how to find the optimal policy if all what we have is trajectories and we don't have the model of the environment. See you in the next video. So let's start by policy evaluation model-free algorithms. And the first and simplest like algorithm we would start with is called Monte Carlo evaluation for, you know, state value function, but you could also use it for state and action value function if you want, and we will cover this like later. But this algorithm is really simple. Like suppose you have some trajectories like SA, right? And then maybe you took some action, and then you get some reward. So maybe this is R1 if you want, and then you end in a specific state SB, you take another action, and then you get R2, and let's do another one. So you end up in SD, for example, and then you take some action and you receive R3, and then this is maybe the end, or like here you have the terminal state. Okay, so this is one trajectory. Now suppose you have another trajectory like this. So SA again, and you take some action and you get R1, and then you get to SB, you take some action, you get R2, but then you end up in SA again, and you take maybe some action and you get R3, and then let's say you also terminate, and then you have a lot of those. We would like to develop an algorithm to estimate the value of SA. So SA happened here, it happened here, and also happened here. We would like to estimate the value of SA based on those returns, but you have, a trillion returns. Like, you need this, for this to really be a good estimation, you need, a very large number of trajectories. But for the case of, introducing the algorithm, those two are enough. So we have two versions of Monte Carlo evaluation. One of them is called first visit Monte Carlo prediction, and the second one is called every visit Monte Carlo. So now let's cover the intuition, and then we will cover a slightly better, or slightly more efficient algorithm to calculate this. So first visit Monte Carlo really says that if in any one trajectory the same state appears multiple times, we only care about the first time it appears. So in those trajectories, we really ignore this one. And we have two returns. We have one return for SA. We have one return from here to here, which is really R1 plus gamma R2 plus gamma squared R3. So we can have two values of the return from the first state until the end. Let's call them G1 and G2. So G1 from the first trajectory, it's really R1 plus gamma R2 plus gamma squared R3. And then you could also have like G2 from the second trajectory, right? Starting from this state. So this is G1 for the initial state, and this is G2 for the initial state as well. And you just average them out and you say, okay, so this is roughly the value of SA. So under Monte Carlo first visit, this is how you get V of SA, or get an approximation or an estimation to the value of SA, right? Now, if you do every visit Monte Carlo, then you also need to account for this one right here. So for every visit, you will have three terms. The first one is the return from here to the end, right? The second one is the return from here again to the end. The third one is really the return from here to the end. Like, remember that the return only looks into the future. And so if I face this right here, this SA right here, I don't care about what happened in the past. I just need, the overall or the total discounted return from this time step right here until the end. So if you do every visit Monte Carlo, you have three returns, right? For SA, so plus G2 plus G3, and then you divide it by 3. So again, this is another estimation for the value of SA, right? And now if you have lots and lots of trajectories, those two will actually be roughly the same. However, if you don't have enough trajectories, then maybe one will be better than the other. It really depends on the system. I don't think there is, a clear answer on which one is much better in general, but you get the idea. So this is the intuitive idea, and now you do the same for all states. So here we got it only for SA, so this one, and this one. Then we need to do it also for SB, and for SB you have a return from here to the end, and from here as well, from SB in the second episode, you have a return from here to the end as well. So you'll have two values, and here first visit is the same as every visit because state B never repeats, so you have no loop that could get SB again after you reach one SB. So in this case, they are actually the same. So this is the intuition of the algorithm, but now let's actually show how to implement that maybe more efficiently, because the way I described it right now, it is as if I move into my episode and then I find a state, and then for this state I calculate the entire return until the end, and then I get to another state and I calculate the entire return again from the end. But there are obviously some shared part, so we don't need for every state to recalculate everything until the end, right? So we can actually make use of a very important recursive relationship that we covered before, which is the return at time t is equal to the immediate reward at time t plus 1 plus the discounted return of time t plus 1, right? So this is actually an important relationship that we can use right now, because we can sample the entire episode. We anyway have to sample the entire episode in Monte Carlo evaluation, and then we get to the terminal state. Then we get the last return, like G final or GT, sometimes called like this, so GT. And then for the terminal state, this will actually be 0 by definition. but then you can use it and use this reward, which is R3, to get the return for this state, right? And then you can again use the recursive relationship. So the return at this state is equal to this reward plus gamma multiplied by the return at this state. And then the return of the state is equal to, again, R1 plus gamma multiplied by the return at this state. So you kind of move from back to beginning, and whenever you encounter like a state, you can update its return based on this recursive relationship. So one possible algorithm for us to get this every visit Monte Carlo prediction or like policy evaluation is this algorithm in front of us. It is not the most efficient yet, but it is also not the worst in terms of efficiency. It's like a middle ground. So let's see how this works. So the input to this algorithm is just a policy, because we want to evaluate one policy and find the value functions, right? Or the value function. Now we also define some array to hold the values for every state. So this is similar to the array that we used to do in our numerical example, just an array. But then also we need to keep track of all the returns for every state. So every state could appear multiple times in all of our trajectories, and every time the state appears, it has its own return until the end of episode, right? And so you need to keep those returns, because then you want to average them at the end, right? So this is the algorithm. And what happens is you loop forever, like you have a while loop or something, or like you loop for, you know, the number of episodes that you have. But here it's a little bit online in a way that you loop and then you generate an episode following pi. So it is here in this specific implementation, it's as if the robot actually moves in the environment and collects those rewards and gives you, you know, what it collected, and then you have another episode and you could calculate the return. So in a way it is online, but you could also have, you know, a list of episodes that are pre-generated if you want and do things a little bit differently. But here, let's move here. You have some episode, right? And then you loop from the end to the beginning. That's because you would like to make use of this recursive relationship right here, as I explained like earlier. So you get the return at the terminal state, which is 0, and then you see, okay, what state happened to exist at time t minus 1. Then you update this state with this return in the sense that you append this return to the list that corresponds to this specific state. Maybe it is SC that happened, so you append this return to this list SC, and then you update also the value function for this specific state to be the average of the returns. So this returns for every state could have, you know, 100 returns, and then every time you just average all of them. And this is one way to do the algorithm, but obviously it doesn't seem right, because first, it is not memory efficient because you store all those returns for every state, and also there are better ways to calculate an average. So I will talk about those smarter methods to handle an average in the next lecture, but this is really a clear algorithm to look at and to understand what's going on. And if you want it to be first visit, you need to tweak it a little bit in order to have exactly one return for every state in an episode. So you still will have multiple returns per state, but every return will come from a unique episode. Here you don't do this constraint, and so you could have multiple returns in the same episode in case there are some loops or something. So in the next video we will see how to do this in a little bit smarter way, and this will be important because this formulation we reach will keep popping up through the entire course. So let's try to have a more efficient implementation of this algorithm, an implementation that does not require us to store all those returns in a list for every state, because this is really memory inefficient. And we need to remember that we are actually calculating an average right here, and there is already an efficient iterative implementation or algorithm to find the average. So let's just remind ourselves of this one. It is not reinforcement learning specific, it is really just for any average. So remember that an average at a specific time step k can be calculated as summation from I equals 1 up to I equals k xi, right, over k. So this is really the definition of the average, nothing fancy. But then you can also say that uk minus 1 is equal to summation from I equals 1 until k minus 1, again xi over k minus 1, right? So this is the same equation. But now we can say that this one here, this one right here, is really equal to summation from I equals 1 up to k minus 1 xi, right, plus xk over k. I just separated the last term right here. Now this term right here from the second equation, this term is equal to uk minus 1 multiplied by k minus 1. So this is equal to k minus 1 multiplied by uk minus 1, right? And then we have plus xk over k. Now we can take this one with us a little bit down and simplify it a little bit to reach a very, elegant equation. So here this is uk, right? So you can say that this is k multiplied by uk minus 1 over k, and then minus 1 over k multiplied by uk minus 1 plus 1 over k multiplied by xk, right? And so the k's cancel out, and so this is uk is really equal to uk minus 1 plus 1 over k multiplied by xk minus uk minus 1. So this is really, an incremental update for calculating an average, and it really makes sense. It has some intuition to it. So it says that the average at iteration k is equal to the old average, and then it can move up or down depending on the relationship between this new sample and the old average. Like if the new sample, let's say, is much larger than the new average, then this quantity will be updated based on this error, if you would like to call it error, right? So if this is larger than the average, the new average will increase compared to the old average, and if this quantity here is negative, then the new average will decrease based on or compared to the old average. So this is the incremental average update. And in the case of value functions, what we will do is, instead of having those list of returns, so this list of g, we will actually only store the list for the value functions, and then whenever we have a new return or a new time step that we calculate, we could just say that the new value for a specific state s is going to be the old value, right? So this is new k minus 1 of the same state plus 1 over k multiplied by the new return that we just calculated minus the old value of the same state. So this is really the same equation right here, but I'm using the return instead of this arbitrary variable x, right? And k here will be the number of times we visited this state if we are using every visit. So you could actually define this, and we often do, so we define this to be an alpha, right? It's like a learning rate or learning parameter. Somehow it will become a learning rate soon, but now this is just alpha, where alpha is equal to 1 over k, or is equal to 1 over the number of times we visited this specific state s. So if we still work backwards, right, from the terminal state, and then we are at a specific, time step t, we look and see which state corresponds to this specific return right here at the same, time step, and then we look up its old value from the array we hold, and then we update this value using this formula, and this is a perfect iterative algorithm that saves us a lot of memory. But in reality, in reinforcement learning, the reason why we like this formula is not just for memory saving, but it's because in general we can control this parameter alpha right here. So we can just use it 1 over n if we want, and this will be, a perfect average. But we can also, let's say, increase it a little bit or decrease it a little bit depending on what you want to do. But generally you increase it a little bit, and sometimes you also have it like just a constant parameter, like maybe 0.01 or 0.1 or something like this. And the reason is, in a lot of reinforcement learning algorithms, we actually try to, evaluate the policy and improve it, and evaluate it and improve it, as we will see later on. And in this case, you really need to be more biased towards newer episodes. So you need to give more weight to newer episodes, and you need to be a little bit more forgetful of the old episodes that were generated using maybe a completely old policy or something, and this will become clearer in time. But I'm just trying to tell you that you could be more forgetful by making alpha bigger than 1 over n. In this way, you will give more weight to the new sample compared to the older samples, and sometimes or often you actually need to do this in reinforcement learning, and this is why this formulation is actually used in the general sense in almost the entire remaining part of the course. But now there is a big problem with Monte Carlo evaluation in general, which is you need to sample a complete episode until the end before you can do one update to the values of all states in this trajectory, and this might be actually slow, and we can find better algorithms that depend on the idea of bootstrapping that make this a little bit faster. So imagine you have a robot, you have an expensive robot, and then you try to collect enough trajectories to do policy evaluation for one policy, and maybe every trajectory requires half an hour or something. So in order to have 100 trajectories, then you spend 50 hours, and that's for one policy. And then you use this policy, you evaluate it, and then maybe you also act greedily in a policy iteration fashion to improve the policy. Now you have a new policy, and then you again need to collect 100 trajectories, and everyone takes a lot of time. So I mean, this one here, this policy evaluation, this Monte Carlo policy evaluation algorithm is a little bit slow, and so we will prefer later on to use some other variants that are actually quicker to evaluate a policy. So let's start with that in the next lecture. So the Monte Carlo policy evaluation algorithm is nice and easy and simple, but it suffers from this problem that we talked about in the previous video, where it is actually slow. You need to wait until the end of the episode before you can have any meaningful update to the values of any of the states that happen to exist in the trajectory, right? So what we want to do now is we want to find some variations of this algorithm that allows us to do more frequent updates to the value functions. Okay, so let's remember the update rule that we reached in the previous video. So we can say that we update the value of a specific state st based on the following. So the value that we store in our table or cache of the same state, this is the old value, right? Then plus some update rate, alpha, and then here we have a target, which is gt, minus the same old value, right? And we mentioned that this value right here controls how much we would like to trust the latest sample versus the older ones, right? So this is really the update rule for Monte Carlo. And the reason why we need to wait until the end of the episode is we would like to get GT, and we say that GT is really equal to, or by definition is, the reward at the next time step plus gamma multiplied by the reward, like 2 steps from now, plus gamma squared, RT plus 3, and so on, until you get to the end of episode, right? So this is why we wait. But now, are we forced to do this? Can't we do something a little bit, quicker? And the answer is yes. We can actually, instead of waiting until the end of the episode, we can, take a couple of steps and then estimate the rest of the return until the end of the episode, right? So we can, for example, say that GT is also approximately equal to, maybe we take one step and then we have gamma, and then for the rest, we actually just estimate the rest of the return by plugging in here the value function of st plus 1, right? So it is still on average gonna be equal to this return if you have, again, a lot of trajectories, like 1 trillion trajectories or something. So for every one of those trajectories, you get different rewards, and then you also get a different next states, and then if you average the values of all those next states you get, assuming you know them for now, like assuming you have someone telling you what this value is, then you could actually estimate this return without waiting until the end of the trajectory if you have enough, samples, right? Or in other ways, you could say that if you use this update rule, but instead of waiting for GT until the end of the trajectory, you just substitute this equation, but you have a lot of samples, a lot of trajectories, then on average, the value function will actually be correct. Of course, there is an assumption here, a rough assumption here, that you actually have some way to knowing this value, the v of st plus 1, or the value at the next state, right? But this assumption has been with us as well in dynamic programming. This is actually bootstrapping, right? So if you write all of this into a single equation, then you are saying that the update rule for this modified algorithm that we call temporal difference algorithm, so this is temporal difference algorithm, we say that the value of state st you assign here, so the value, or you update it by this quantity, which is the value of the same state, but the old value of the same state, right? Plus some learning parameter or some update rate, and here you put the next reward and then a discounted estimation of v of st plus 1. This is now your target. This is now kind of an estimator for GT, right? Minus the old value of st. So in a way, this is very similar to the bootstrapping idea we did for dynamic programming. We are updating an estimate towards an estimate, or using another estimate. So when we did this for dynamic programming iteratively, for every round, we kind of assumed when we did something like this, v pi of s is equal to pi, or summation over a, pi of a given s, multiplied by r of s and a, plus gamma multiplied by this summation, probability of s prime given s and a, multiplied by v prime of s, or v pi of s primes, right? This is the Bellman expectation equation. So whenever we updated the value for this state right here, we kind of assumed that this one is fixed and known, and then we made an update to the value of this state right here. So we are doing something actually very, very, very similar. Let's just remove this here. So we are doing something very similar. We are updating, in this case, an estimate, which is this one, towards another estimate. But this, on average, will also be a good estimation for the return, GT, that we want. And the reason is, the same intuition we had before for the dynamic programming, which is at some point, if we imagine an MDP with, some terminal state or some goal states, at some point, some of the states close to this terminal state will actually be updated based on the reward of this terminal state, for example, and then this information will actually keep spreading through the system. But again, we don't need to have a terminal state with big reward or big penalty for this idea to work. And the reason is, anyway, this estimate right here, this term that you are updating towards, or this target that you are updating towards, is anyway more grounded in reality, because you have this reward right here. So this reward is gotten from the environment directly. So anyway, you are saying, you know what, I have some estimate of st. It is an estimate, it is a guess, right? It is what is in my cache right now, and I want to make it a little bit better. And this is actually a little bit better, right? This is a little bit better because it has some component that is really grounded in reality. You get this from the environment, so this is not a guess, and this a guess. So in a way, you could think of it as, partially a guess, like a partial guess and a partial reward from the environment is definitely better than just a guess, right? So you are updating a guess towards some quantity that has, a mixture of a guess and something grounded in reality, right? So this is roughly the intuition of this update, but more formally, you could just say that this term right here is a good estimate for the return GT if you have enough trajectories and if you keep visiting all the states sufficient amount of time, then this actually will converge to something correct in the long run. So what I described right here is called the temporal difference method, and this term, this entire term right here, is called the TD error. So maybe more formally you could say that VST plus, or VST, you update it by the old value of ST, right, plus alpha multiplied by what we call the TD error, okay? And the TD error is really just the error, so it is, in this case, it was RT plus 1 plus gamma multiplied by the estimated value of the next state, whatever it was, minus V of ST, the old estimation of the value of state at time t. So this is called the TD error in this specific case. Now what I covered here is actually called one step TD error, but if you think about it, you could also have something different. You could say that I need to update ST based on the old ST, then alpha multiplied by something minus the old value here, right? And here we could put any estimate of GT. So we used the Monte Carlo estimate, which is until the end of the episode, but we also used the one-step return if you want. So you take one step in the environment to get a reward from the environment and then guess the rest or estimate the rest. But you could also do something different. You could take two steps in the environment. So you take RT plus 1 plus gamma RT plus 2 and then estimate the rest. So do something like this. So now this is ST plus 2 in this case, and then minus V of ST. So this is another way. So this is called the two-step TD. So two-step TD error, right? Or you could have three-step, four-step, or in general n-step TD algorithm. So for n-step, you estimate the return as being equal to RT plus 1 plus gamma RT plus 2 and so on, and then eventually you have gamma over n and estimate the rest using the value of ST plus n. So this is called bootstrapping. Again, you are updating an estimate, which is this one, based on an estimate. So this is again bootstrapping. Okay, so this is the idea of an algorithm that allows you to make more frequent updates, because now with every step you take in the environment, if you use this one-step temporal difference, you take one step in the environment and then you update this value directly, right? You take only one step and receive one reward, and then depend on your estimation, your current estimation of the expected discounted future reward from state ST plus 1. So you take one step and then make an update, and then you take another step and make another update, and so on. So the update frequency here is actually like much quicker, but we also say it is biased. It is biased because it's really biased towards your initial, estimation here, or towards your guess right here. So you are biased to be closer to your guess, and your guess might be not completely correct, right? So it is a biased estimate. But again, if you have, a trillion trajectories or a lot of trajectories in the limit, those eventually will tend up to be working very well, because the more you take steps and the more you sample trajectories, the more of those rewards, real rewards from the real environment, you will gather, and so the more the entire system will be grounded in reality. So when you start, you could just start with saying that the entire vector or array has all zeros for the value of all the states, and then it will be a very bad estimate. But then as you go on and on and on, you receive real rewards from the environment, and eventually your estimates will become better and better, similar to what happened in dynamic programming. And so eventually things will work out well if you visit all the states a sufficient number of times. So this was maybe the mathematics of what we're trying to do. In the next lecture, I'd like to provide some intuition on why this actually works, using some toy examples, but I think they will help very much, because we will actually realize that the temporal difference method, it's not worse actually than Monte Carlo. Sometimes, even though that we are doing this bootstrapping, it actually sometimes makes more sense not only from an algorithm speed perspective, but also from the perspective of what we are trying to do really. Sometimes this will make more sense even in theory, even if both algorithms, we could make them, work in the same speed. It actually sometimes makes sense to use this temporal difference idea. So see you in the next video. So in the previous lecture, I argued, and I hope it was a successful argument, that if I want to estimate GT, one thing I could do is to record, RT plus 1 plus gamma V of ST plus 1 for a lot of trajectories, like an infinite number of trajectories ideally, and then if I record those values and just average them out, it is actually a good estimate for GT. So this was my argument. In this lecture, I'd like to show a little bit of an extra formal proof for the same thing before we dive into the intuition of why the one-step temporal difference algorithm might actually be better than Monte Carlo, in some cases at least. But I'd like to give some more, formality, because there is a subtle point that I would like to talk about in this formality. So I would like you to remember the definition of the value function. So the value function at state ST is by definition equal to the expected value of GT given ST, right? So this is the definition of the value of a specific random state ST. Now we also know and have shown before that GT, so here GT is equal to the immediate reward plus gamma multiplied by GT plus 1, and all of that is conditioned on a specific ST, right? And this is an expectation, so we can separate it into the addition of two expectations. So this is really equal to expected value of RT plus 1, given that at time t I am at state ST, right? And then I have gamma multiplied by the expected value of GT plus 1 given ST, okay? So this is really still V of ST if you want. Now, if you look at this term right here, what is it asking us? It is telling us, suppose you are at state, a specific state at time t, so here you are at time t, what is the expected return from the next time step? Not from here, but from here. So again, as we did something similar to this before, but here you could move to multiple next states, right? And for every one of those states, you could have a different return on average or a different discounted return on average. And the value you want here is the average of those returns starting from the next time step right here. So in a way, you could say that the first term is, the same, RT plus 1 given ST. But the second term is the average of all of those, returns, expected returns at those different next states that could happen, right? So this is really equal to the expected value of ST plus 1, given that at time t you were at ST, right? So this is really equal to this one in expectation. Again, that's because you want the average value of the return that you could have starting from here, right? And then you could see that from here you could land at any of those states. All are consumed into the same random variable ST plus 1, and so it's really the expectation over all those values, or the average of all those values, if the word average makes it easier for you, right? So this is really the estimation of the value of state ST. So this is the target that you would like to calculate. If you could calculate this term right here, you will have a pretty good value or estimation for this value function. So in a way, our target, the target that we would like to reach, is this quantity. Now there is a very nice thing when you have expectations and you want to estimate those expectations, it's really easy for you to sample trajectories. So whenever you see an expectation of something that you can actually sample, you should get happy, because now you could create trajectories and maybe start at a specific state S that you want to care about. So suppose that ST is now a specific state SA, then you could start multiple trajectories here, so you get different rewards and next states and rewards and next states and so on, and then you get another trajectory with a reward and next state, reward and next state. And also I'm assuming that the actions are already converted into an MRP if you'd like. So now you have another reward and next state and so on. So you have an expectation plus an expectation, and whenever you have expectations, you could really just create a lot of examples and just average them, and this averaging will respect the probabilities that are represented by this expectation, because you are sampling according to the expectation. So there are a lot of things that are embedded here that I'm not really writing formally, but you have the policy you are operating based on, and you have the state transition probabilities, but anyway you are acting in the actual environment, right? And so the state transition probability already exists in those trajectories. Like if the environment tells you that state S prime can never be reached from state S, then you will never find a trajectory that has S followed by S prime for a specific S prime pair. So I'm just trying to say that this sampling here still respects the environment, but in a way that is implicit. And this is why when you do this average, it is not something that is mathematically incorrect. It is actually mathematically correct to do this average, as long as you are acting in the actual environment and receiving rewards from the environment. So for example, if the environment gives you like a reward of 100 very rarely and the reward of 1 very often, this will be already shown into the trajectories, and that's why averaging them is actually a good estimate for the expectation. So now this is the target we want, and we can calculate this target using those samples. So for any specific sample, we can say that we should update the value for ST based again on the old value of ST plus some parameter alpha, and then we try to go towards that target, right? Target minus the old value for this state right here, and this target is a sample of this addition of those expectations. So this target is really equal to RT plus 1 plus gamma multiplied by V ST plus 1, which is really the same result we reached in the previous lecture. But in this lecture, I didn't start by saying that this quantity on average is a good estimate of GT. I instead started from scratch and tried to get this relationship directly as a target for this value function right here directly. And you could argue that this is really the same, but I just view them as slightly different perspectives to reach the exact same equation right here. So anyway, I hope you are now convinced that this is a valid target to aspire to reach, and also that with the help of bootstrapping, if you have enough trajectories and you visit all states enough amounts of time, you will get more and more grounded in reality by those rewards, and eventually everything will work out quite well, and you will get a good estimation for all the states in your MDP. See you in the next lecture. So in this video, I'd like to give more intuition about this one-step temporal difference algorithm. But before I do this, I have one tiny note from the previous lecture that I'd like to iterate upon a little bit, which is, in the previous lecture, I mentioned that the expectation of GT plus 1 given ST could really be replaced with this value right here. And I kind of argued about this intuitively, but I also would like to, give a more cold reason for this using the laws of probability. So expected value of GT plus 1 given ST. Okay, this is what we want to calculate. Now there is a simple rule in probability that tells you that the expected value of X given Z as random variables is equal to the expected value of X given Y all given z. Okay, so this is a general rule or law of probability. And if you use the same here and apply to this one, you could really condition gt plus 1 on anything. So the expected value of gt plus 1 given st is expected value of gt plus 1 of the expected value of gt plus 1 given anything, and we can choose st plus 1 here if you want, all given st. But now this right here by definition is the value function of state st plus 1. So this is really equal to v of st plus 1. This is the definition of it given st, and this is the result that we wanted to reach anyway, which is this one, right? So this is maybe a more formal analysis on why this correspondence is true. Okay, so this is all that I want to say about this point. Now let's try to give more intuition about the difference between one-step temporal difference learning and the Monte Carlo learning. So I'd like to give you an example that illustrates this difference. So let's suppose you are going home from work. So we have home, and let's say you reach a point on your road here. Let's call that state A, okay? And then you have two roads to take to home. So one is maybe this one. This is the first road, and maybe another one that it is actually a little bit taller, okay? Now this one is shorter, but it is a very dark road. And suppose you have a policy, the policy you are evaluating is always take shortcuts. So policy is take shortcuts, okay? And you want to evaluate this policy. So now this road right here, let's call it road 1, will save you like 10 minutes of walking. So you really prioritize going into this shortcut. So your current estimation of the value of SA under the current policy is really high. Let's say 100, or high in general, because this is really a shorter path. But now this path is dark, and in the middle of it you get to a state SB. So in the middle of this dark road, and then you hear some people coming closer to you, some big people, and you suddenly become very scared because now you are in a very dark road and there's a group of very big and serious people coming over, and you are thinking, you know what, they are gonna rob me, I'm gonna get hurt. And so suddenly you think that the value of this state is very, very bad. So you think that the value of SB is really, really bad because you think you are going to get robbed, right? Now, in temporal difference learning, you immediately update the value of SA based on your current estimate of the value of SB, right? This is what we say. We say that in this equation right here, we update the value of ST based on the reward we get plus our current estimate of the value of ST plus 1, right? So now at SB, you think SB is really, really bad, and so you decide to update SA a little bit into the direction of being bad, right? So the result is, given that, you move SA to be a little bit worse, okay? Based, of course, on this alpha parameter. So this is what happens in temporal difference learning. But now, those group of people turns out to be really peaceful and they don't do anything, they're just minding their own business, and you end up reaching home successfully. So you have successfully terminated an episode without getting robbed, okay? Now, if you were using Monte Carlo, the value for, or the update for state A in this entire episode will actually be positive because you reached home successfully. So when you do Monte Carlo, now, you just get a positive update because you didn't get robbed. While when you do temporal difference learning or temporal difference, evaluation, you actually get the value of state A under the current policy, it gets worse. Or maybe in other, terms, you could say that the action value of SA and going into the shorter path gets lower. While in Monte Carlo it gets better. It gets actually better because you anyway reach it home successfully. So now if you think about it, which is really better? Like, which should you wait for Monte Carlo estimate, or should you do this iterative, or like quick update, I would say, or more frequent update. In this specific example, I think actually the temporal difference makes more sense and does a better job. And that's because on average, if you spend every day going into this, risky road or like dark road, you are eventually bound to get robbed actually. Maybe you were lucky today, but if you try out trillion episodes or trillion days of going back home from work, you are eventually gonna get robbed. Like the value of SA under this policy is really not great. You got lucky in this one specific instance because those group of people was like a good group of people, but you can't guarantee this, and this is really risky. So updating your estimate of SA based on your current feeling at SB actually makes sense more than waiting, for the end of the episode, right? So this is like a fundamental difference between the two. Now, in the limit, they both will give you the exact same result, right? So if you have a trillion episodes, even in Monte Carlo, you are gonna, get robbed at some of those, episodes, and then you will really update, you will have a very bad, overall return at the end. And then you will update SA to go, the value of SA to get a little bit down anyway, but this will take more time to converge. So in general, Monte Carlo in practice takes more time to converge compared to the temporal difference learning. We can have a similar intuitive example for the same idea roughly. Suppose you are driving your car and there is a distance of 100 meters between you and the car in front of you, and under your current policy says if there is a distance of 100 meters, try to make it like speed up until it is like 20 meters, maybe something stupid like this. So you actually follow this policy and you speed up significantly, but then the car in front of you also, presses the brakes, or slows down at the same time. So you eventually end up at state where you are terrified you are gonna have an accident, right? So again, in this case, so the initial state was A, right, where you had 100 meters. Now at state B, this is the state where you think you are really gonna die, you are really gonna have an accident. So this has a very, very low value. The value of B under the current policy is very, very low. So you immediately, if you are using temporal difference learning, you immediately update the value of state A under this policy to be very low. So now you say that if I have 100 meters distance between myself and the car in front of me, and the policy is to speed up to close this gap, this is a really, really bad policy. So again, in temporal difference, you do this update kind of immediately. Of course, depending on how you implement the algorithm, but intuitively this is what you do. But then maybe by luck, you get saved and you don't have an accident. And again, you reach your destination successfully. If you have Monte Carlo evaluation, the value of state A under the current policy would actually have a positive reward or a positive change to increase its value a little bit, because you did reach your destination successfully. So again, this is the same idea of temporal difference. Maybe it gives you more frequent updates and it gives you it converges faster practically. So this is what I wanted to say about the intuition of the difference between the two. In the next video, I'll cover some more differences between the two. Okay, so we should be kind of convinced now that if you have an infinite number of trajectories, the temporal difference algorithm and the Monte Carlo policy evaluation algorithm will reach the exact same values for every state. But now there is an important question, like what if we have limited amounts of data? What if we have a limited amount of trajectories? Would the two algorithms still converge to the same values or not? And the answer is actually no. They will reach values that are significantly different. And this is because if you think about it, the Monte Carlo algorithm kind of treats every state independently, right? Like from every state, you just count the rewards until termination and then, do an update or do the discounting and then do an update. And then for another state, you also count the rewards until termination and do discounting with gamma and so on, and then do the update. So in a way, Monte Carlo algorithm does not enforce any Bellman equations in its processing, right? Like it doesn't enforce that the value of A and the value of B need to have any sort of relationship. It doesn't try to enforce that. While if you think about the temporal difference approach, it really tries to enforce this roughly, right? So it tries to say something like the value of ST should have some relationship with, so ST plus alpha multiplied by or t plus 1 plus gamma v st plus 1 minus v of st. So if you look at this equation for the temporal difference update, it tries to enforce some relationship between this value and this value. Monte Carlo does not try to enforce this, so it does not try to enforce any Bellman relationship, and this is why the two approaches might end up with different estimations. And to make this clear, let's actually have a concrete example. So suppose you have just 6 episodes. So you have maybe an episode where you start at state A, you get a reward of 0, and you end up in state A, you get another reward of 0, you end up at state B, and then you get a reward of 0 and terminate. Then maybe you have another episode that goes like start from A, you get a reward of 0, reach B, then you get a reward of 1 and then terminate. Then you could have another one that starts B, get a reward of 1 and terminate. Then B, get a reward of 1 and terminate. Then B and get a reward of 1 and terminate. Then B and get a reward of 0 and terminate. So suppose you have those 6 episodes right here. Now let's see what would a Monte Carlo estimate, end up doing. So the Monte Carlo estimate treats every state completely independently. So suppose you have gamma is equal to 1 for simplicity for this MDB. The Monte Carlo will really look at every state and try to figure out from this state what is the total return I got from each one of those states, right? So let's look at A. So A happened like one time here, one time here, and one time here. So A happened 3 times, okay? Now let's suppose we are doing every visit, Monte Carlo, not first visit, so every visit. So A happened 3 times. For this time, the return is 0 and 0 and 0, so it's really 0, and we have gamma equals to 1, so no discounting, so it's really 0. And for this one, you also get a g of 0, and for this one, you get a g of 1. So out of 3, you got 1 only once and 0 twice, so this means that under Monte Carlo, every visit, the value of A you get is really going to be equal to 1 over 3, right? Because you get 0 plus 1 over 3, and so the value of A is 1/3, okay? Now the value of B for Monte Carlo every visit, you could calculate it similarly. So B happened 1, 2, 3, 4, 5, 6 times. 6 times, and out of those 6 times, 4 had 1 and 2 had 0. So really it is 4 over 6 or 2 over 3. So this is the estimate you would get from a Monte Carlo estimation. Now, does this really respect the MDB? The answer is no, and let's see why. So before we go into temporal difference, let's actually try to think what is the best MDB that represents those episodes that we call, the maximum likelihood MDB. This is the MDB that really represents those transitions to the best of our ability. In a way, so let's get maybe this a little bit to the right here, and let's try to think of an MDB that represents those. So we could see here that whenever we go from A to A, the reward is always 0. It never happened that you went from A to A and the reward was 1. So to the best of your understanding, you could say that you have a state A here, and you could have a transition from A to A, and the reward is always going to be 0, right? Now, what is the probability of going from A to A versus going from A to B? Because sometimes you also go from A to B. So you went from A to A here 1 time, and you went from A to B here and here, so 2 times. So it seems, again, to the best of your ability, probability of going to A given A is equal to 1/3, and then you can go from A to B, so you can go to B, and the probability of B given A is 2/3, right? So this is really an MRB, not an MDB. I'm ignoring the actions, but this is fine since we are doing policy evaluation, and for any policy you can convert an MDB to an MRB, right? So this is really fine. Now, what is the average reward if you go from A to B? So here from A to B you got 0. Here from A to B you got also 0. So it seems that the reward here is going to be 0. Again, every time you go from A to B, you get a reward of 0. Now from B, you seem to always reach a terminal state. So, and sometimes you get a reward of 0, and sometimes you get a reward of 1. So you could actually model that as having two terminal states. So maybe the good terminal state, maybe call it G, and here you get a reward of 1. And maybe there is another terminal state, which is L, and the reward here is going to be 0. Now the probability of going to G from B seems to be 4 times out of 6, so this is 2/3, and this one, probability of L given B, is 1/3. Okay, so in a way this is actually one way to construct a model from data. And maybe if you want to do model-based reinforcement learning, you could first use the data to construct a model, and then from this model you can solve it using Bellman equations or anything like that to get the values. So this is maybe one way of constructing a model out of data, or converting a model-free problem into a model-based problem if you want. But this is not what we are trying to do here. So now we created this MDB. Now, if we want to solve this MDB to find value functions that respect this structure or this relationship or those transitions between states A and B, then we could actually use the Bellman equations themselves. So for an MRB, the Bellman expectation equation for an MRB is really going to be the value of any state S is equal to the summation over all the possible next states, probability of getting to the next state from the current state, multiplied by the immediate reward of S and S prime, plus the discounted next state value, so V of S prime, right? This is the Bellman expectation equation for an MRB, for the state value function of an MRB, if we decide to use the R of S and S prime notation, not just the average R of S notation. So let's actually apply this to both states B and A, and let's start from B, since B is closer to the target goals, and I think it will be actually easier. So the value of B is going to be equal to, you have two paths, so it's really the probability of the first path is 2/3 multiplied by the reward, which is 1, right, plus 1/3 multiplied by this reward, which is 0, and I'm ignoring the value of the next state since those are terminal states, and by definition their value is 0. So V of B, if you solve the MDB, is going to be 2/3. So this is if you really solve the MDB. Now in Monte Carlo we also get 2/3, so the value of B seems to be the same. The difference is going to be in the value of A. So the value of A is maybe more interesting, because the value of A is going to be equal to the probability here is 1/3 multiplied by 0 plus the value of A, so 1/3 multiplied by 0, which is the reward, plus gamma, which is 1, multiplied by value of A again. And then you have 2/3 probability of going into the other path, which here has a reward of 0 and the value of B. So here you get 0 plus the value of B. And we know the value of B is already 2/3, so we could really just put here 2/3, right? So this means this is equal to value of A over 3, and then 4/9. So this is equal to the value of A So you could say that value of a minus 1/3, so 2/3 the value of a is going to be equal to 4/9, which is really 2/3 multiplied by 2/3 again, and you could cancel this with this. So value of a is going to be 2/3 if you really solve the maximum likelihood MDP using the Bellman expectation equation, which is different indeed compared to what we had in Monte Carlo. It was 1/3 over here, but it's now 2/3, so there is indeed a difference. So what we established now is Monte Carlo doesn't respect the MDP, but we still need to show, at least in action, that the temporal difference algorithm will actually converge to the same values as the direct solution of the Bellman equation, because now we have solved the equation like directly. We didn't really use this iterative nature of the temporal difference algorithm, because we have this learning rate or learning parameter alpha that is a hyperparameter and so on. So we need to show that the temporal difference algorithm will actually converge to the same result. We go try it here. It kind of makes sense because this is the algorithm update rule, and it will theoretically never stop updating until the equation is satisfied. And in this specific example, this equation will only be satisfied under those numbers, because under those numbers you will get that v of a is going to be v of a, which is, like we said, is 2/3 plus alpha multiplied by RT plus 1, which is always 0, plus the value of b, which is like 2/3, minus the value of a, which is 2/3. And so 2/3 minus 2/3 is 0, and so it will give value of a is 2/3. So it will really not try to update the value of a if it already reached somehow 2/3. It will not try to update it again. And the same for the value of b. The value of b will also converge on 2/3. So what I'm trying to say is the temporal difference algorithm, once it reaches this value, it will have no motivation to update its estimates again. But in the next video, actually, I'll show this using code, and I will talk a little bit more about this parameter alpha, because this is a hyperparameter in the iterative algorithm, not in the Bellman equation, and it has a lot of effect on what the algorithm ends up doing. So see you in the next video. So let's have a closer look at what the code implementation of the temporal difference algorithm might actually converge to, and how sensitive is it to the value of alpha. Now let's actually think a little bit before going into code. Like, what do we want the value of alpha to look like? Now, I want you to remember when I talked about the incremental, average update for the Monte Carlo evaluation, I just said that if alpha is big, this means I favor the newer samples more than the old ones. And if alpha is very, very small, like less than 1/n, less than the number of samples, then I'm really favoring old, values over the new ones, right? So this is the balance. And if alpha is equal to 1/n, then I really get the actual average, right? So we want to get this intuition with us, and now we have a batch of data samples, like 6 samples, like we defined here. Now, in order to implement this algorithm, we actually put those 6 samples in a data set or something, and then we loop over this data set over and over and over again. This is kind of like an epoch. If you are familiar with neural network training terms, this is really an epoch. So an epoch is a pass through all the data you have, and you do multiple passes or multiple iterations over those over the entire data set. So you have multiple epochs, and this is how you train a neural network in supervised learning or in regression learning and so on. And this is what you do when you have data in general. So this is what we do. And now, if alpha is too big, then we are trying to tell the algorithm, like, if you find something you do not expect in the newest sample, like panic and go all the way in order to correct this error. And now in the next sample, if you find something that also does not satisfy, the Bellman equation right here, also panic. So a large alpha, similar to a large learning rate in your networks, actually leads to oscillatory behavior, because you see a sample, you panic, and you update all the way in order to make this specific sample have zero error if you can, or have as little error as possible. So you might like overshoot. Like this actually happened in your network as well. If you remember, like in your networks, we wanted, let's say, to minimize a loss function, something like this, right? So maybe this is the weight and this is the loss function, and you want to reach this minimum of the loss function. And maybe you have a weight that puts you here in the loss function, and now you see an example that tells you you really need to decrease the weight. But instead of decreasing the weight by a tiny amount, you decrease the weight very significantly. So you go all the way here, right? And then you get this weight right here. Let's go W dash. And then in the next sample, I mean, assuming you have only 2 samples, then in the next sample, it tells you, you know what, you want to reach here, right? But again, the alpha parameter or the learning rate is too large, so you overshoot and you move all the way back to this point right here. And then you do this again and again and again. So you keep oscillating, and if you print at every sample, you really get those oscillating values for the weight, and the value of the loss will never be minimized because the learning rate is too high. This happened in your network when you try to minimize this loss or this error. And in a way, this TD algorithm is also trying to minimize the error, which is really the difference between the target and the current estimate. It really is trying to minimize, the TD error, which is this quantity. It is trying to minimize this quantity, because if this quantity is 0, then you get V of ST is equal to VST, and this means the algorithm is converged, right? Now, there's an interesting point here. Like, if you print at every sample, you will see the oscillatory behavior. But if you only print at the end of every epoch, and if you process the samples in the data set in the same order for every epoch, so in our case here, the epoch is just 2 samples, then you might always actually reach the exact same point right here. So when you print them, you have the illusion that you converged. You will have the illusion that this is the best weight you could ever get, and the error will actually not be minimized. But you might, if you are not careful, you might think, okay, you know what, I'm getting the exact same value every epoch, and this means the error is minimized. But this is not really the case. You can't guarantee that the error is minimized, except if you also have another check of by the Bellman equation, and really see for yourself that the Bellman equation is satisfied. So I'm trying to say that just the fact that the value that you print for the weight, or for the value function in our case in reinforcement learning, stops updating, this really doesn't mean you converge it to the correct solution, because you might have a stable number, but you really are not at the minimum of the loss function or the error function, okay? And we will see this actually when we dive into code. So all what I'm trying to say is you need to treat this alpha the same way you treat the learning rate in your network. So you need to make it small so that you could make, small steps, and then have something like this, and maybe smaller steps and smaller steps and smaller steps, and then you will actually reach the solution that you want, okay? So a lot of theory, but let's actually go into the code right now. I had this code written up. I don't think I need to go into the details. You trust me if I tell you that I implemented the algorithm, but I defined gamma to be equals to 1, and now I choose alpha to be 0, 0, 1. So I mean here the comment is low for now, not high, but I will show you what happens if I set it to a high value later. And then I have 10,000 or 100,000 iterations, which is a lot. And then I define the same transitions that I defined in the previous lecture. So the exact same 6 transitions here. So from A I get a reward of 0 and I end up A, and then I go to B, then I get a reward of 0 and terminate, and so on, right? So those are the exact same 6 trajectories. So this is a trajectory, this is a trajectory, and those are the remaining 4 trajectories. And then some groundwork here, some code here, just to calculate also the Bellman solution. This is not really needed, so this part is not needed to do the temporal difference algorithm, but this is needed for the final check that I talked about, that you need to really compare the actual solution of the Bellman equation to the solution you get from the TD algorithm to ensure you really converged, and that you just are not stable at a wrong fixed point. Like if you keep oscillating and print at the end of the epoch, you might keep stable at a wrong fixed point. So this code right here is really trying to compute the MRP solution, and then there's a function that checks that both solutions are the same or not, or the tolerance between them. I mean, I'll share this code so you could check it if you want, or you could also just ask Gemini to write it for you. But anyway, the most important function is this one, the TD0 update. It's called TD0 for a reason that I'll talk about actually very soon. But TD0 is the one-step temporal difference algorithm, and we will see why it's called TD0 like in a soon future lecture. But this is really the update rule. You get the target, which is RT plus 1 plus gamma multiplied by V next. And then the TD error is really the difference between the target and the current estimate. And then you try to update in this direction with this learning parameter alpha. So now, if you just run it, you will see that it converged after those, 100,000 steps, but actually it converged much earlier. But I don't stop the calculation here. But anyway, let's see actually what this table is trying to say. So maybe I need to go very much up here. So this here tries to get you the value of A and then the value of B, and also checks if the Bellman equation is satisfied for A and for B. Okay, so at the beginning the Bellman equation is not satisfied, but then after just 5,000 or maybe even 4,000 or 3,500, you start getting a yes for the Bellman expectation equation being satisfied. And as you might expect, it gets satisfied for B first, and then after a couple more iterations, it actually gets satisfied for A. Okay, so this is if you use an alpha of 0, 0, 1, and you actually get the value that we got mathematically. Remember, we got 2/3 for both A and B, and this is really what you get right here. So you get roughly 2/3 and roughly 2/3. Okay. Of course, up to the tolerance that you define. But now if you go here and change the value of alpha to be maybe 0.5 and run the same algorithm, you actually never converge. So interestingly, you reach this value here. Let's go up again to just see the column names. Let's go up to see the column names. So for the value of A, this is the value of A and this is the value of B. Okay, so 3 to the left. So you end up with some values that don't change, right? Those values kind of don't change. So you might be under the illusion that you have converged, but actually those are wrong values. I mean, the value of B is wrong and the value of A is wrong. Like both here are actually wrong. And this happens because of this oscillation that happens for the learning parameter alpha, and you actually never converge, right? And this is why you always have a no here, because the Bellman equation is not satisfied for either A or B. So you need to be very careful with the learning rate alpha. There is also an interesting graph in the Sutton and Bartow book that also tries to quantify the effect of alpha. So it has one problem, any problem you want, any MDB you want, and then you have some samples, and then it really tells you the effect of alpha. So this reddish color is really the Monte Carlo. Remember, Monte Carlo iterative update also has an alpha that could change however you want, and then you also have TD. Right, so you have those blue lines are TD and the red lines are Monte Carlo, and you could notice two things here. First, in general, the error of the TD algorithm family seems in general better than Monte Carlo. They seem to converge faster to lower errors. Okay, so this is what we theorized about, or like had some intuition about in previous lectures. But also, if you look at TD only, you see that for alpha being 0.15, you get this curve, while for alpha being 0.05, you actually end up at a better spot earlier. So this really illustrates what I was trying to say. Like, if you choose alpha, you need to choose it to be small, and small is better, but obviously extremely small is also not great, because then the update is very tiny and you take super long time. So you need to balance alpha to be small enough to not oscillate or converge to a wrong fixed point, but also you need to make it big enough that you converge in a small amount of time anyway. Another approach that people use sometimes is to use a decaying alpha. So you start with a little bit large alpha and then you decrease it over time, which is also another method people use in your networks with the learning rate.